Last one to turn in my slides. I'm sending them. So I tested them. No, no, no. Now you can. No, I think it's the mic. Yeah.
Hey Lorenzo, how's it going? How are you?
Good, good. Let's do this.
A button on the top. Okay. Hello, everyone. Very good morning to all of you, both to the in-person attendants and the remote audience. I welcome you, all of you, to our VFIO IMMU and PCI micro conference. Just a quick reminder before we start about a few main topics. First, the micro conference is really intended to be a lively debate. So if you have questions, if you want to engage with the speaker, you're very welcome to do so. The micro conference is not intended to be just a presentation. So just interact with your speakers if you have the topic that currently being presented at heart. Another thing, especially for our remote audiences joining online, if you have a question or if you want to interrupt the speaker and just raise some problems, voices, and opinions, please do ask us to pass you the microphone in a catch box. It helps people who are joining remotely to catch the essence of the questions. In terms of the schedule, we are very fully booked this year, almost up to an hour. Therefore, we will try to make sure that all the presentations and talks are meeting the time slots to make sure that everyone can have the allotted time. And as usual, follow the code of conduct. So that goes without saying. So with all that, again, welcome, and I will hand over the presentation to Dan, who is kicking off the micro conference today. Okay.
Okay, thank you for having me. I am going to talk today about the work on TIO, and I call this a series of modest proposals because I don't know if the origin of that modest proposal is something maybe not so modest, that is hard to accept, and this TIO is that. But I mostly want to focus on discussion. So your questions about what is going on here. So I have some prompts to, if people can't think of things to talk about, but there's so much to talk about. I'm going to put up some pictures so you can point at things. But for the most part, this is not a presentation. This is a discussion. But I'll go through kind of what the overall problem statement is, try to catch everybody up to the same level. Where are we at? Hey, we got some stuff in 619, where we're going, and then spend most of the time on discussion. So this eye chart is the problem statement. The problem is that folks want to assign a device to a VM, and they want that device to talk to that computational VM's private memory. In order to accomplish that, we need to have platform support. Those are those blue and green, and that's Intel and AMD and ARM and RISC-V. They all have various specs for this. We didn't happen to catch this early enough to standardize that, so everybody does it a little bit differently. But those are all mostly similar, and then they have to go touch all the purple. And so starting from the bottom, this is like the bare metal hardware, the kernel, host user space, kind of virtual hardware in the guest kernel, guest user space at the top. All that purple is all the shared stuff that we all care about to get this feature supported. The only way that we're going to touch all these subsystems in deep ways is to have consensus. It is to come together and say, hey, by the way, person who is very busy on their own subsystem over here trying to keep it up and running, we want to bother you with this little feature for TIO. Yes, it might be a little bit invasive or different than what you're used to, but don't worry, you get support for 4 different vendors all at once, and these 4 vendors have agreed ahead of time that this is what they want. We can still negotiate, but if ARM and Intel and AMD and RISC, if we're grappling with it, everybody else is gonna. If we're arguing, everybody else is gonna stay back until we stop arguing. So, the whole point of this effort is to mediate those discussions, come to consensus, and present proposals to all these subsystems. The way going about this, and this we can talk about alternatives, but this is the way we broke it down into different phases of the work. I would say that we've completed phase 1. Phase 1 is get the PCI layer to understand that a device can be both authenticated and have its link encrypted, and have that establishment mediated by something called a TSM, a TE security manager. And Linus made fun of me last time I sent a pull request saying, what the heck are all these acronyms you guys keep coming up with? You guys have a disease. So I spelled out all of the acronyms in this pull request and was much more successful. That has one vendor's implementation, but the other 2 vendors that are ready is ARM and Intel, and those are in something we have a staging tree for those. They have some dependencies. They couldn't hit 619, so we just merged the AMD thing. Yes, the Intel person is okay merging the AMD stuff if it advances the commons. The next phase we want to go to is the guest side, and this is assuming that everything on the host is already taken care of. And the reason we want to do that is because that is kind of the longest lead time. Once the guest side can understand a confidential device, that starts the pipeline of people being able to bring their own VM images to clouds. It's a little bit easier for the clouds to say, hey, if the host kernel changes aren't quite ready, we can carry a little bit of stuff out of tree, but it's really hard to get your customers that are bringing their own images to accept out of tree stuff or that kind of thing. So get the initiative started. Have a skeleton. That's this phase 1 bit. Build on that skeleton for get all the kind of phase 2 flows, which is all the guest. We call it the lock and accept flow. Take the device that you see in your guest, lock its configuration so it can't change. Validate that the host has set up all the secure memory and all the secure DMA, secure MMIO correctly. You check the device's certificates. Once that's all good and everybody's happy, you accept it and off you go. The place where I think we're going to spend the bulk of our time in, and this is where many of the Modest proposals are hitting, is all the changes we need to do on the host side to set up private MMIO and to set up private DMA. And this is where I'm making new friends all over the kernel in terms of figuring out crossing over lines that I didn't know were battle lines, and just kind of stepping on landmines. So I think phase 3 is where we're going to spend most of our time as a community. And then I know that attestation is a very huge part of all this, but in terms of like the kernel mechanics, I'm okay if that comes later in the flow. Like, I'm happy that folks like Matthew and Lucas and other people are looking at some of these ABIs. I'm happy to let those debates play out, and we'll adopt whatever they do. But in the meantime, we have a lot of work to do on just the mechanics of getting this stuff set up. And then attestation, the plan is fill that in on the back end. This color gradient thing is basically how much risk is there, and so how much purple you see is related to how much purple is here. Like how much of the solution is touching core pieces versus kind of the TSM driver layers, where a lot of people just kind of nobody really cares. The rest of the kernel doesn't really care about Intel's ABI versus AMD's ABI so much, talking to the firmware. So we're assuming the community doesn't have heartburn with that, but they're going to have a lot of heartburn with the purple stuff. So that's that color guideline. So now I have a few pictures kind of showing which phases touch which pieces. We can refer back to these. I don't need to walk through all of them, but phase 1 was pretty simple. We touched the PCI core and the device core. And we have some new sysfs ABIs for connecting a device. And connect means that you are now authenticated and your link is encrypted as far as your TSM implementation is concerned. The next phase is all, like I said, is all guest side. We still need to figure out, or we still need to negotiate with like the driver core folks to get them on board with the concept that a device can be that a device needs acceptance. We probably need some new mechanisms around not auto probing devices, if that's a policy people want to say, like, I want a chance to validate all devices before they start talking. So that those are things we need to negotiate with the driver core folks. Phase 3 is where we get to all the fun. And Alexei has a question. Go ahead, Alexei.
Hey, thanks for pushing my stuff upstream. Phase 2, it includes bits in the host for guest request and HTTP related stuff.
It does. I mean, it implies a communication from the guest to the host, but I'm not sure that I mean, and we might be able to get some of the host side stuff upstream as well. I'm not sure we're going to have the entire DMA buff IOMMUFD work done at the same time. So that's where we'll have to play with it and see if we can get that guest request stuff upstream as well. For the room, guest request is basically all the marshaling of data, like interface reports and certificates and measurements that you need to ask the host to give you, talk to the device over the SPDM mailbox, get a whole blob of stuff and to ship that back into the guest. And and because we have no standards, each vendor does that communication differently. So that's what Alexei's talking about with guest request. But was that the comment, Alexei, or more, there's more?
That also includes lock and accept, which is in my case handled on the host.
Yeah.
So.
Yeah, some of these, that's also a difference where some of these TSMs have guest side, like on TDX we have TDG calls. We can talk directly to the module. That side on SebTAO, it has a ship over to the host, but yeah, we're trying to abstract that away from the rest of the kernel. Those kind of details. So wait, back to phase 3. So phase 3, and this is where we can start talking about some of the discussion points. One of the main things we need is a way to describe private MMIO and kind of coordinate that with KVM mappings, because KVM doesn't really want to understand that things are MMIO or not, and we want to kind of handle that outside of KVM. And so Yiloon from Intel has a proposal that Alexei and Anish are both adopted in its kind of staging form, but it touched on a sore point of the DMA buff implementation with some of the graphics folks, and we are realizing that we need a better lifetime model for DMA buff. And I need you to check that at Jason.
So I'm very happy to report that in 6.19, the DMA buff, VFIO, and IOMMUFD parts of this diagram have been merged at about 75% completion. So we're getting a lot closer, and I intend to start negotiating the last piece with Christian the new year. So Yiloon just needs to work on the KVM parts.
Okay. I mean, I'm hoping that it's the 75% complete doesn't mean that the last 20% is the hardest part. It's going to spend 90% of the work, but that's the worry. But we'll see.
Christian has said some positive things, in my opinion, to the current proposal. So I think maybe not, but also yes, definitely for sure.
I mentioned the tab Q&A about estimating. Do not estimate badly to your program management. Yiloon posted his version of this stuff in January of this year. And so, in terms of trying to predict when things are going upstream, please do not make bad predictions.
It's moving at light speed then.
It's moving at kernel speed.
75% of the infrastructure, the aside from KVM, merged. Amazing.
Yes.
In 1 year's time. It's wow. It's like
that's actually pretty good.
I think it would be coming to like private DMA heaps, right? Or DMA buffs. Like you need some user space. You need to expose a heap to the user space where allocations can come from. That's not there.
No, it's different. Yeah, it's different.
So okay. So what we do have merged now is VFIO can create a DMA buff that wraps around its physical MMIO space, and we can pass that DMA buff to IOMMUFD, which will program it into the IOMMU. And the piece that's missing with Dan here with KVM is we want to pass the DMA buff to KVM and have KVM install it in the EPT or the S2 or whatever, have it be just like the IOMMU does. And as part of this, when we talk about confidential compute, the DMA buff can convey the meta information of is this MMIO private or shared, and that will influence how it's mapped into the KVM and IOMMU S2s. That's where we're going. The challenge with DMA buff is that DMA buff only works with DMA mapped addresses, and as we're programming S2s like in the IOMMU, in the CPU page tables, they have to be physical addresses, and DRM has a historical trauma with dealing with physical addresses. So we need to work a solution.
Yeah. The easy thing would be, we'll just pass a PFN instead of a page with DMA buff, and that was so easy. But life is fun.
Yeah. So we are also dealing with this private DMA, but we don't have this KVM and all stack. But it's the secure media pipeline use case where we need to work with private DMA, and where host doesn't have access to the buffers, but only the devices have. And now we have like guest and the devices that are associated with guest.
Yeah.
So I think it's different, but it's just the private DMA.
This is private DMA.
Both side.
Yeah, and I think one of the things that makes this interesting is that we want to dynamically convert devices from the shared world to the private world, like maybe that's kind of foreshadowing some discussion points to catch people up on. But so DMA buff looking good. I think we need to touch IOMMUFD, too many letters. And currently, I think we have maybe 2 or 3 different implementations of that. Was there an aspect of the ARM implementation that you think is different than the Intel and AMD that you want to?
We can all come to one kind of IFTLs. So basically what we are actually looking at is there is this bunch of IFTLs, IOMMUFD IFTLs, which kind of like the TSM framework would call into, and then like all the 3 architectures now have to agree that IFTL interface is the same. So one of the things we could do is, like the TSM framework, one of the implementation can be pulled up and then everybody align into that so that they get all the structures correct. And then I could possibly post what I have in the ARM tree, and then we'll see if I can kind of.
Yeah. The way this has been going is basically everybody show their cards. Then we look across and see if are we different because of architecture reasons that we need to incorporate, or are these just arbitrary things? Work through all those details, and then then come to a consensus. That consensus is showing up in a tree called tsm.get #staging, and that tree is not in Linux Next, but it is at any given point in time. It shows the state of the state of consensus. People might have patches that are beyond that in their own kind of vendor trees, but this is kind of the clearinghouse for all these approaches. There's a document in there. I'll add to these slides after the talk to put that link in there. But there's a document in there called the maturity map, and in that document is basically a list of all the phases, like I talked about before, topics in there, and then there are various levels of maturity. Like, is this just an RFC? Is this something actually that we've got consensus on? Is it something that we're willing to put in Linux Next, or are we completely done in this upstream? So at any given point in time, you can kind of check that as a quick rubric of where we're at. But there are no kernel estimates of when this stuff works complete in there. So just maturity. Okay. So some other topics, discussions we would need to finalize. Is this protocol for what I'm calling lock preparation drivers? One I talked about before, that we want to dynamically shift devices from the shared world to the private world. One of the reasons to do that is some of these devices aren't ready to be locked until the guest does some configuration to them, and so you need a driver to do the configuration. But then you also want to switch into secure world later. And Jason showed me this trick that they're doing with the VFIO, where they have special drivers that you can bind to VFIO, do your locking and your setup, unbind that, then bind the real driver after you've accepted it, and it's in the secure world. So the main driver will only see devices ever in the secure world, but we might have this kind of dual driver situation for folks that can't arrange for their devices to arrive ready to locked.
That assumes that all the device quirks that are needed for getting the device to be locked are same, right? I mean, if you are looking at a generic driver that you load to kind of get the device ready to be locked, that means whatever needs to be done is generic, right? What if it's device specific?
That's the point.
The mechanism Dan is talking about is you can declare, I think we kind of called it a variant driver in the driver core. You can say, I'm a PCI driver and I'm of type VFIO, for example. And then your mod alias file says, it distinguishes it. So you can go in user space and you can say, I have this PCI device. I know it's mod alias string. I want to find its VFIO driver for it. So there can be multiple drivers that are matched based on PCI IDs. So you could have one for you, one for me. And I mean, I feel that this lock preparation, if you've built hardware that needs that, you're probably going to be sad for lots of reasons. So please don't take it as advice from the kernel community that you should build that kind of hardware. But if you unfortunately did, this is how we imagine making it work.
Yeah.
Mod alias for that.
Yeah. Before Anish had the mic, he was saying, that this is something we would do with mod alias. But ideally, the device arrives ready to lock, ready to rock and roll. So, but the reason why we want separate drivers is because the Linux DMA subsystem does not understand the idea of this initiator, this device can talk to two kind of DMA worlds at the same time. Because you can think of it like literally unplugging the device from one system and plugging it into another memory domain. And so the rule we're having in Linux is those transitions cannot happen while the device is bound to a driver, while it might have DMA mappings. You have to effectively unplug the device as far as the driver model is concerned and replug it back in the secure world. I know some people have use cases, we want our device to talk to two different worlds at the same time. That is explicitly something that we're kicking down the road to get the base support going. So for now, it's you can run a shared world, you can run a secure world, and then we'll figure out the DMA subsystem will need to be much more mature to be able to handle that kind of dual world situation.
So usually we have a similar situation, like device has two modes, like it has like two stream IDs in IOMMU, where it has to access secure buffers or protected buffers and normal buffers at the same time. So yeah, it's the similar kind of situation. We are also would be dealing with the IOMMU programming, like device needs to use a different stream ID when it's accessing protected buffers and a different stream ID when it's accessing normal buffers. So yeah.
But have you taught the streaming DMA API how to do that?
Yeah, actually that's a work in progress, really.
So not yet. Okay.
Yeah.
Like one hack that can satisfy in the mean term is if you can control how many virtual devices your device puts out, you can have two devices, and then you can solve the coordination in your driver, like so driver to driver communication to say, hey, shared driver do this, hey, private driver do that. But then Linux is never confused that one device has two different DMA models.
Yeah, it's like two devices. We are trying to create two logical devices for the like video device. Then each have their own stream ID.
Yeah.
You'd probably be happier if you use substream IDs. You would probably be happier if you use substream IDs, PASID, right? That would give you an easier programming model. You could put your private traffic on a PASID. You could program the PASID into the IOMMU yourself, and you don't need to mess around with the DMA API and don't have these problems Dan is talking about.
Yeah.
So substream IDs are something that we have implementation and support for today.
I think we have a question up here with Hannes and then Chris. Yeah.
I really would not want to go the direction that we have to rebind drivers, because that is will always be a pain, because they come and go and you have events, whatnot, logging things don't. It would be far easier if we just indeed go with a sub-device model that once we lock the driver, that a new device appears, which is locked. And this then basically is kind of a child device, however you name it. SRV would definitely be beneficial if you could just say, all right, lock the driver, and then any SRV function you spawn from then on will be locked already. So that would be fine. Would be an easier model all around. If you just say, right, okay, don't do the rebind thing, do a sub driver and keep the old driver there.
Oh no! Well,
why not?
Because the DMA API sees that the initial driver as the thing we're programming. So like it's the sub device doesn't have its own appearance to the IOMMU.
Yeah, that's the problem. Okay. Oh, you okay there? Sorry. I don't think it's as big a deal as you're thinking, Hannes, because keep in mind, this is still confidential compute, and you still have to do the attestation step in user space. So, I mean, you're just basically saying attestation is a little bit more complicated. After you attest it, and to lock it, you have to do a few more steps in user space. And my kind of hope is that there'll be like an attestation accepting helper in user space that just manages this for everyone. So it won't. I hope that it doesn't. Yeah, it'll just do like it'll do the locking and the run, and it'll figure out if it needs to load a special driver and unload it, and it'll just do all of this for everyone, and it won't bother anyone.
Yeah,
it's not like you have to special. Yes, but a horrible complex piece of software that lives in user space besides the validator, which is already a
very complicated. Yeah, but we're generally trying not to have drivers like ideally a driver that's written today would not need to change. You just send it a secure device, and it's none the wiser. And all the details about safety and locking, accepting are handled outside of it. Willie, go ahead.
Jason, you said use just PAS IDs as a solution. Are those now widely supported in the PCI ecosystem? Okay, because when I was looking at something like 8 years ago, they were not deployable on certain vendors.
Especially for what we're talking about here, where you have special ARM hardware with special IP with like a special DMA path. Yeah, you can put the what's called the SSID on your interconnect bus and wire it up to the ARM IP that already exists and has all the software support. And on modern server CPUs, I think all the vendors' latest products all have passive support for PCI, so you can use it there too. Yeah, it's better.
Okay. We have a couple, 1 more minute, 2 more minutes, right? Yeah. Okay. Yeah. So just so people understand the flow, though, the host side is going to get the device into a state where it's bind ready before it hands it off. So everything the TSM, basically the TSM will be ready for the guest to say go, the guest to say lock, handle a bunch of transactions, and then for certificates and things, and then go into the run state. So this is the part we want to. This is where we need to make sure that IOMFD is not surprised by its need to go talk to the TSM drivers, but details to be determined. On the attestation front, we talked a little bit about it yesterday. I do think that the TIO case is different enough from the CMA case that we might use the same ABI to dump a certificate chain because that's just a blob, but all the other extra stuff and nonces and evidence and measurements and transcripts and things that the TIO case needs might be a separate interface. In the last minute here, how to get involved. So Linux Cocoa list, like we know and love. We have a Discord channel where we hang out as well. If people want to come join, we're friendly. We have the CCC kernel SIG, and then I learned yesterday that it actually wasn't called Linux kernel, but it's called the kernel SIG. And but talking to John, I think we're going to rename this to the OS Special Architecture Special Interest Group and try to get participation from other OSs as well, because these TSM ABIs affect all of us. So maybe that's a place where we can all talk in the open. And then the link to the staging tree. And yeah, come send some patches. Thank you very much.
Thank you, Dan. And I would like to invite Jason next onto the stage.
Let's go here. All right, everyone. Not quite as tall as Dan. So I got this slot to talk about primarily the generic page table in hopes of getting it merged, but Jorg has merged it now. It's in 6.19, the first 30 patches or something. So I've changed this a little bit into a review of like what are the next steps, and if you want to help, like I've given some slides about guidance about how would you convert a driver and how would you add another format. Hopefully people find that helpful. So every time I come up here, I try and give people a little summary of where we've ended up in the last year with the new IOMUFD features. And this year, the pink boxes are quite large. So we did really well. We got some, I think, kind of innovative things like the MEMFD support for mapped file really significantly improves VMM launch times, and the change process allows the VMM to sort of upgrade itself with exec and not disrupt the VMs that are running, which are, I think, really novel features. And we've also now got 6.19 has basically full support for virtual IOMMUs on VTD and SMMU in the kernel, and the QMU work is getting very close to being merged, I hope. It's starting to look like it's converged nicely. And then finally, we've got the DMA buff stuff that we just talked about with Dan has landed, and the consolidated page tables. So the next year, hopefully we'll see AMD will complete their VIOMU. They've got patches on the list that are looking pretty good, that get about halfway there. Kernel Live Update is a microconf that's going to happen in the afternoon to explain that. There's like 3 talks about those features, I believe. Jacob is working on no IOMMU support. It turns out that people actually want to use VFIO no IOMMU support. Like, I know Alex and I had sort of figured it was like some weird thing that we don't need to worry about, but it turns out people have actual use cases that kind of almost make sense. So we're trying to make that a little more robust and easier to use. And we made some progress on the ARM MSI routing in the last year so that it's actually usable with the RMR approach, but we'd still like to see that get completed so that the ITS routing works the way ARM architected it to work. And then finally, the confidential compute, which Dan talked about. I understand that, you know, from Dan's slides that patents exist, they just haven't been posted on the mailing list, so I can't link to them. And then we'll talk about the page table optimizations in the rest of this. So, I mean, overall, I think IOMMUFD has been going really well. We're getting a lot of people coming with ideas and features, and I think we're going to start to see it really mature in the QEMU ecosystem in the next year. And I know that several CSPs are already running it in large scale production. So it is doing what it's supposed to do. So the generic page table, I talked about it briefly last year. It is an effort to unify all of the page table code and all the IOMMU drivers. We have like 6 copies of these algorithms. They're all basically the same. I know Will was pointing this out when he was reviewing the very Silicon driver recently that has the same page table algorithm as a Rockchip driver, like almost exactly identical. And like AMD and Intel have similars, and so does ARM, and it's all quite a duplication. And the duplication prevents us from adding new features in an efficient way. And we have a long list of page table related features that we'd like to improve, but trying to do it and doing it across 6 different copies of just to cover the server chips is far too difficult. So I've taken on this task of making a single code that runs the page table algorithms for IOMMU that works on all of the drivers that we have. So this is very similar to the MM. Like the core MM code for working with page tables runs on all of the architectures, and the architectures provide like a little bit of architecture specific stuff. So the design is kind of similar. 6.19 includes AMD and VTD support. RISC-V support is on the mailing list. If anyone from RISC-V is in the room and would like to help, please test it. Please tell me what's broken. Let's get it merged too. I have about 3/4 of ARM in my tree that I hope to get finished the next year. And that will give us basically all of the modern server drivers. From then we can have a discussion, maybe in 2027 if we want to also do the embedded drivers, maybe the historical ones. Like it certainly would be nice to move all of the all of the 64-bit ARM page table drivers to use the new code, so we don't have both page tables concurrently. But we can talk about it. We can see what it looks like. So I'm going to talk a little bit about what this is. I assume everybody in the room is kind of familiar with how CPU page tables works. They're basic radix tree data structures where you take a 64-bit or 32-bit virtual address and you slice it into indexes, and then you walk a tree. So in this diagram shows the 57-bit kind of configuration with 5 levels. It's very similar to what x86 would use, and it's showing the labeling that the generic code uses. And this was one of the points that a lot of the reviewers like to bring up is the numberings that I've chosen. Like level 0 is at the least significant bits, and level 4 is at the top, and it's 0 based. So if you read the specifications for all of the different implementations that I've done so far, no 2 are alike. Everyone has chosen some different variation of this. ARM does it backwards. I think it goes starts at 1 and goes higher for some reason. And Intel likes to use 3-letter acronyms: PGD, PMD, PTE. They have some other ones. I can't remember what RISC-V did, but it was also a different thing. So inside the code, it always uses this. And this is chosen because it's mathematically easy. Having the least significant bits be 0 means that when you multiply out the index, everything, you don't need to make subtractions and adjustments. So hopefully this gives us a nice consistent thing to talk about. While doing this, I also standardized the terms. Again, all the specifications from the CPU vendors all sort of have their own little bits of jargon, and I said, this is what this will use. And it's largely inspired by how the MM works. So we have virtual address is basically the input address, and output address is often called the physical address in specifications. This is a little bit generalized because this often also works on multi-stage translations where the output address is in fact an intermediate address or a guest address or whatever. There's so many different versions of that concept too. And then we have the integrated support for contiguous pages. So this is the idea that if you have PTEs that are physically contiguous, like I think ARM, you can do 16 in a row. You can group them together and the hardware will recognize them as a 64K or otherwise entry. And this gives you better TLB efficiency. So this is a new invention in the last couple of years. The MM has got support for this now across most of the architectures where it exists. But it was kind of retrofitted. It was done first. Like the very, very first implementation I did was contiguous page support for ARM, and then I did contiguous page support for AMD. So in the code, you'll see this slight distinction of something called an entry or an item. And an entry is the grouping of contiguous PTEs, and an item is a single entry in the table. So a contiguous PTE may have 16 items in comprising a single entry. And we follow the MM thing of using leaf and table to refer to the other parts of the code structure. So the integration with the driver has changed as I've worked on this a few times, but this is how it ended up. The concept, and one of the asks, especially from Intel, was to avoid extra function pointer indirection hops, because Spectre mitigations make indirect function calls kind of expensive on some platforms. We want to have the core code called directly to the page table implementation. If you look at the way the existing IO page table integration works, the driver often has to provide a set of stub functions that all they do is reflect one pointer op to another pointer op while doing a container of operations. So we've flattened those. And the way that was done was embedding the domain directly into the page table structure itself, and then the driver can union them together so that the page table code can container of itself directly from the domain. This avoids the function pointer hop, and it's relatively straightforward with some little macros that are kind of reminiscent of Matthew's macros for folios for checking that all the offsets work out. Perhaps this will go away someday and we'll teach the core code to directly call an op in the page table code. But for now, this is a simple way and it gets the introduction. So the first step in the driver is you'd go into your protection or your IOMMU domain wrapper structure, and you inject the page table formats that you want. And this is for AMD. So AMD supports 2 page table formats. They're first and second stage, depending on how you want to think about it, the guest and the host, I think they call it. And this gives you all the page table structure. And then you will use this macro here, IOMMU PT domain ops. I hope that's sort of visible. I tried to make it really big. That goes and inserts the operations with the correct function names so that it's directly binds the page table implementations directly into the driver operations. And then you may provide the operations that the page table code uses at the top, and then at the bottom is the weird bit for dirty tracking, which has the same thing. I hope to get rid of that down the road. And this is right out of the AMD driver, and that's enough to give you a working page table. You have to hook up the flushing stuff according to what you need, and you have to implement the attach and the free minimally. But that's a pretty simple page table implementation. Compared to what it was, that removes like 1,000 lines of code from the AMD driver. Then you have to, in your allocation function, you have to initialize the page table. And all of the page tables have quite a bit of configurability. All the architectures and all the hardware have all kinds of different options. Maybe you support 3 or 4 or 2 or 1 or whatever levels of walking. You might support sign extension or not. There's coherency flushing that some hardware needs or not. So your driver will have to go through and figure out what it wants and set the features and the parameters, and then it invokes the init function to create the actual page table and the domain and everything is then ready. And this is pretty much the extent of what the driver has to do. When we merged the initial version of this, almost all of the bugs were in the lines on the screen that I'm showing you right here from the Intel driver, because it was very hard to understand from their spec and their implementation what they actually wanted out of their page tables. And we had a number of misses where older hardware with some weird kind of settings didn't quite get what it needed. So hopefully we've worked through all of those. I guess we're going to see in the next couple weeks, well, after Christmas. Everybody's going to wait for Christmas before testing, right? But yeah, they've all been very easy fixes, but whoops. And then finally, when you attach a device inside your driver to a domain, you have to program your hardware somehow. So like ARM calls this an STE, it's a DTE in AMD, and in Intel, it's a scalable passive entry or some such. This is where you write the tabletop pointer for your page table. You tell it what kind of geometry it has and whatever other weird rules you might have. And the way it works in the new system is you get the format specific PT info, and you call the format specific function to get the info, and then it pulls it out of the internal opaque data structures and gives you the information that you need to program into hardware. So this provides some modularity. And then in AMD's case, we had the interesting thing with the SME set, which is confidential compute related. It's an AMD weirdness that says that the hardware should walk the memory as encrypted, which doesn't make a lot of sense, but that's where we are today. So it's generally, when I've done the conversions, they've all so far started out with a medium-sized series to clean up and modernize the driver, and then a smaller series to convert the now fixed-up driver to use the new page table things. I find this helps reviewers. It makes the code a little bit easier to understand. So we did this for AMD and Intel, where we reworked their attached functions. And because the domain ops now are single format, you also need to split the domains in the driver. If it's like a first and second stage driver, it now needs separate structs, or separate ops structs at least, and probably separate call paths. We've also found that the sign extension feature in a lot of the hardware is very exciting. It turns out that the people building the hardware didn't document or think about this maybe as thoroughly as they should have. For instance, Vincent discovered, after I asked him some questions, he went to his hardware people and he discovered that the AMD driver does not, in fact, do sign extension for PASID 0 only, but PASID 1 and everybody else, it does do sign extensions. This is really surprising. I think everybody was surprised when he discovered this. But I imagine that other hardware has a similar thing. And I know in ARM land, when we've talked to hardware people about sign extension on the I/O paths, we've kind of discovered that lots of hardware has taken shortcuts, and the physical I/O buses do not actually preserve a 64-bit sign extended value correctly, and there's all kinds of weird broken stuff in the end. So currently in the I/O subsystem, even though the hardware may support a sign extended address space with upper bits, we always turn it off and we don't let anyone use it, so we don't have to trip on any of these weird bugs and issues. And I don't know of any good use case to turn it on, so I think we'll just leave it that way forever, but if somebody has other ideas. And my last bit of advice, which we were able to do for AMD, but Intel is still a maze, is to put the hardware info really close to the place where you actually create the data structure, like the hardware data structure. So on AMD, when it creates a DTE, it gets the info and it sticks it in immediately. On Intel, we get the DTE and we call about a 5-level deep call chain of functions doing all kinds of stuff before it actually reaches real hardware, and it's quite hard to follow. So the other thing you might want to do is you might want to make a page table format. Maybe you have a different piece of hardware. This will not one that I've already done, like a rock chip or a VeriSilicon, for instance. So this also kind of shows how the multi-compilation system works. As I mentioned earlier, it's inspired by the MM, where we have C code that's common that uses a consistent set of names. Like in MM, it's like PGD put or something like that. And here the names all usually start with PT. And the way we make that work is we compile the common C code for every format, changing the include files that are used every time we compile it. That way, the format can provide the correct implementations for the common names, and we end up with a single set of C code. It's very similar to the Linux architecture code works, except the make files actually compile the file multiple times and alter the include files. So that's what I'm trying to show here. You'd start out by declaring your format. This is the C file that actually builds the module at the top. You include the template helper, which has a whole bunch of macros in it, but it distills down to what the second one shows, where it includes some common things, and it includes the format specific ones. Like it's here, it's got defs VTDSS and format VTDSS. And then finally at the bottom includes, it'll include the actual C code to build the operations. And then the format version on the final black box, it'll implement the function, the common function, and then it always defines it to the common name that the C code expects. And it was designed this way to make backtraces and GDB debugging work much better, because when you get to the compiler after removing all the macro magic, you have distinct names for every format. So when you get a backtrace or whatever, you get their names in the backtrace instead of everything being the same. This also helps code indexers and things kind of make a sense of it. So in your Oh, yeah. Jacob.
I was just wondering the flush range feature, is that the page selective validation for TLB, or how is that related to?
Yeah. So all the feature stuff there, the IO page table stuff we had today, it calls them quirks. They turned out lots of them aren't actually quirks. They're just the way it works. So I called them features. Each of them has a comment block that describes what it does or what it's supposed to do. And the ones on the screen here. So flush ranges means that the flushing hardware supports a range flush. So you can say this VA to that VA, take everything in there and wipe it out of your cache. That's distinguished from like what ARM does, where ARM says you have to go and individually target every single IO TLB entry with exactly the parameters that it has and issue an invalidation for each of it. ARM has a future extension called range invalidate, which would then be closer to range flush, although I think it has a few little differences. So the notion is that the integration has to specify the features that matches the hardware capability. In this case, range flush, if you have like x86 style invalidation.
But how is that related to building the page table?
The invalidation code that's compiled in is optimized to match the need. So for instance, there's no reason to build the ARM invalidation logic that costs performance for an x86 page table, because it will never be used.
Okay.
So the features thing is done like this, and that's a really good point, as a micro optimization. The features actually feed into the generic code, and the generic code has something that's not dissimilar to is enabled. And if the features are not turned on at build time, the compiler throws that stuff away. So like, for instance, the incoherent flushing, if your page table is always coherent, then all the code to do the DMA flushing just disappears. It doesn't even have an if statement. It's just gone. So the AMD second stage, for instance, is like that. It makes use of that. So inside the bulk of the header for your format, you'd have to define at least the functions I've listed here. They are enough that the generic code can go in and operate your page table. You won't get contiguous pages. You need a few more functions for contiguous pages. Generally, in my adventures, the contiguous page support has been the most difficult one for the formats to implement, because there's a lot of stuff often going on. But for a very basic format like RISC-V, for example, without the SVNA pot, it's very simple. The code is very simple and clean. Dirty tracking and software bits add a little bit more complexity. If your format is intended to be used with hardware that requires DMA flushing, so it's caching coherent, it has a caching coherent walker, then your format has to provide a software bit. Jacob, can you chuck it at his head? There you go.
Regarding the dirty tracking, do you plan to add a split and merge as well?
Yes, that's one of the objectives of all of this work. So that's another slide that we will just get to, it looks like. The reason you need a software bit if you have an incoherent walker is because we've taken the algorithm that I think Will implemented for ARM64's page table and made it common and shared and used on x86. So this relies on an atomic release and acquire of a software bit in the page table entry to tell you if it's been flushed or not, to avoid some races with the kind of the PMD level. This was a bug that, like, VTD's implementation of coherent flushing actually had this race that ARM had fixed. And as part of the consolidation is one of the many bugs that we fixed in the VTD driver and the other drivers too. So once you've done all of this and you got your basic format working, the next step on your journey is to run the KUnit. Basically like this. The KUnit is split up into a couple categories of tests. The format test here is the most basic test. It goes in and tests all the format functions and tells you if you've implemented your code correctly. In my experience, if you make a mistake in the format function and you try and run the IOMMU test, you get very impossible to understand failures, and it's very, very hard to debug. So I built these individual tests to make that a lot simpler when I was adding formats. Like, I think I ultimately wrote like 6 formats, and I struggled with many of them with bugs using the IOMU tests. So it does things like, you know, if I write something to your page table and then read it back, does that work? Do I get the same answer back? And other basic sanity tests that show that the page table structure functions are basically working. Once you've got that taken care of, then you run all the KUnit tests. And if those pass, then, like, so far, the experience has been it will work on hardware. I have yet to find something that the KUnits aren't catching. So what are we going to do with all of this? What are people's ideas? One of the next medium-sized series I've already written, I'm going to post, is an optimization where if you're mapping something big that has lots of different page sizes in it, instead of calling multiple times and then rewalking multiple times, you'll be able to pass the whole thing, especially to unmap, and it will walk once and sort of realign itself as it goes without having to rewalk every time. This gives about a 10% benchmark improvement alone, getting rid of the multiple function calls and getting rid of some of the logic and the rewalking. The debug.fs dumping, the AMD crew wants to add that to their driver. So the plan is to build something meaningful that doesn't have the races that the VTD implementation has by using RCU. And then we would delete the VTD implementation, and then everybody will get debug dumping for their page tables. RISC-V is on the mailing list, so hopefully we can get that tested and fixed up. And then SMMU v3, the format is written and debugged. I need to also do the integration and the invalidation logic. And then finally, what we're talking about earlier here is to optimize things like DMA map SG or what the IOMMUFD does, where it's putting a batch in. Again, we rewalk every time we move to a new entry. If you're doing a scatter list of like 4K, it's rewalking every 4K, and it's extremely inefficient. So I'd like to clean that up. I'd like to optimize that. And there were some patches on the list that pointed out that the cache flushing algorithm, if you have an incoherent walker, is monstrously inefficient because it's constantly walking and flushing the same line for every 4K. And if we can do efficient batched operations, we can also batch the cache flush, and that will dramatically improve the map SG performance on that kind of hardware. It will also, I think, significantly improve the performance of IOMMUFD's VM teardown flow, which currently has to walk the page table at 4K granularities for the entire VM address space, which might be 100 gigabytes, which is just impossibly done. So, yeah, that's the end of the presentation. If anybody has any questions. Oh, haha.
I go back to the PTL menu config page.
This one?
Back config, nothing in here. Yeah, this one. So I'm wondering, the output address of this config is set to 52. So I'm wondering, is this done intentionally?
I hope so. I think this was something that was in the VTD thing. I think there's this. We talked about this recently. I think it's a kind of an error in their design. The output address, on an Intel platform, the maximum allowed physical output address is actually stored in ACPI, and it should be copied from the DMAR, and it should be put here. But the previous driver, before I worked on it, didn't do that. It just hard-coded 52, so I left it. But in practice, this doesn't do anything except enable some debugging checks, which you can turn on at runtime. So it's not a big deal.
So I'm wondering, yeah, it's okay for the if the driver is running on environmental, I guess 52 is okay because especially for the platforms people are using mostly after Ice Lake, should be 52. But if it's running in the guest, so the value of this address is actually emulated from the host side.
Yeah, I know. I mean, as I said, the only impact is that the debugging code won't fail mappings. But if you're trying to map something that's outside the physical address space of your VM, you've got other problems, and this isn't going to help you. So you're right that it's a minor error, but it doesn't have a practical concern.
Yes. So, I mean, if the guest is running using the wrong value, so it will have to. It can only hurt itself, right? So it's still okay. So actually, our PVL MMU driver is also hard coding this value to 52. But I'm wondering, because I do not want to use CPU ID, and we do not have any interface for now to get this value.
That sounds like a mistake. You probably should have an interface to get that value.
Okay. Thank you.
But again, it's not that important. Just don't put physical addresses in your guests that are outside the space, and you'll be fine. All right. Was there another? Oh, way back there. Oh my gosh.
Okay.
KVM has a similar sort of design for shadow paging, and one of the things that's annoying about it is code indexing and jumping around within the generated code. Have you figured out a sort of solution to that while you were developing this?
Like indexing, you mean?
Like in your editor, jumping into one of these generated
Yes,
functions?
actually, I do have a sort of a solution for that. So the way that it ends up working is that the header files that encompass, like if you wanted to edit the map and unmap function, the header file on its own is not self-contained, so it will not include the right definitions. But what I've done is at the very top, there's like an if def that detects effectively if Clang is indexing it, and then it includes one of the formats, like AMD in my case, is how it defaults. So if you wanted to code index for RISC-V, you could go up there, you could change it to RISC-V, and then your code indexer will work correctly.
Okay, that sounds promising.
All right, I've run out of time. Thank you, everyone. Oops, thanks.
Thank you, Jason, and welcome Alex to the stage. Sorry. Okay.
Hello, my name is Alex Mastro, and I'm here to talk about enabling user space drivers to vend more granular access to client processes. This talk is largely a reiteration of an upstream mailing list tech topic that I sent out back in September, and the link to that is in the webpage for the talk. I'm on Meta's ASIC platform software team. We are responsible for shipping the low-level software for supporting the ASICs that we build. We work on a variety of things, but this talk will focus on the device driver aspect of it. The rough agenda is that we're going to cover what we're doing today and why, the rough direction we want to head in, and some potential ideas for how to get there. So in our current architecture, we're deploying a user space driver that sits on top of VFIO and IOMMUFD. Well, that's a lie. We haven't transitioned to IOMMUFD just yet. We're still using the legacy VFIO containers, but plan to switch imminently. We like this model because our ASIC program is relatively young. We're still figuring out all the interfaces across the various layers of our stack. And it's really nice to be able to just atomically deploy a single package of user space stuff to update the low-level stack for our devices. In this model, the user space driver kind of manages some of the more traditional device management functions like firmware bootstrapping, fault collection, metrics, and resource arbitration. And when new clients come and attach to the user space driver, clients who want to submit workloads to the device, they perform usually these like one-time resource acquisitions from the user space driver, and then the hot path is only involves communication directly between the client processes and the device. The reason why we do this is that any alternative has really unacceptable performance trade-offs. Because we're a user space driver, the only means for communicating with it is some sort of IPC scheme where you either have to go over Unix domain sockets or perhaps queues over shared memory. And no matter what you do there, you're never going to beat just being able to talk directly to the device, which is why we need to share the VFIO and IOMMUFDs with the client today. And what that does is it lets the client mmap the regions of the device that they need to access so that they can, for example, directly submit commands down into the device. In the opposite direction, we need to enable the device to DMA directly into the client process address space. So they also need to be able to create IOMMU mappings into their address space. So how does this kind of organization compare to other users out in the wild? QEMU doesn't have the same problems as us at all because they are QEMU is performing mappings on behalf of a client that's inside the same address space. You don't need to worry about giving some other peer process the ability to create these mappings. Our use case is kind of similar to DPDK. DPDK user space driver networking stack, and their stack supports running in a multi-process mode, kind of similar to ours, where there's like a primary orchestrating process, and you can have these secondary DPDK processes, which also need to directly communicate with the device. And in that model, they also lease the VFIO. I think they lease the VFIO group FD to these secondary processes, and then the secondaries pull the VFIO device FD out of it and then mmap the bars. One piece that's different there is that the client processes don't need to create IOMMU mappings. From what I understand, the primary creates the mappings once against shared memory, and then all of the processes kind of use the shared memory, the same shared memory, which has already been mapped to IOMMU. So the downsides of the current approach are that we have pretty poor access hygiene. The scope of access that the clients need to accomplish their work with the device is very narrow compared to the access that they have. The clients really only need to be able to touch specific slices of the bars and only need to be able to map specific parts of the IO address space. But they have equivalent capability to the user space driver because we're sharing the entirety of these VFIO and IOMMU file descriptors. So despite the fact that we're collaborative, a misbehaving process could, stomp on parts of the bars that they shouldn't, reset the device, or unmap other processes' IOVAs. Okay, so one question you might have is that, why do you, given that you're implying that clients can initiate DMAs. Like, why do you care about trying to lock down this access? And the answer is that the user space driver, in combination with the device from our Harvard policy, can still constrain the side effects of client process access to the parts of the bar region that they've been given. So, for example, you could have, as part of this vending of access, the user space driver configure the firmware that any DMAs you receive over the queues in this part of the bar address space are only allowed to target specific regions of device memory or specific host IOVAs. Okay, so our initial goals that we're interested in exploring is enabling user space drivers to enforce better access hygiene in the form of restricting the parts of the device that the client process can access. And then a follow-on to that is to be able to control the lifetimes of any objects that are leased that convey that access. We're not interested in treating client processes as completely distrusted at this point. And also, we don't really care about enabling processes themselves to vend nested restricted access to another client process. Any questions so far? Okay, so yeah, I think the basic options for lifetime control are, or like lifetime management, are giving user space drivers either the ability to explicitly control access or observe access that it's lended out. So by control, I mean like forcibly revoke access that it's given to clients. And by observe, I mean have some means of detecting when the access has ceased. And I'm not convinced that we absolutely need both just yet. I think we need at least one of these because with just one, the user space driver at least will have the means of guaranteeing exclusive access to a specific part of the device over time. With control, you can just yank it away. With observation, you can just block releasing the outstanding part until it's been returned. Okay, so we can use some existing tools for simplistic lifetime observation if we assume that the access conveying things are scoped to the client process lifetime. The user space driver can just derive a PID-FD for the client process, wait until it exits, and then use that as a proxy to determine whether that client's access, whether the things that lend to that client are like no longer in use. That works out as long as the clients themselves don't transfer the file descriptors to another process. So it's kind of like, a workable but incomplete solution. Okay, so getting to how the rubber might, start to meet the road. Yeah, as Jason covered, VFIO and DMA buff support just landed in the Linux VFIO tree. So thank you very much, Leon, if you're in the audience, for pushing that through. And I think our desire to vend restricted bar access would compose very naturally on top of DMA buff, because DMA buff represents some number of slices within a bar backed, with a file descriptor in front of it that you can give to a user space process, to give to a client process. So instead of vending the entire VFIO device FD, the user space driver would allocate a DMA buff that only has a view of the parts of the bar that the client needs to access and vend that to the client. The main thing that's missing for that to be actually useful for the client is the DMA buff ops mmap support, which I think there should be line of sight to. There might be some interesting details to work out around revoke The existing mmap revoke semantics in VFIO PCI are primarily concerned with zapping the mmaps created by the VFIO device FD. So we would need to figure out a way to get that working with DMA buff. Jason has a question.
So much safer. I think you just need to make the VMA link to the VFIO address space, and everything will work for you.
Okay.
And I'm pretty sure you can do that without any trouble.
Okay.
I think.
Okay. Okay, so yeah, mmap seems like we can get there. And then some more, new things that we might want if we want to move beyond this simplistic lifetime observation I described earlier, are either user space initiated DMA buff revocation. I'm not sure if there are any other use cases besides ours that would benefit from that, but this would basically give the user space driver a way to yank access from clients that it's given the DMA buffs to.
So this is all on server, right? I believe server use cases.
Server use cases.
So coming to that, I was having the same question. It can be useful for some of the auto safety use cases, which is where. Auto safety use cases, because in the auto, what happens is that most of the drivers and surfaces being reduced in a kernel to get the safety, which I don't know much, and to get into the user space. And this is what VFIO and hacks around it is being used to get all of these kernel primitives access into the user space, and which is not yet in upstream because it's pretty much ported from the QNX world to the user space and then just making it work with the Linux. And that's where their entry point here, and then they need a DMA buff, and they kind of starting adding that. And by the way, I'm from Qualcomm.
Okay.
So that's why it's like I'm saying auto use case. So
I see. So
Igor is there, so probably he'll add more maybe.
Yeah. Sorry, I had a question for you. So in your use case, who is the DMA buff? I guess
multimedia.
Who is exporting it, and who are you yanking?
So we have a driver kind of which gives all of one SIM driver, you can call it, which provides all of this back to the user space, so that all of my multimedia driver, even display driver, or even remote proc, which is what we talk to the other coprocessors, and everything comes to the user space, so that we can reduce the surface in the Linux.
I see.
So yeah, we can talk offline. But
okay.
Hi, I also do automotive, but for NVIDIA. One thing we are working on is we have code, is having multiple address spaces in EL1. We use ARM. So there we have different write properties to the same memory region inside the kernel, but then we expose this also to user space, because we use pages with different write properties to create different processes, so that a kernel space which has a lower safety level cannot overwrite pages of a process which has a higher safety level. But then we also have the problem of dealing with device drivers which use VFIO. So this looks interesting for safety, really, also in that perspective.
Okay. Yeah, I'm not sure if there are any. Besides the vending to other user space processes, I'm not sure if there would be any benefit to be able to benefit for user space initiated revoke in order to yank access from in kernel DMA buff importers. So I don't know if. Yeah. Right. Yeah. Okay, and then the complement to the control is. If we don't have that, if we have the ability to observe DMA buff ops release, then that would at least give USD the ability to passively wait until this least DMA buff lifetime has ended. Okay. Question.
I'm gonna try and suggest a different solution for this. The way we do it in the RDMA driver is that we have the kernel driver arbitrate the allocation of the bar addresses.
Mm-hmm.
Would you consider doing that to the VFI driver?
I'm not sure that the VFIO driver would have sufficient context for owning the allocation policy in that case.
Sounds to me like a generic type of implementation.
Oh, okay. So you're saying if we put a generic bar allocator in the VFIO driver, maybe.
And my next question is, how do you sync between these clients and the main process which boots the device?
How do you sync?
Sync between these client processes with the main process that boots the device. If that main process goes away, what happens with all these differences, right?
Yeah. I mean, that is a failure mode that is, I think, that user space drivers introduce.
Yeah.
And I think that like you can try and put as much policy on the device side as possible to kind of have there be some kind of detection when the user space driver has gone away via like heartbeats or something that
It could be a simple protocol where you have main process initialize everything, and then you can allow this DMA buffer revoke them after that process.
Right. Yeah, that's a good point. Having there be, if there was a backstop that could automatically revoke once it determines that this USD process has exited.
I would move some of that architecture.
Yeah, makes sense.
Yeah, I think just a follow-up on that question. So I think you mentioned, what's the real motivation to use this user space driver?
What's the real motivation to do what?
To use the USD, this user space driver. Because his suggestion was to write something in the kernel space, right?
Yeah.
But what's the real motivation to do this USD?
So we found that we like writing user space drivers. We it's really nice. I mean, so it's like really nice to not have a significant footprint in the kernel for all the all the things we've needed to do so far in production, like haven't required like specific ASIC specific policy for our device in the kernel.
Okay, because I saw in the initial slides you mentioned you want to give the developers one single package, right? I saw was that the motivation? Like
that's part of it. Yeah, it's nice that you can have multiple versions of the driver bound against different devices, like that own different devices. From like an operational standpoint, it makes pushing out updates quicker, a lot easier. You got your developer workflow is all in user space when you're working on the stack.
And then you have the there's a slide you have this for life cycle. Yes, this one, right? So that means there will be only one user at a time, right, on this device.
So the slide is showing that, but we support multiple concurrent clients that might be accessing other distinct parts of the device.
Okay.
So.
Okay, it's a multiple client, but not a multi-tenant.
Sorry. It's a single file descriptor. Which one is a single file descriptor?
It's a single file descriptor. It's a shared file descriptor.
What is it?
All the clients are accessing the device through one file descriptor, right? From the kernel point of view.
For the VFIO and IOMMU case, yeah.
Yeah, kind of following up where you were going with this is that what you're trying to do is put in a little bit of access control, I think, at the front. You just basically want to a minimal amount of restrictions so you can say this client needs to play in this space. That is definitely a kernel thing, but it's not a big kernel thing. Mm-hmm. You just need to put in just enough of a kernel driver to get that and then continue with your model as you have it here. and then you don't have a maintenance burden because that kernel driver is just going to sit there and not really change over the years. So you'll be fine. But if you keep going this direction, what you'll be doing is something very similar to the ancient evil of the X driver, which I'm not an X driver developer, but they built a big user space process. Originally, you had to run it as root, and it supposedly owned all the security. And as you know, that doesn't actually work. So you know, 30 years later, you don't want to start with that model. Just go directly to getting your kernel access control, and then build this stuff as shown on top.
We've been talking that this kind of sounds like MDev, and we've kind of been trying to figure out what is the future of MDev. And if you have a device that doesn't really have discrete RIDs, VFs, things like that, maybe that kind of driver that you can actually create a device and give that to a client process and destroy it and figure that in bar sizes and whatnot.
Okay, I'm kind of unfamiliar with MDev. What is the premise of?
It's basically just a software-defined device.
Okay.
It's how VGPU originally started, that you have a device that doesn't support IOMMU separation of devices.
Okay.
And so you create a software abstraction of that device, and you can have it mediated, basically. M is for mediated.
I see. Okay.
It strikes me that what you're trying to do is very similar to what Intel tried to do with SIOV, Scalable I/O Virtualization. You want to take a single PCI device and you want to slice and dice it cheaply and assign it to different functions. And I think that your hardware team has made a small error by not supporting PASID. If you had PASID, this would all be very, very, very easy. You could do what all these people over there are telling you to do and it'll be fine. Maybe do that in V2, I don't know. But for now, if you want to work around it, like, I don't have any problem with what you're showing on the screen. A revoke function call is super easy to add. It's not an issue. I'm more interested you hopefully can finish your presentation and talk about the IOMMU side.
Yep.
That's harder.
Okay. All right. Let's talk about that then. Okay. Yeah. Just an aside. If you're doing this, you need to be able to, you know, stride your bar regions appropriately so that they can be properly isolated. Not a restriction unique to USDs. Okay. So for IOMMU FD access granularity, we want to give clients the ability to just only to be able to map unmap to their specific allocated part of the IO address space. And we also want to avoid putting policy in the kernel that would need to be arbitrarily dimensioned. So one of the things that Jason brought up on the mailing list when this discussion was first circulated was whether there would be scope to add some kind of BPF enforced access policy, where the general idea is that the USD would attach a BPF program to the IOMMUFD instance, and then when that instance receives syscalls, the BPF program would be provided sufficient context about the syscall arguments, the caller context, in order to yield an access verdict. And this is probably the area I have the least line of sight with, just due to unfamiliarity with BPF. I did see that there's some precedent for attaching BPF programs to instances of opened devices in the Linux infrared remote control subsystem. It looks like doing it that way requires a specific new kind of BPF program type. But I know, Jason, you were alluding to some, ongoing work which could be adjacent to this in CComp or LSM that, someone on your team.
We have eBPF LSM
right
already, where you can attach a eBPF program and you could hook it into different things. For your purpose here, I'm wondering if you could maybe build like a proxy file descriptor, like a file descriptor that's an eBPF file descriptor, and when it gets an ioctl, it runs an eBPF program. And if the eBPF program says yes, then it just calls the same ioctl on another file descriptor. So it's like a wrapper, like a firewall kind of thing. And that could be very general. And you could use that with like firmware control or RDMA or to do the same idea where I know people want that there too. I don't know anything about eBPF either. Know anything about eBPF? No, he doesn't want to share. But like you're right, like HID has done it, and Input has put eBPF stuff into theirs too. So, you know, I noticed on your name badge, I think it said Meta, right? So they know everything about eBPF.
Right.
I wish you luck.
Yeah. Okay. We only have 3 minutes left, so there's only one more slide. So just to recap, you know, I think some of the discussion here is around, you know, whether this is a problem worth solving in the first place. And so far we think so, but, you know, open to revisiting that. Second point is whether there would be implementation line of sight to some of the like more obvious things like DMA buff ops mmap and revoke, and that seems to be true there, but again, IOMMUFD and BPF is less clear. And then future composability, like if we were to add these features to the kernel, to what extent would they encumber, you know, the degrees of freedom that the kernel has to pursue other unrelated features, but then has to carry around this baggage. Yeah, that's it. Thank you.
So I'm not sure if you have questions.
Yeah, so to second your point on using PassID or like PassID in the process, like a lot of like the current hardware already supports it quite well. And the thing is, again, I kind of understand if you want to have a particular level, like security level on a component that you control versus whatever you give to some other component. But I think this folks could be like a much more like on the application level, some way to like differentiate context, like either by having a process fork or other things that are naturally fitting into this FD model, right? So from that side, having PassID as an additional option, I think would be a very good idea.
Yeah, we want PassID. I agree. Yeah,
but you don't have it at the moment.
Right. Any other questions? Right. Thank you.
Thank you, Alex. Now we have a little bit of a break for half an hour, so everyone can grab refreshments, catch up with the speakers to discuss some topics, and I will see you later in about half an hour. Thank you, everyone. And on that note, big thanks to the PCI, IMU, and the VFIO team, to Bjorn, Lorenzo, Mani, Alex, and Jörg. Thank you for help with putting the micro conference together. Nice to meet you.
About the user, do you have any? Why not? I want to.
I see the kernel. But if you wanted to do some complicated HMM thing, for example,
about the history because I also follow the efforts on you. Oh, wow, that's like a base. Yeah, because I saw those last.
I 选不了。
So you have to tell me. Okay, let's. There you go. You can review it.
So.
If you want something changed, you send me a range of updated slide. It can be uploaded before your.
Well, I don't want to interrupt.
Unless everything is okay.
Yeah, I think it. I think I already.
Yeah, just double check. No problem.
Okay. Honey, Canada, trying to get
Really? It's because the sugar thing?
Because
like
it's food.
Huh?
Because it's food.
No. I ship to China, no problem. I ship to a lot of different places. I haven't.
Canada. I don't know.
How often do you come to
Where?
US?
Once,
No.
like,
I'll give you enough.
Yeah. Post.
So it is.
Weird because Canada and US are continentally connected, so
Yes.
it's impossible.
Which is why we're very protectionist, especially now.
I'm tempted to like what's the worst
Yeah, no, that's true.
Am I gonna find or are you gonna find?
Yeah, they'll probably throw in the garbage. If you don't have the right stickers and stuff, they'll be like, you can't do this.
But does it have to fry?
The next one is going to be Hubertus, and then Alex just a second ago. Oh, you wanted to do this one? Oh, no problem.
Yeah, I just want to have
Hi.
There we go.
Hi. So,
You guys will download the website. Right? Yes. Oh, you wanted to update something? No, all good? Okay. No problem. Yeah, if you need anything, updated slide or anything, just let me know, or we can. Right. Thank you for submitting the talk.
Yeah, to be honest, I don't have to that much. One of these is related to
Just restart to get the but the presentation uploaded. Probably.
If you want to log into Indico from here, you can download them and then upload them,
I
or,
think I'll do
from
that.
your own. If you're, cool.
Oh, so speaking of we kind of
We have to add all the.
Are done.
Ah, okay. Thank you so much.
So we have the same problem, but how we are talking about it, because right now we can handle dynamic, we can handle normal probe order and but the thing is, Because we might have aligned it, but like if it was, I think static is a effectively, we have one of the GUIs. Effectively, it's the but it's the never do it. But everybody else can see it as like if we have GUIs and we have to support non-GUI devices, like makes the BIOS saying, hey, I want to reserve this for some rental.
Hi, Wei. Hi. Yeah, thank you for organizing it. Yeah, a lot of everything is up there. So yeah. Christoph with architect. Have you ever done this before? I mean, presenting LPC, no. I did like a KVM forum before. But yeah, it's straightforward. I mean, if you can even test the slides if you want, but you just need to the arrows to which slide. There is nothing.
Hello, everyone. Welcome after a break. I will be passing the presentation to Hubertus, who is going to take over.
All right. Thank you. How does this operate? The arrows. There you go. All right, so we are squeezed into 20 minutes, right? So, and this font is very tiny here. So, you know, we're working on VFIO, and, you know, we always come up with interesting names, right? So we coined VFIO, very frightening IO, and you will see for a moment, in a moment what that is. It's basically about taming wild guests and their PCI config space abuse. This is a common work between a university, which is Boston University, and IBM and Red Hat. The person who implemented has been driving this, has been Chatura, he's a graduate student at Boston, so a shout out to him here. Unfortunately, for many reasons I can't tell you here, is he couldn't come to Japan, but he has been handling the interactions on the community itself. So I want to give a quick outline here. So the background, we want to talk about what PCI pass-through is, you know, particularly what the configuration space is and the mappings to give a little setting of where this problem has been identified. Then we're going to speak about specific problems that we can anticipate because of the pass-through. Then what have we actually observed on various devices? So we're looking at the exploration of these RAS issues, and we have basically built a fuzzing environment and then have done a root cause analysis to get down of why certain devices seem to be breaking. Then we have to propose the mitigation for that. So there's a VFIO patch out that we have already, I think, sent out like 6 months ago, I believe, right? And there were some discussions going on, and then they've died out a little bit, and now we're trying to re-engage with this discussion. And then we'll see how much time we have left here, okay? So in order to first understand where our problem space is coming from, we have to basically talk about what PCIe pass-through is. Why are we doing this? So if you look how devices today or in the past have been assigned, is that, do we have a cursor? Do you see the cursor? Yes. So you have basically a service provider, right? He has a host OS. He has basically various devices, and they have been basically accessible indirectly through guest VMs. So guest VMs either through virtualized interfaces like VirtIO basically request certain services from the device driver and the host, which then basically communicates with the device. As you can imagine, that really by having to go out of the VM, you effectively having a significant reduction in performance and increase in latency. So given that many of the devices have high bandwidth requirements now and low latency requirements, we see that it's actually beneficial to pass the entire device. Think about like a GPU today as an example, right? Pass the entire device to the VM and then abdicate the responsibility of managing this device and interacting with that device to the VM. So now the device driver moves into the VM, and as a result, whatever applications run in the VMs will now, through the pass-through, have direct access to the dedicated device. As a result, we get higher performance, lower latency, and that's what everybody wishes for, of course. Okay, now, where's the problem coming from, right? So let's go into a deeper organizational structure here of the PCI configuration space. So there have been 2 versions, right? And we all know about the PCI legacy, which is 20 years plus back, right? And that's a 256-byte configuration space that is common between PCI and now the PCIe spaces. And then there's the extended config space, which is above 256 to 4K. That's in the PCI devices. So in the extended configuration space, there are effectively many regions, and we draw this here at the bottom, and you can see that each region is basically a certain capabilities, which are well-defined header. It has a certain size, and then we have certain gaps, which are unassigned regions. And ultimately, as you're basically reading and writing to the PCI configuration space, the device is expected to respond according to the PCI specification, which is not always exactly precise, right? And there actually lies often the problem that we observe. Right. So we now basically have to look is like, how is this PCI configuration space mapped or basically elevated up to the guest, right? So there are different ways of thinking about it. So we have here like 5 variations, so to speak, right? So we have a pass-through register. So every byte or every word in the PCI configuration we consider to be a register. So a register can be completely passed through. That means when the guest writes to it, that write via load store will ultimately go straight into the PCI configuration space on the device, right? It immediately affects it. Then the second one is that in VFIO PCI, that register can be completely hidden. So when the guest would write to it, it's not visible to the guest. Okay. Then we have a third one is where the PCI emulates it. I'm writing it, VFIO PCI captures it and then emulates the instruction. And then we can register, have that register emulated by QMU. This is under 4. That means we do an exit into QMU. QMU catches it and basically emulates it. And then finally, this completely unassigned, right? So there's no access to it. So what have we basically as potential problems? So when we have a transaction layer packet here, so we have the guest OS, it basically does a write request, and most of our problems are originating from write request. And the hypervisor basically in the VFIO driver issues the TLP. The host hardware platform basically forwards it to the device implements it, and if the implementation or the reaction to that write is inappropriate, it can effectively create a PCI bus. So imagine you're writing a wrong value into a register, the device is not properly functioning or hasn't anticipated this particular value, it might react, for instance, with an error. So we have seen that this not every error that is being thrown by a device is actually captured in the VFIO device drivers properly, and then basically leads to host crashes, right? Very undesirable. Why is that? Because the contract between a VM and the host or the infrastructure provider should be very clear. A guest should not crash the host. That would be our fundamental contract in the cloud. That is a very fundamental assumption. The second thing that we have recognized is that by writing to some of these registers, often the device goes haywire. So not only does it respond with the wrong value, but it basically shuts down itself and becomes unavailable to other guests if it's shared. So often what we've seen is that for certain devices, you effectively had to reboot the host. Again, now you're basically having an impact on other VMs that are running on the system. So, yes.
I don't get the premise of the host reboot for PCI errors. Like AER, DPC should result in, basically, depends on what user space does, but I believe QMU today will just terminate the VM, right?
But it doesn't. That's the problem. Right?
Doesn't?
It really depends on the platform error handling. So some vendors take it to the extreme that they see this as some kind of data loss event that they can insert themselves to provide higher certain guarantees to the user, those sorts of things. Yeah, ideally, we would like to consider that the host handles this and it's a RAS problem on the host platform, firmware, hardware, whatever.
Right.
It becomes a usability issue.
Exactly. Particularly when the host crashes, right then. So one thing that we have seen, for instance, forwarding the error automatically to the guest and have the VM crash, that would be acceptable to us, right? But the host should not crash, period. Okay. Handled this one. So let's take a look of what we effectively recognize. So how widespread this is. So we have multiple devices, and I'm purposefully not mentioning vendors here, right? Because it's not a vendor issue per se, right? It's pretty widespread. So we have looked at NVMEs, we have looked at GPUs, we have looked at smart NICs, and we have looked at legacy NICs. And probably it's like 10 devices that we looked at or have identified. We have looked at a few more, right? And you can see that often with a single write, we can, into some of the regions or the PCI regions, we can effectively crash the system. Okay, and when you do a root cause analysis, it's usually when you write to the unassigned region of the PCIX configuration space. That was the most common case. In the legacy device, we were actually also able to crash the system by writing illegal values to the power management. Okay, and so when we effectively look at how we would like to deal with this, right, it's like we need to look at the root cause, right, which I already mentioned in the previous thing. It's like by writing to unassigned register or to unassigned PCI register regions. That was the common cause. We have not seen any crashes that resulted out of read operations. Okay, now the way we effectively now let me go back here for a moment, right? The way we went about it is we actually wrote a full fuzzing framework for this, right? And it's an automatic fuzzing framework that basically randomly writes values in the PCI configuration space. It starts out with a single value write with random values going essentially through the integer values and effectively records. Once it has recognizes that the system has hung, it reboots and continues one value afterwards and basically gives you a list of things that went wrong. Okay, and that enabled us to basically look at many, many devices. It's very consistently you can crash these systems. Okay, so what is our mitigation? So we basically propose a patch, and it is basically on the fundamental assumption that if you do not advertise your region, you should not be able to write to it. The reality is that vendors seem to be hiding registers for debugging, for temporary accesses, right? Whatever function they would like to hide there. And that is not in the spirit of the PCI configuration or the PCI specification, right? And so we believe just because somebody steps out of their purpose of what they're being granted to, they should be basically brought back into the swim lane, right? The pain should not be with the folks or with the drivers that essentially play by the rule, right? But the pain should be with the ones that effectively need these special accesses. So what we're effectively proposing is that device vendors should block bad PCI config space writes. Often they don't do it, right? So that's a problem in their firmware. So until many of these things are fixed, we should have at least a temporary solution. That's effectively what we are proposing with this patch, right? So in that patch, we're blocking all the requests or all the write requests to unassigned regions in your PCI configuration space. It's actually a very small patch, right? And so the patch has been proposed already, has been somewhat discussed, as I mentioned early on, right? And so we recognize that different vendors would like to have different ways of configuring this. So by default, you can do today's, via kconfig options. You can go with today's behavior. You can enable it, so then every device will basically only be allowed to write to the regions that they advertised. Right. We have a monitoring version where we say, okay, we allow you to write to it, but we also record that you wrote to a region so that we can later on lock that in the kernel lock. Right. And then we need an escape hatch. So, we recognize that there are devices out there that have this behavior. And as a result, you basically need an escape hatch. Right. That basically says, we have a question.
Sorry.
I'm wondering, are you talking about regular PCI devices or are you talking about SROV devices? Because it's not a problem. As far as I know, it's
a pass-through device, right?
Pass-through, but it doesn't exist for SROV devices which are designed to be pass-through, which are usually given for untrusted guest VMs, which can write whatever we want, right?
Yeah, so if you have like a VF as an example, right, a virtual function, that we have not recognized this error.
Okay.
But
you're talking about
PF functions, yes.
So if you are talking about someone who gave a broken or untrusted PCI device to untrusted VF, and after that has errors, right?
Well,
what I'm trying to explain, I'm not sure what this problem is actually exists in the real world.
Oh, it does, right? I mean, we're passing through GPUs and NVMEs as PFs. Okay.
This is why we have SROV, and this is why
but
we
it's not that common.
we are passing. Also, GPU supports WAFs, so
but
NVMe, NICs, and proper GPU support WAFs and SROV.
So if you go, for instance, go to Cloud Lab and other device, providers of infrastructure, they're providing you the entire device. It's not via VFIO and SIOV, not via VF and via SIOV. They give you the full device. Okay, we have 5 minutes, but we can take it offline.
Yeah, sure.
Right. So, sure.
Just a quick question. And I know you say you trust the VFs. Has anyone ever tested all of that? Are they well scrubbed, and has actually, if you pass VF through, is there a chance VF could take out the host? Not that I don't trust you guys, but I don't trust you guys.
Yeah, I wanted to also object to the untrusted device. These are devices that are in production for many of these neoclouds, right? And they're not untrusted in that way. Again, I don't want to mention the providers here, right? They're very common, GPUs and NVMEs. Okay. So there was a raised hand as well. Yes.
Yeah. Yeah. One question. Can you hear me?
Yeah.
Okay. I think the most problem is this untrusted PCIe you just pass through to the guest, and we don't know where or which regions we should assign as inaccessible. So I mean, mostly we use this device pass through the guest. We just to the simplified the drivers deploy. That means we needed to modify the host driver and direct the product to the guest. And we mostly we didn't touch this driver. We won't modify that. So my question is, so what's the policy of your these two block unsigned write read allow IDs? Do you allow, the device firstly access a region, configuration region, and get into the host, and the host will behalf on the guest to access this region and return the value, and then it would unblock this region. Is that the policy you have mentioned?
No, the policy is to effectively intercept every write operation, right, to the config space, and basically verify that it falls into one of the regions that we have mentioned, right? The device advertises what it believes are the valid regions, and it should stay in those swim lanes, right? If it then decides to write somewhere else, you have...
who take the responsibility to set this region?
Well, the device advertises it in its PCI config space, right? So you iterate through it, and then in the VFIO device driver or the VFIO PCI device driver, you basically verify that you fall into one of those regions.
That means I needed to modify the current implementation and add the specific device region.
This is all contained in the VFI. This is all contained in the VFI PCI driver. Right, the code actually already existed, but was numbed after 2013. Okay. So what we had some discussion. I only have like 1 minute left, right? So this is not a, let me go to the main point here, right? I think the mechanism is very simple, right? You decide that you intercept every write to the PCI config space. This is not a critical path. This is a control path. The data path is still as fast as ever, right? And then the question is, how do we basically do a user interface on the discussion list? There were, for instance, do we put a sysfs out there? Do we put in its kernel boot options to just provide the escape hatch for devices that are not compliant to what we think is the right way of doing it? Okay, and let me see. I think I want to remind every vendor that there's a certain responsibility, right? I mean, when we talk to the vendors who we have identified, they think that it's a responsibility of the software. The initial discussion in the kernel community was like, well, the vendor should play by the rules, right? And so the question is how we break this stalemate, right? And I believe the right way is like putting a temporary patch in there and then see how it works in the community, right?
Right. It's going to be messy, however we do it. We know we're going to break things.
Yes.
So it's going to have to be some sort of opt-in, escape hatch, like you said.
Yes.
See how it does, and maybe.
Well, sometimes you have to push the system a little bit and see what the feedback is, right? And if there are vendors here, please use our fuzzing network before you put your device out and your firmware out, make sure that it doesn't crash. Okay, I think my time is up for the things. Yes.
I know you had that quick line trial on can you do this be IO or MMIO paths? Like I pretty much guarantee for most physical functions, you can trash the host machine by just doing anything dodgy to the MMIO region.
I mean, this is not going to solve every problem, right?
It stops the PCI one, but the other ones are going to be way worse. Like
okay,
may only have to get the device to not respond to something.
Well, yeah, if the device doesn't respond, then you get a host error, and if then the PCI device
back to the RAS.
does a reset, right? Okay.
Thank you, Hubertus. And I would like to invite you to take over the stage next. Oh, and you, Jacob, as well. Oh, okay, together. Okay,
yeah,
off you go.
So, yes. Hello, everyone. I'm Yu Zhang from Microsoft Linux team, and I'm working on the pair virtualized features on guest Linux in Hyper-V. So my topic is Hyper-V-based PVLMMU using JSON's generic LPT. Yeah. So this work is done by me and my colleague Jacob and Iswar, I think, who is also online. And so I would like to give some design choices of our PVLMMU driver and the generic workflow, its current status, and most importantly, some opens. So if you have any question or suggestion, please raise your hand and feel free to chime in. Thank you. So the primary goal is to enable virtual MMU inside the Linux guest on top of Hyper-V, so that this virtual MMU can provide some like three fundamental functionalities, like in-kernel DMA isolation, enabling of user space drivers based on VFL and LMMUFD, and some advanced features like VSVA and virtual PRI. And this driver should fit into the LMMU core system elegantly. But we do have some, more ambitious goals, maybe. So we want to make our MMU driver to be vendor agnostic, or maybe even ARC agnostic as much as possible. And we also would like this driver to maximize its performance by fully utilizing the MMU hardware enhancements. And based on these goals, we have made several design choices. The first one is PV versus emulation. Yeah, we choose the pair virtualization because in Azure Cloud there are many different types of LMMU hardware, like VTD, AMD, and SMMU. So it could be quite a lot of work for our hypervisor engineers to provide the full emulation for each type of LMMU hardware. Oh, thank you. Yeah, so another reason is that we believe with good abstraction, pair virtualized LMMU can at least achieve the three basic functionality. With minimal code change. And another choice is we want to make use of nested translation instead of sending map and unmap requests to the backend. So yeah, there is performance benefits without trapping of map and unmap. And yes, we know that with nested translation, that means a guest need to send the hypercall to hypervisor to perform the LTRB flush and possibly the device TRB flush. But for that hypercall, we argue that this LTRB flush can be lazily and can be done in batch. And also we admit that if the LTRB misses, yes, nested translation requires more page table walking. Yes, so we will maybe perform more evaluations. And another important reason we choose nested is because the consideration of page table memory accounting, which is a requirement from hypervisor. So if we use map and map trapping, that means Hyper-V will have to create separate domains for each guest LVA domain. So meaning a combined translation shall be created for each GLVA into HPA, and the guest can maybe ask for many different GLVA domains using the host memory. So that's something we do not want to see. And also, we use the nested because we believe the ecosystem is ready. So most hardware LMMU has supported the nested translation. And also from an implementation point of view, thanks to Jason, we have the generic page table, so we do not have to cook another page table management code in our PVL driver. And also we start with just supporting one PVL for each guest. Another design choice is about enumeration. So by enumeration, I mean the detection of this virtual LMMU, its presence, its capability, and the device scope it covers. So for now, all the LMMU driver uses SPI table, like DMAR for VTD, LRT for SMMU, and even VLOT for the water LMMU. But we choose to use hypercall-based enumeration because, we just want to avoid the need to the spec change and the need to modify the virtual firmware. As you can see from the right-hand side, there are two hypercall output. The first one is used to check the presence and capability of this PVLMMU. It's only a common LMMU feature set. There's no vendor-specific capabilities. And for the second one, the get logical device property, it's only used when the endpoint device is being probed to check whether this endpoint device is supposed to be managed by the virtual LMMU. So we do not need to provide any data structures like device scope in the DMAR. So I hope this choice is acceptable. This is a general workflow of this PVLMMU. As you can see, we have talked to the two hypercores. Okay.
This looks very similar to what we are doing in PKVM. I don't know if you're aware about the Google Data PVIMMU driver as well, which is basically pretty much we are calling hypercalls and taking up SMMU v3 driver and then doing that for the same thing for the guest. And not sure, it's there already. Again, not in upstream maybe, and that's pretty much what is been designed for the guest. And Qualcomm does it a little bit differently under Ganya. So we were, for SMMU v3, we are exploring more of a VertIO MMU. For the host side, even not doing a complete nested stage translations. But again, we are more inclined towards now more stage 1, stage 2, kind of doing a trapping and emulating because of performance and maybe things are getting improved on SMMV3 hardware side. So, but not sure if it is a duplicate kind of stuff we are doing or if you are aware about it. So there's already work done there. Maybe not common framework like you are trying to achieve, but maybe there is something there. So in ARM case. At least.
Thank you. By the way, so are you using the only ARM specific?
It is SMMV3, so yeah.
Yeah. So you are actually power virtualizing in the SMMU driver.
Yeah, for the case we are pretty much using those.
So any reason you did not use VertIO MMU?
Yeah, so that's where I think Google's, I don't know the original reasons, but they started with the kind of not using VertIO MMU because we just want to have a hypercalls into the hypervisor itself rather than coming back to the host and then doing all of that. So.
And those hypercalls are into KVM?
PKVM, basically.
PKVM, okay. Yeah. Okay, thank you.
I can send you the link.
Thank you.
I think
yeah.
Yeah, we're also looking into x86 PKVM, and we are looking into PVIO MMU on that platform as well. So I think we need to talk.
Thank you. Thank you. Yeah. So by the way, so for PKVM in x86, are you trying to power virtualize in the VTD driver?
So we trying to do what ARM does for PKVM, but because
but x86 is different.
It is.
The root, non-root.
So we essentially virtualizing the host OS and using, I guess, virtualization to achieve the isolation.
Mm-hmm. So, are you also trying to use nested translation? I think so.
I'll have to connect you with
thank you
with my lead to
sure
to give the details.
Sure, thank you.
The latest version that Mustafa posted for PKVM for ARM has given up on the, I don't know, the sort of para-virtualized like you're doing, and the PKVM is just providing a para-virtualized SMU v3 hardware model directly, and it's using the normal SMU v3 IOMU driver. I strongly encourage them to do that, and in fact, I strongly encourage everyone to do that because all of the hardware people that have implemented nesting have thought it through enough that it's designed to be para-virtualized directly, and you'll get a better result because so much of the hardware detail leaks out that by the time you get like a VertIO IOMMU or something that can deal with nesting, you've basically just duplicated your driver 3 times because all the invalidation logic has to be exactly the same, and it's all incompatibly different. All the passive logic is incompatibly different. Things like the GCRE versus the CD table are incompatibly different, and they all leak out to the guest.
But Jason, your suggestion is only for ARM SMMU?
No, all of the platforms.
And the reason is, I mean, ARM has very specific LTLB flash requirement, like you mentioned, but for x86?
x86 has a different flush command than AMD does, and a different flush command than ARM does, and a different ATS command than either of the two of them, and so forth and so on. And it leaks out. You have to, especially if you want the AMD and ARM have options for guest-controlled command queues. So if you want to expose that performance feature as well, then you're duplicating the entire command queue logic now from all the native drivers, and it's just there's no reason. You don't get it.
That's something we want to discuss maybe.
Yeah.
Yeah.
I would like it if you explained why Microsoft thinks that they want to have a common virtual IOMU driver instead of using the existing hardware drivers. Like I think that's a really key thing to articulate.
Oh, so That's a question about whether to use PV or emulation, right?
It's all sure.
Yeah. So because we are using Hyper-V.
Unless the hardware has some trouble and they do not have like direct command queue kind of support in the case of ARM, where okay, hardware is lagging and you will see some sort of performance issues or something because of trap and emulate everything.
Well, currently the only vendor that has actually published direct command queue is AMD.
There is ARM word difference, but
NVIDIA's proprietary for ARM is published,
yes.
and
it went into the specs.
Yeah, and then ARM is doing something that we can't talk about, right? Yeah. So.
Online question, 1 second.
Go ahead.
Answer this.
Okay, is that a call for the report? Yeah, Jason, I was wondering if your recommendation for the everybody to use the in-kernel drivers is specific to KVM, or does it like regardless of hypervisor?
Yeah, I think it's just a general recommendation. Yeah, if you want to do nesting, you want to use nesting hardware, and with IOMMU, then the guest driver I feel is best to be the native driver.
Well, I think other than the hardware acceleration, the command QV, we have yet to see. I mean, like the emulation logic has a lot of overhead, right? I mean, compared to PV, and also when you optimize the driver, you're not going to consider how many VM exits are going to cost, right? So the optimization of the bare metal driver may cause counterproductive effect on the on the emulation. So by doing PV, everything is abstracted out, and that can be more.
Almost.
Yeah, something, but
very little.
Yeah, I guess we haven't yet to see invalidation being such a critical factor, especially for IOVA. So mostly lazy, batched invalidation, other than S. Yes, that's maybe it has a slide.
Please share the mic between these.
So next page. We can just move on first. Okay, this is a general workflow of this PVRMMU, and those are the hypercores we have introduced. As you can see, there's no trap for the map and the unmap, and yeah, we are using LTRB flash hypercore, and for now we are using domain selective LTRB flashing, but we do have new hypercores to be introduced to do this page selectively. And the status, yeah, I have sent out the patch of GLV support earlier this week. Sorry, I think I forgot to CC to some of you. So Jason, Alex, anyone. So I'm sorry, but please forgive me and please help us review. Yeah, and for the GLV support, yeah, we have finished the POC, and I think there's another question.
Can you hear me?
Yeah.
Okay. My question is, what's the comparison between the VOTIO IOMMU and your PV IOMMU? I mean, what's the advantage?
So
yeah.
So currently, whatever IOMMU, their upstream code is actually based on the map and the map request to the backend. That means for each map and the map, it will have to trap to the host. And I think Jean-Philippe is trying to propose a page table based whatever IOMMU, and I'm not sure if Jean is online.
Actually, internally, we have expanded the VOTIO IOMMU driver in our system, in the RISC-V system, and we have added the user log domain, we have added the nested log. We have added the add user domain. So actually, it needn't pass through to the backend. It can directly mapping the support nested translation in the guest.
Yes, it
So
can.
I think
Yeah.
this is not a reason. So do you have the, other advantages
Well,
beyond to the file?
Actually, we also have some prototype based on WhatLMMU using also JSON's generic LPT to construct nested translation. And we have not sent out the patch because WhatLMMU spec is not finalized in the committee. So I guess, yeah, if it's finalized, I think it's also okay. But by the way, Hyper-V does not have a WhatL. So that's why we are introducing a Hyper-V hypercar based one instead of extending the WhatLMMU.
I might have to ask you.
Yeah, I think I'm almost I'll be quick. Thank you. So opens. So one of the open is that we want this driver to be vendor agnostic. So yeah, we have JSON's generic RPT, so we don't have to provide ARC-specific pivot table management in the PV driver. But we are wondering if there's any requirement or any plan to offer a generic passive table. No.
Use the real drivers, right?
Yeah.
This list encapsulates why I'm telling you to use the real driver.
So yeah, well, we do not want to use that driver. But yeah. So what about we offer one? Yeah. Okay. So and also about the hardware acceleration. So for the virtual command queues submission. Yeah. Okay. And also, yeah, about the adoption, maybe any requirement from the WhatLMMU side. So if yes, maybe we can collaborate. So that's it. Thank you.
Yeah.
Okay. Thank you so much.
Any more question?
Yeah, one question is, do you think introduce?
Sorry, Google, please. We don't have.
Yeah, we can discuss offline.
You can take it offline, please. Thank you very much.
Thank you.
Thank you.
Thank you.
Thank you, Jacob. We need to quickly move on and pass them to Wei. Presentations.
Okay, thank you for coming, and I will get started. My name is Wei Huang. I work for AMD Linux team. Today, I'm going to talk about a new device we are developing and the current status of this new device. So, as part of the presentation, I'm going to give a quick kind of overview about what SDXI can do, what's the features, and what's the benefit of this new device. And after that, it will be more like a kernel implementation status. We have been starting to submit our patch set to the upstream, and we want to get some feedback from the community. And also, there are different phases of the implementation, and we want to get some feedback about the direction for our next phase. So about SDXI, this is a new device, kind of specification developed under SNIA, and is a collaboration between different industry companies, including like Dell, VMware, and AMD and others, especially also some other startup and storage companies. And what it offers about this one, the main thing is about the memory operation. It can do the cross address memory operation without with a minimum CPU interaction. So the idea is we want to have some extensible specification that support this type of the memory operations you guys can come up with. And for the use case itself, SDXI could be used in different system, could be something like like a mem zeroing or mem copy across different devices, or it could do the like a network memory copying and so on. So the SDXI design itself is by itself is a PCIe endpoint device. So it come up with the support SR-IOV, and each function can do a lot of the operation by itself. So I'm going to show a little bit more details quickly. And the capability and the configuration is basically accessed in the memory. So here, just show you one diagram, and is basically the bottom of the diagram kind of is the architect of the SDXI. So the SDXI function, it basically, most of them, actually all the functions relies on the MMIO register and the in-memory data structure. So we designed this back with the idea that trying to be able to support the save and restore. So only MMIO and in-memory are used to do the device management. And there are two levels of the not page table, two levels of data structures to support a lot of contexts, like up to over 65,000 contexts. And I will show you quickly. The context itself is the execution unit. And I also want to point out the key here, another two key component. One is the R key. So this is a kind of receiving key table. And that basically is like a security checking for the incoming traffic. So to monitor the system traffic and guardrail the security. And the last one is error log. Is a lot of error log being implemented here to be able to handle, for example, context failure and also function failure and so on. So like maybe address space not being handled properly and ATS failure and so on. So all the details are in the specification. You can take a look at it. I also want to point out the bottom here, there's a address space. I highlighted in the green box. So this is a key concept for the SDXI, and they basically use the passive for a lot of the memory access. I will show some other examples later on. So about the context itself, I mentioned that this is the key execution unit. So the context basically handle all the descriptors submitted from the user. So basically, you can see that in that green box, and it basically there's a context control data structure point to sub data structures like a descriptor ring, which handles like is a circular buffer for the descriptor submission. There are like other data structures like write index value, similar to a lot of the device endpoint PCIe endpoint device design, right? And the last one is the context status. So you can see that the kind of right portion is highlighted in gray area. So this is on data address space. You can see that you can control this address space using a different passage in the SDXI data structures. So about the address space, so the key here is be able to access like different address space. By default, most of PCIe device you only access the its own address space by default. The same case applies to XDXI, but XDXI also in its descriptor when you submit it, you can actually specify kind of extended the target buffer or the source buffer with extension. We call it A key entry. And this pair, A key entry plus the address, kind of give you the be able to specify where you want to read a memory from or write a memory to. And the A key entry itself contains the target function that you want to access to, and also it contains the entry of the packet ID of that function. So this A key entry basically has two pairs, kind of indicate where that address is living in. So with that, as I say, the R key will validate the incoming traffic. So the R key entry has that capability to check if that incoming traffic for a specific function is allowed or not. About the descriptor itself, the design is 64-byte descriptors, and for now they are being developed with different categories. As you can see, there were some DMA copy descriptors. That's the most important one, maybe. And there are some other atomic operations. And for the administration group, by the way, I forgot to mention, the context 0 is for the administration purpose, so that all the functions has a context 0 reserved for the administration operations. So the administration can do like a function update, context update, and so on. And they also, the SDXI also provide the interrupt support. So this is a separate descriptor group. The most important thing I would say is it actually allows a vendor extension. So there's a special group your vendor can develop maybe for memdiff or encryption or whatever CRC you want to do. You can extend it over there. So they all put it in the same 64-byte descriptor format, and you are able to discover the vendor support through some mechanism. I'm not showing here, but yeah, it's all in the specification. So here is like a quick example. In this example, I showcase a mem copy from a user process inside a VM to another user process inside another VM. So there are two virtual functions. One, both of them, each of them being passed through to the VM1 and VM2. And when we submitted the descriptor in the VM1, it can basically saying that, hey, I want to copy memory from myself to another VM. And in that case, the A key entry itself contains the information about we call it the target function, right? And that target function is contained in the VM1's A key entry, and also there's a packet associated with that process in the VM2. So that information combined together, you can do memcopy without the hypervisor interaction. There's some prior setup and so on, but yeah, this should be is just a very simple example, show you how the whole thing works. So the SDXI software design, we have been working on the this software system for SDXI. Obviously, very similar to a lot of existing software design. You do device pass-through, and then on the host side, you have the physical function SDXI driver running on the both PF and VF, the same driver. So when you look at this diagram, I want you to kind of put it in the mapping relationship is basically the SDXI function is mapped to the virtual machine. And the context itself is more like to every process in that virtual machine. So this is a very a high level mapping relationship, and you can use that. Question?
So actually, maybe the previous slide. So the packet you use to communicate, is that what's the namespace? Is a system-wide global packet?
Is system-wide global parset. Yeah, actually no. Sorry, the parset itself is that as we call it as from the target functions parset. So there are different ways you can allocate a parset. Even right now in Linux, I think right now SPA in Linux use a global parset for the implementation, but it doesn't matter because as long as when the traffic coming in, you go through IOMMU and then you get, for example, AMD IOMMU, you use the parset, whatever the parset for the you go through a device table entry and then find the GCR3 and use parset to find the GCR3. So it shouldn't matter.
If I understand correctly, the AMD parset table can be GPA or HPA. So you're using, I guess, HPA this table or host SPA.
Is in the GPA.
I use GPA.
Yeah.
So how do you make sure there's no conflict? I mean, how do you make sure that the parset used for VM1 are not, it's not used, I mean, it's not conflicting with, or you're separating?
Yeah, they're separate VM.
Okay.
Yeah. Okay, so I don't know, any other question here? All right, so I will continue. And the implementation, we kind of intentionally split this design into two different phases. After talking with upstream, there was some feedback from the upstream about how we approach this problem, especially this is a part of the intention for this presentation. So the first part of the implementation we submitted is as a DMA engine. So this is obviously the first use case for SDXI device, right? So we hook up with the DMA engine layer of the Linux system and provide SDXI device as the DMA engine. So it does a basic mem copy and also the give us the opportunity to kind of introduce the SDXI data structures, including all the MMIO and all those like control data structure and so on. And the it has a, I would say it's relatively a straightforward implementation. There's some limitation. Right now, the DMA engine, we only support the pool mode, but we haven't get the IRQ completion in place. So you can only do a DMA test with a pool mode. But we have been working on the IRQ completion inside, and the next release should include that. And the locking mechanism and so on, those are also fairly simple. So right now, the RFC of this patch set has been, I would say, 2 months-ish. And we got some feedback from the community, Bjorn and Jonathan from Huawei. And so get some feedback from that. So on the next one, we actually got this one working in-house, but we also want to get some feedback from the community. It's about the user space support. So we want to be able to assign that SDXI owned by the user space. So what we are proposing is SDXI iOcto, and there are two categories of the APIs. One is to the device level, and that's allow the iOcto to control the device with like a administrator level of the privilege. And the second one is the allow the user space to control that SDXI device, so I access that.
My first kernel patches were DMA engine offload. It's been 20 years.
Correct.
Of DMA engine always losing to CPU over time.
Correct.
Or other device offload. Why? Why are we doing SDXI?
Correct. Yeah. So
I mean, I'm kind of okay with like in kernel use cases, but like when we get to start doing new user ABIs for things that we're not sure are going to be there 5 years from now.
Yeah.
I'm like, if we can hide 100% of this in the kernel and we offload some very heavy memory copy things that are rare to hard to find, like I couldn't find them for 20 years. then maybe, but user ABI scares me.
Yeah. So to answer your question, I think nowadays the CPU design, I agree that most of mem copy is high performance. Pretty much you couldn't beat the like CPU mem copy performance. However, if the CPU cycle is precious for you, you still consider like offloading that to a third-party device. And then secondly, there are certain operations that CPU is not good at, like the encryption, and there are certain operations that CPU is not good. So this type of thing, SDXI may be able to jump into the help.
So the UAPI, from the first description, I was expecting that there would be an mmap-based interface where you do like a 64-byte MMIO to start the descriptors. Is that also part, or is that future thing? Because if you always go through IOCTL, then there's obviously this.
Yeah, there's a mmap, mmap, but actually the I kind of not share here, show it here. The user space will be able to own this the gray area that as a context, so they don't need to do mmap. Actually, they will own that address using passive by itself.
So the mmap, I mean, would be that you can do the MMIO on the to trigger an operation instead of having to go through an IOCTL.
Yeah, you can do that. There's a doorbell ring that need to happen to allow the software to inform hardware that the software submitted a descriptor. So yeah, we can take it offline. I'll try to wrap up. So we have cover some points here, and we're going to go forward with the DMA engine part, and that will send another revision before the end of the year. And also for the user space support, I would appreciate all the feedbacks, offline discussion. For the tool support, I've been kind of on and off working on the QEMU emulation for SDXI emulated device. So hopefully can get it done. If that gets some interest from your community, we can share that as well. So the last ask is about a use case. We tested the mem copy, mem zeroing, and some of the folio page copying, and also in TB with SDXI device. And if there are other use cases, we would love to hear from the community.
Thank you for that. And so this is basically it, right? Yeah. Okay.
All right. It's me again. You will have to stick with me for another 15 minutes. All right. This one is actually a little bit different. This one already in the kernel, but it's kind of interesting. Okay, so it's about the TPH support in the PCIe. It got accepted. I think a lot of people think, well, it's part of the standard, and that's one of the main reasons. But we want to show you some good performance number in this presentation, and ask for maybe you as a device driver developer or some endpoint device vendor may consider use that. And it's not vendor specific, so it's kind of vendor neutral. So it will be interesting to see. And so the first thing is about the this new technology is PCIe TPH actually, and we call it AMD SDCI. So we leverage this SDCI using the TPH to allow the smart data cache injection. And I'm going to cover a little bit about the kernel integration and show you some performance benefit as well. So about the purpose of this design, right? So cache injection is not new. There are other vendors already did it, but they use the last level cache data injection. And with the chiplet design and more complex SoC layout, we need more flexibility for the be able to handle the complex cache design. And also we want to allow the device driver to cherry pick what kind of traffic they want to do the injection, not kind of dictated by the vendors' injection policy, and we also want to make it to be flexible. So this come with the this SDCI. So the AMD SDCI is stands for the Smart Data Cache Injection, and what it does basically very simple is when the traffic DMA write traffic coming in, we will try to put the data to the L2 cache that's closer to the consumer of that data. So all the inbound DMA traffic will be injected to L2 cache based certain policy. And what you need is basically we need a TPH support for the obviously the endpoint device, and that's a standard, right? So it's relatively easy. And endpoint driver and endpoint firmware, so a lot of them need to kind of decide, hey, I have this capability. I want to, should I use that and be able to get my traffic into the L2. So the bottom here is a TOP header, right? If the TOP, TH bit is 1, then the traffic going through the IO die and the AMD SoC will be considered for the cache placement. There are a complete kind of complex cache policy placement, a cache placement policy for SDCI, but you can kind of get an idea from this diagram. I'm not going to elaborate the details. There's a lot of probing. They have to find all the check all the cache line and location and so on. So the software component here is very simple. So the first one is the BIOS need to provide DSM. This is a ACPI DSM developed between AMD and ARM. I believe, yeah, it was ARM. What it does is providing a mechanism for the OS or the driver to query that, hey, I have a CPU ID. I want to inject the cache. Could you tell me what's the steering tag value? So that steering tag value is vendor specific. And the second layer, Linux obviously need to do all the TPH configuration and so on. And then device driver itself decided what they need to inject, what kind of traffic they need to inject. So very simple. So the API itself is fairly straightforward. They are the PCI subsystem, the core API. You do the enable TPH and disable TPH depending on driver's need. And there are two main functions that is to get CPU ST value. So that one allows the driver to query that DSM to retrieve the ST value. And the second function is to set the ST entry. So this function will automatically check the location of the steering tag table, which could be located either in the MSIX entry or could be in the TPS extended capability space. And then after that, that's all, everything we need. So from that perspective, we get this support in Linux kernel and 6.13 already. So if you guys are interested, you can take a look at it. There are different modes supported, like a no ST mode and PCI TPH, the vendor specific mode and so on. So it's all in the details. So I'm going to skip this one quickly. So about the performance. So as I say, when we submit this patch set, we didn't disclose any performance, and this one actually is a collaboration between AMD and Broadcom. We use our Broadcom P2100 100 gig NIC and set up with our iPerf, and is based on the AMD Turin Zen 5 processor and so on. So we have two different setup. One is a 1Q on the right hand side, and then the other one is a 4Q iPerf setup. So this is, and the performance number, as you can see, actually is pretty significant. Now, I need to point out that we didn't show you the iPerf performance improvement. The reason is with current CPU and everything, it's easy to get a line rate 100, 200 gig or 400 gig. So there is no way I can show you that the performance improvement, like in terms of the network traffic bandwidth, but I show you here that we can save the memory bandwidth by using the SDCI. So the for the 1Q case, you can see that a lot of mem traffic actually is coming both read write. We can improve significantly for the total memory bandwidth in the 1Q setup. We can improve by like 70% reduce, and for the 4Q case is over 50%. So that kind of show you the memory bandwidth benefit by doing SDCI on. And another performance study is about, hey, we show the memory bandwidth saving, but where the bandwidth saving from? So using AMD performance counter internally, we kind of trying to see where that data come from. And the same thing here, the diagram shows a 1Q and 4Q setup. As you can see that majority of the data now come from cache. It could be a local L2 or could be across CCX. But you can see that the memory traffic actually is reduced significantly for both 1Q and 4Q cases. Okay. So this kind of prove that we by using SDCI cache L2 cache placement, so we can get the data closer to where the consumer is. Okay, so the another one is about the latency. So this one we use the AMD Xilinx solid flare NIC card. This is a fintech kind of focused network card, and in this case, we do the SDCI on and off. And as you can see that for all the different payload sizes for both like traffic TCP UDP, we will be able to consistently improve the network latency using this network card by turning on the SDCI. So this kind of showcase the latency benefit. Okay, so yeah. About this talk, I think the main thing is about the collaboration. So the current status for SDCI support, as I say, 6.13, we have that patch included in a tree. And Broadcom BNXT driver support for SDCI is included in the 6.15. And recently, another AMD engineer get the like QoS support into a 6.18. So pretty much we have all the pieces in place. If you're interested, you can take a look at it. And I'm working on the virtualization support for TPH. Basically, when you do device pass-through for TPH capable device, I want to be able to do update the steering tag in the steering tag table entry. For the community collaboration, I think the first thing is for other vendors, as I said, this is not AMD specific. The DSM is the ACPI DSM is open standard, so you can plug in whatever value you feel is right. So you can enable that and maybe be able to leverage the same SDCI TPH support in Linux. And then secondly, the device driver can consider that for the a lot of I/O write intensive workload driver. You can use SDCI to reduce, maybe improve performance or reduce memory bandwidth or latency. So those will be the good benefit. We are also exploring other techniques like a different use case, maybe different I/O traffic type. Right now, it's kind of limited. We work with Broadcom and to identify what kind of traffic may be useful. Yeah.
Guo, I mean, we should give him a chance for once to ask a question.
Sure.
No, I saw it now. Guo, you still there?
Yeah. Okay. Can you hear me? Okay. My question is, we have the steering tag to put the CPU ID in it. That means that every queue, every descriptive ring bind to the one core. And my question is, if a core binding a ring, pulling this ring, and this ring is in the L2 cache, actually in our the mesh network, the Snoop filter knows the cache line it is. So if the core pulling the ring in the L2 cache, and actually the NIC send out the stash transaction to the network, and the Snoop filter the home node could the Snoop filter of home node could transfer stashed cache line into the L2. So it seems it's not need explicit the CPU IT setting for the queue. Does it make sense?
Yeah, but how did you instruct the CPU to do the placement? You say you got the CPU CPU core ID.
Yeah. I didn't. I didn't put CPU ID. I mean the calling the core zero pulling the queue in the L2 cache, and the cache in the L2 cache. So Snoop filter knows the cache line where the cache line it is. So when the NIC send out a stashing transaction to the network, and the Snoop and the home node would transfer the cache line into L2 cache. That would stash to it. So since we needn't explicit the ST tag setting, maybe the ST tag could set up the level ST tag is flexible. You can define it, set the level. It's called stashing. You want to stash into the L3, you want to stash in L2, but since we didn't to determine to give the hint to which CPU ID it is, because Snoop filter could help you to route the cache line to the right core.
Yeah, I think.
Guys, I think you need to take it. I mean, he asked the question. I mean, I'm happy for you to take it offline because we need to give Manny a chance.
Okay. Yeah, we can take it offline. Yeah. So I think the key here is flexibility. You guys have to use a static pinning for that. That's my understanding. We can take it offline. Sorry.
Thank you.
All right. Thanks.
Thank you.
Thank you, Wei, for the talks, and handing off to Manny.
Hello, everyone. Thanks for being here. So I'm Manivanan Sadasivam. I work for Qualcomm. So before going into the talk, I would like to give a quick fact. So when I submitted the abstract for this session, I was contributing to this power control framework. And since I was co-maintaining the controller drivers, I was trying to use it, and then I faced a lot of issues. So, and then a lot of community people also shared some issues with it. So I thought about just presenting this session and then ranting about the power control framework and the issues it's caused. But apparently what happened was a couple of weeks before, the power control maintainer, Bartosz, added me as a co-maintainer. So now all of his issues are mine. So I cannot just complain loudly anymore. So so I indeed decided to present something to fix the issues. All right, so so this is the agenda. So I'll give a quick introduction to what power control framework is, what is the current design of it, and then what issues it is right now fixing and what it didn't fix. And then finally, I'm going to present the proposal I made a couple of weeks before that is hoping to fix all the issues that are happening so far. So the PCI power control framework was introduced in 6.11 in a hope to handle power management for the PCI devices. And it's mostly required for the device tree platforms and not required for the ACPI platforms. I know that the ACPI folks might be laughing at me and then saying, get a life. But that's how the life for the device tree developers, actually. So on the device tree world, there is no entity that is going to handle the power management for the PCI devices in a proper way. So there are a couple of ways that we can do it right now. So first one is by using the bootloader. So before the kernel boots, the bootloader can turn on supplies for the PCI device and then just hand over it to the operating system, and then Linux can just enumerate the device. But the problem is the OS can't do runtime power management because it doesn't know how to control the supplies. And then unlike in ACPI, where we have the ACPI methods to talk to the firmware, we don't have such interfaces for the devices in the device tree firmware. And then there is one more way, which is by using the host controller drivers. So the host controller drivers can actually use the device tree nodes to fetch the power supply information for the PCI devices or slots, and then try to control it. Some of the drivers, they do it right now, but the problem is they can only do it for certain slots, like the SEM slots or mini SEM, which have a couple of supplies like 3.3 volt or 1.8, and then a couple of enabled GPIOs. But when it comes to complex power supplies, because the PCI base spec is very flexible in allowing the vendors to have their own power supply requirements for their devices. It doesn't even define the connector interface in the base specification. It allows the supplementary specifications like SEM, mini SEM, M.2 to define the connector interface. But what the vendors have decided, at least in the embedded and mobile use case, is that it's often better to come up with their own standard or custom connectors, or just solder the device into the PCB itself and forget about the connector. So that's what's happening for at least a couple of Qualcomm WLAN BT devices. So when the power control driver was merged in 6.11, it added support for a couple of Qualcomm WLAN BT devices with the help of one more framework called PowerSync. So the PowerSync driver is the one that is actually handling the sequences of handling the power, because these devices, they require some complex power supply sequences, because they have like 8 supplies and then a couple of GPIOs, and they need to be toggled in or enabled in a specific sequence. Otherwise, the device will not just work. So the PowerSync driver or the framework will handle those supply requirements, and then the power control will handle the PCI part, because this is like a shared device, right? WLAN BT combo. So Bluetooth is also going to make use of this device. So PowerSync is kind of an aggregator, and PCI power control is the one controlling the PCI part. So this stuff was merged, and then it at least solved the problem of handling these complex power supply requirements that we have been trying to solve for at least 6 to 7 years. Then I added support for power control slot driver, which was supposed to handle the power supply for the SEM and mini SEM slots, and that was added. So this is the current design of the power control. So it's not visible clearly. I apologize for that. So the way it works right now is that when the PCI bus scan starts, the PCI core is going to check whether the device has the device tree node or not. If the device tree node is available, it's going to check whether the platform device is available for that node or not, because we don't create the platform device for the device tree nodes of PCI devices actually. But some of the PowerPC guys do, so that we skip the device tree nodes that already have the platform devices, and then we check whether the device requires any power control or not. This is decided based on the presence of supply properties. So if the device tree node of the PCI device have any supply properties, then we consider that, okay, this device requires some power control, so we just go and create the power control device for it. So we create the power control device for it, and the driver core will automatically try to bind the power control driver to it. And the way we bind the device and driver is by using the compatible of PCI IDs. And if the driver is bound, it will try to probe. And then in the probe, the power control driver will just power on the PCI device. And then the PCI bus scan will just continue to other device and so on. So by this time, the device will be turned on, and then it will be enumerated at this point of time. So, but there are issues. Even though it looks simple, there are a lot of issues. The first one is there is no burst integration. So the burst is the fundamental reset or out of the band signal defined by the PCI spec. And this signal is supposed to come from the PCI host to the devices to signal the stability of the power supplies and reference clock. So when the burst is asserted, which means that the power is going to be removed. And if it's deasserted, the power is stable, power and ref clock, so the device can just start working. Unfortunately, right now, the power control framework doesn't control burst. And what really happens is that the host controller drivers, they just initialize their own resources and then deassert the burst way before starting the bus scan. So before the power control driver gets a chance to power on the device, the burst will be deasserted. And that is completely against the spec like SEM and mini-SEM, which defines that the burst should be deasserted only after the power and ref clock becomes stable, and that too after 100 milliseconds. So that is completely violated right now. And then the next one is there is no, this power control framework will just work fine for simple endpoints, but then when you try to connect a PCI bus extender like switch, it will not work, because in the previous slide I mentioned if the driver is not available by the time the power control device gets created, the bus scan will just continue. And which means that your device is not going to get powered on. And if you have connected the PCI switch, and if that requires the complex power supply dependency, then the switch will not get turned on, and then the PCI core will just assume that if the root port is not hot plug capable, it will just allocate resource for one bus, which means that the core cannot know, he doesn't know whether there are going to be more buses showing up after the boot or not. So it just tries to allocate resource for one bus, and then if you try to connect a PCI switch afterwards, then it will result in enumeration failure, because there will be no bridge window, there will be no bus numbers allocated for more than one bus. So this is as an actual issue. People try to connect PCI switches and then they realize that, okay, it's not working. And then third one is the controller drivers have no control over the power control drivers, because the power control drivers are just created by the PCI core autonomously. And so for some some host controller drivers, like the one used in MediaTek or Samsung, they want the devices to be powered on before initializing the PHY. So if once they call PHY power on, and if the device was not initialized, then they result in they see a PHY power on failure. Actually, I think that PHY driver is trying to do LTSSM state or not, I don't know, but they reported that it doesn't work. So this is one of the community problem. And then final one is there is no D3 call support, which means that when you do a system suspend, you can't just power down the device and then do PME, turn off, broadcast and everything. It will not just work. So these are the major issues that the power control framework right now has. And I tried to address all these issues in my recent patch set, which introduces a couple of APIs. Actually, these APIs are supposed to be called by the host controller drivers. Right now, I have made sure that the host controller drivers have control over the power control drivers. So in one of the API I introduced is the create device API. So in this API, when it gets called, it will try to create the power control device firstly before powering it on. So only the struct device of power control will get created, and then that has no dependency, and then it will just create it if there is a device tree node and based on the existing checks. Then I have one more API which does the actual power on, and this API is supposed to be called whenever the host controller driver has initialized all the resources like ref clock and all, and then it should call this API. What this API does is it just goes through all the device tree nodes and then tries to see if the power control device is there or not. If there is a device, it just calls the power on callback, and the power on callback will just enable power to the device. But there is one catch here. If the power control driver is not probed at this point of time, this guy is going to return eProbe defer. So the reason why we require probe deferral is that if we do not turn on, or if we do not power on the device before starting the bus scan, we already saw that we are seeing the resource allocation issue from the PCI core. And most of the devices, root ports I'm dealing with are non-hot plug capable. So if the devices show up after initial bus scan, I'm going to see this resource allocation issue anyway. So I've just assumed that all the root ports are non-hot plug capable. We can add support for hot plug cable root ports later, but at this time, this guy just returns eProbe defer if the power control driver is not available. So once this API returns success, which means that all the devices that are defined in the device tree, whether slots or just regular PCI devices, they will get powered on. And then the host controller driver can finally deassert the bust as per the specification requirement. And then it can start the bus scan, and then everything will just work. And then this is the final API, which is just the opposite of what the power on devices API does. So it is supposed to be called during the scenarios like system suspend. So first, in the system suspend, you will do PME turn off, just broadcast the PME turn off message, and then just assert the burst, indicating the devices that the power is going to be removed, and then just call this API. So this API will just do the reverse of what the previous API does, and then it will power off all the devices. And finally, you can turn off all the controller-specific resources, whatever block required. And in the system resume, you can just call the previous API and then just deassert the burst. And that's going to work like an ACPI. All right, that's it. I hope with these APIs, most of the issues I have talked about are getting fixed. At least I have verified it on Qualcomm platforms, and one guy verified it on some Google Pixel phone and, MediaTek Chromebook. And I hope other vendors could also make use of this power control framework. Right now, many of the host controller drivers are just doing the plumbing power control on their own. I hope I can actually convince them to just switch to this framework since it got stable. Any questions? Okay. Thank you.
Thank you, Mani. Thank you, everyone, for coming. It was a great Mica conference. I suppose people will be now heading to get something to eat. And just after the lunch break, here we will have our sister conference, Mica conference, the Device Tree Mica conference, which is going to be very exciting as well. So everyone is welcome. Thank you again, and have a great time.
From Windows, it's exiting. What's the other? Yes. I made a Spanish
Other than all of the
discussions.
There's no way to what's our
Yeah, I was. I was. No, language. Yeah.
Ciao.
Tam jest inny komputer, dobra.
Okay, Doug, you already raised a hand. We are not in the questions yet.
Oh, I was just telling you to unmute.
All right. So thanks for our sponsors. So this session can happen. We are a Device Tree Micro Conference. Like that. And the schedule is following. There will be a few talks starting with me. And at 4:30, there will be a coffee break. Afterwards, we have still 4 talks. And then the beer should start. So I already gave such talk on the Open Source Summit, so I will not be going through all the slides. I'll be going very, very, very fast. If you are interested in listening to me again, there will be recording after some time. So just in case I'm working for Qualcomm, I'm maintainer, just a disclaimer that what I'm going to show here is based on the actual data, but I will be using from time to time some adjectives like active, incomplete. This represents only my point of view, not my employer. So first of all, so we are talking about the result of the DBS check. So we want the DTS to be compliant with the binding. So I looked back to up to 6.13 and 6.7, trying to reproduce what the results were there and what we have now. So kind of like a 1-year change for the results. So which architectures we have? In the kernel, we have around 13 DTS files, but I will not test everything. Several platforms are legacy. So of course, I've shown here results for the ARM, ARM64. So the ARM, whenever I use here ARM, it will mean the ARM v7, v6, v4, so TI Inspire calculator. I also show some results for the RISC-V, Lungar, and PowerPC. I didn't include MIPS because the time of I was preparing everything, you couldn't build all the device resources for them, such a pity, but I think this is being fixed by Rob recently, or exactly soon now. So how many targets do we have? And by target, I mean the DTB file. So usually this corresponds to a specific board or a DTS to an overlay. So this chart shows that ARM64 has a significant growth, but ARM is still alive. The remaining 3 platforms, like if I zoom there, well, PowerPC is obviously shrinking because it's a legacy, and RISC-V is there still alive, kicking. So how many total warnings we have? There are tremendous numbers, especially for ARM, but this includes the duplicates. So when the warning is in the DTSI file, this also means that it will appear for every board, every target. So this metric is not really that good, and you even don't probably see what's at the bottom, right? I also don't see there. That's 4. I usually show rather the metric of divide by number of warnings by number of targets. And the red line, the big red line for ARM drops significantly. We see that PowerPC is not changing. So the things which improve is a bit of ARM and significant improvements for ARM64. The bottom is almost 0, and that's the RISC-V, obviously. So these are the actual results. How many warnings per target? Obviously, Lungar is an interesting case because they have only 3 targets, should be easy to fix, but they are not fixing. And after my Open Source Summit speech, a few hours later, they sent someone, I don't remember the name, sent patches. So my wall of shame has effect. And RISC-V actually is warning free. These minor bumps could be result of my measurement, my metrics, so it should be considered 0. So an interesting thought that the size of your code base does not mean that you will be warning free or it's particularly difficult, because ARM and ARM64 are both huge, but have significant different amount of warnings in total, right? So yeah, so obvious. More interesting things will be if we look at the actual SoC platform, especially in the ARM64 world. So I will not go through the PowerPC because there's no vendor split. RISC-V is pretty boring because they did the job, so they are done. I can show, on the other hand, how the actual vendors are growing in the numbers. So these are the upstream supported platforms per vendor. Vendor understood as a DTS directory, but not much here else to show. So ARM 32-bit has significant change. So first of all, we have around 40 directories there. I will not show everything. So this is why I will be speaking only about the most active ones, the ones which still receive updates or are the biggest. So all the following slides focus there. And the leading platform, the number of targets, is NXP, obviously, because they have multiple of boards and vendors making the actual eval kits for them. And they're still growing, actually. Yeah. Another platform which is still growing is ASPID. This chart is not really that good. So what is interesting is on the number of warnings per target. And we see here the outlier with the TI has a lot of things to do. So that one with huge one is the TI. We have few platforms which reaching the zero warning stage. So I would like to give kudos to platforms in ARM which receive the significant progress. So Logic is actually warning free. Actions is kind of almost there. Qualcomm did decent progress, and not also that. Pay attention that this chart also includes 619. So the data points are no more linear. In the history is not exactly linear. I have also other metric to show when I kind of count the number of targets which are warning free to see whether, let's say, we at least have some DTBs which are totally good. And this shows this percentage. 100% would be that everything is warning free, and there's only, I think, on this chart there's only Logic, but we have more platforms which are fully warning free. So these are the only ARM platforms, ARM 32-bit, which are there, and Allwinner and Logic are kind of bigger there. A few others are kind of not that active, so maybe that's easy. No, these are the only ones, and the A is a pure coincidence, right? And kudos here for Allwinner because they have a lot of targets, 160. So the question was for remote audience, did I start with A and whether the slides are going? No, there is nothing afterwards. I have, on the other hand, the wall of shame. So these are the platforms where there is no single warning, no single platform DTB file without a warning. And what's here visible, there are a few quite busy ones. The slides are pretty small, but maybe you see. So TI has a lot of targets and ASPID still. So what does it mean? Obviously, we don't work that much on ARM, and some platforms are legacy, but what's worth noting that ASPID is an active platform. So ASPID still receives new boards, but they just don't work on the fixing warnings. And this also changed. So my shaming brought the result, and ASPID now sent a huge passage fixing quite a lot. So good job. I will make the same talk next year, and we'll see what will be the progress. So probably effort moved here, obviously, right? So for ARM64, we also have 40 directories. Some of the vendors are split, like Tesla, Exynos are actually the same, and I use here old naming. So Freescale is NXP, obviously. If you know kernel, then you know the history. Also worth pointing attention that some of the platforms are actually ACPI. So DTS might not be developed, but the platform is still alive. This is purely based on the data for DTS, and it's subjective view what is active, what is not active. And I will also not show every platform here because there are just too many. So, there's a question. Please grab a mic.
Hey, so if the platform is an ACPI, is the device tree coming somehow from the ACPI tables, or is the device tree going to be part of the kernel as well? How does that work?
I think there's no device tree. It's ACPI. I mean, please speak to the mic so that remote.
You're saying in an ACPI system, you have a device tree or not? Before ACPI, you can have a device tree too to generate ACPI tables on the fly as one of the configurations. So that's what we are learning on some servers. Use device tree before it gets into the ACPI. So you can use dynamics tables package to generate ACPI tables. And no, that's all proprietary.
So the device tree is not in upstream. Let's go fast through the slides. These are because I want to actually talk about the problem, so how to fix it. But what to fix, I want to show the numbers. So who's active there? There's also note that the slides are. Another question?
No, just comment to previous one. There is also the device tree fragments in ACPI, the PRP 001, HID,
and they are part of the firmware. Well, they're part of the firmware, so they come with the platform. They're part of the ACPI firmware.
So such devices would not be here ever measured because there are no GTS files in the kernel sources building to DTB. There's also, yeah. Okay, so note that the chart is not linear in the history, but what's worth noting that there are 3 vendors kind of dominating the growth. So there is a Qualcomm, XP, and Rockchip growing constantly over the time. And obviously, this will also mean that they have the biggest amount of warnings, probably. So these are the total warnings in absolute numbers. They started with quite huge numbers, especially in XP, Qualcomm, and MediaTek. And this bottom there is not that really visible. So there are still total number of warnings for the platforms having the highest absolute numbers. So these are the kind of outliers in ARM64, which still have quite a lot of warnings, around 200, for example, for Qualcomm, right? But this is why this also includes duplicates. Rob Herring uses different metric. He deduplicates the warning. I would like to rather show a bit different one. So I will move this chart on one side and show next other chart, which would be the number of warnings divided by number of targets. They are the same colors there, right? So from both graphs, we see that some platforms don't change, his silicon. I think Rob Herring even now suggested to me that I could remove his silicon because maybe no one is using it. Unfortunately, NVIDIA Broadcom is also not working on the warnings recently, but quite good results in improving this ratio for the Qualcomm and MediaTek here. So because they have quite a lot of warnings and now they are quite close to 0, right? Obviously, to show some kudos further, so these are now charts showing the number of warnings divided by number of targets, and we got there significant moves for MediaTek, Freescale, and Xilinx. So these are the platforms which are actually fixing stuff. I also like to show the reverse graph, so how many targets are warning free, and this I do with probably because even in ARM64, we have legacy boards and we don't maybe care about the older stuff, but we do care about the new stuff. So first of all, what's visible here that Freescale got to 100%, and for the such huge ecosystems, it's a great result, but it's not the only one making progress. Also, Qualcomm and Rockchip are almost there. They reached 70% of the targets without warnings, and this is great because you could actually try to remove from your checks, from your CI, some warnings and just check only the new boards somehow. I don't know. That's the discussion further. We have few platforms I would like to give kudos. So obviously, Allwinner, Amlogic, and Apple, they are 100% compliant. They have now warnings, they are warnings free. Amlogic was pretty early. I think Neil did it for 6.12. So kudos to Neil. And Broadcom, Marvell are stagnating in that. I think they just don't care. Samsung was my success from the previous times, and in general is also warning free. And kudos to TI for ARM64. TI for the ARM v7 is rather the outlier, but for the this platform is working good. AMD Xilinx cannot decide. They have really bumpy ride there. So these are the kudos, all of them, not only the most active. This also includes the new platforms, which are not considered that much active. And for example, the 6, BST, Blaze, Axiado, these are introduced this release, previous release, so they are like a refresh, so it's very easy for them, right? So kudos to TI, Freescale, which are, for example, very busy some system, Amlogic as well, right? And of course, I have the wall of shame. And next year, I hope that this will change. We'll see. So some minor commentary, not that important, because I want to actually ask the question, so how to get the kudos for more of the platforms, right? So what do you need to make this list grow? Or what are your problems stopping you from this list from growing? Konrad.
So I think there are people, including myself, who would really like this to happen, but there is the question of hardware availability. It's often the blocker because I may have sufficient information to the best of my knowledge about what the hardware looks like, but before committing that to bindings or changing the device tree, I would like to test that on the actual machine, whether or what I can find is reflected in reality. So whether I need to, I don't know, add a new clock source or maybe shift some things a bit, that requires verification because you can't always trust the docs.
So you need more hardware, but don't Qualcomm has big community?
Yes, because if there's a platform that was submitted in 2017 or so by some person that no longer contributes, and they were the only active submitter, we don't want to remove support for that platform only because no one is actively poking at it, because it presumably still works, but we can't really fix it without being sure that our fix is.
Okay, I cannot help in that way. I mean, you work in Qualcomm, so I guess you would get the hardware. And
Yeah, sure. You were just asking the question what the blockers could be, so I'm throwing out.
So, I think all these warnings might have some level of categories, right? Some things might be very silly to fix. Some things might really end up in changing the drivers and a bit more intrusive. So do you have any information on those kind of things?
I think that all easy picks were already picked, but DT schema is also changing, so there are things. So the point is that someone has to keep checking and fixing the easier stuff. So Rob also sometimes complains that there are warnings which appear on multiple boards. So with the fixing one warning, like you can get, I don't know, 50 targets fixed, right? So there are such cases. Someone just has to put the effort there. Wolfram?
So I think for ARM64, we have everything we need. We just need to do it. For ARM32, a lot of easy things are also picked, and where then there's a problem that we have one warning saying we have a text file which should be converted into a YAML file, but that means not only converting this one driver, but like implementing the whole power domain for the CPU, different CPU cores, and not only writing the YAML file, but also update all the device tree source files for the SoC of a legacy platform. And this,
yeah, that's a lot of work. So maybe you just
this is.
Do you still have customers with this board, with this SoC?
I'm part of the upstream team. I don't know that.
We still have 3 minutes for this session. One of the proposals I think I heard from Bjorn was that DT maintainers take because one of the problems is that new warnings can appear because the device tree bindings come with the subsystem and DTS comes with the SoC. So subsystem, I mean the driver subsystem. And this is the problems also I have because I take the DTS and I need to compare the Linux next. So the warnings, the presence of warning at Linux Next is decisive, but I will see the warnings in Linux Next the next day only, right? No, not now. So the idea was that the DT maintainers prepare a branch with the binding, which will be going for 2 trees. But yeah, I think this will not happen, and we try to avoid taking patches. Rob usually don't take the patches.
Yeah, one thing. Answer is, of course, is I have to look at the actual warnings that you will still be seeing in v6.19 RC1. The easy ones are usually easy to fix, but in my experience, the most complicated ones are for some multimedia bridge device somewhere, which is rather old, may have been converted to YAML quite recently, and there's still some discussion about some of the properties, and it's not clear to whether they all really exist or not, or should be there, things like that.
So again, kind of effort, right?
Yeah.
So you need time, you need money.
Well, it's if it's one of those multimedia bridges, it's something I'm not really experienced in myself.
From experience, can tell that about the hardware and breaking. For example, I did it for Samsung. I didn't care. So if I break something, they will come and tell me, right? I cannot have all the hardware, and for me, more important was to fix the warnings. So I would just suggest fix the warnings, and if you break, yeah, that's the upstream life, right? We still have like a last question, or we are. Oh, Bjorn.
Yeah, so the question of how do we get the bindings and the DTS in. So the model I fell back to now is that I build the process schema from Linux Next, and then every time I merge a DTS, it has to, I validate it against that. The tools I have there are by me for me. You wouldn't want them yet, so maybe I can share those at some point. But one thing we do see problems with is when we have lone DT bindings patches and they sit on the list for a long time, either blocking DTS patches being merged or the binding fix just sits there. I think we have a better success rate on getting bindings merged together with drivers. I don't know if we would like to make some change there on how we pick up those lone bindings, or if we could have some clarity in that in certain subsystem we have an agreement with the maintainer that you guys, device tree maintainers, pick that, or that I pick it together with it.
I think the consensus is that you pick up. I mean, so you are the platform maintainer, and you can always grab abandoned binding, and no one will be offended by this.
Okay.
So that's grab.
I never pick the binding because I expect there.
So you have a permission to go. Okay, thank you very much. Let's move to the next talk, especially that it's a remote one. So let me just pick up the slides. I guess it's you, Saravana, right?
Yep. Thank you. Can you guys hear me well?
Yeah, I can make you a presenter, then you will be changing slides yourself. Does it work for
Yes,
you? Can you
please.
change the slides?
Not yet. I'm not presenter yet.
I made Doug. Sorry. Wrong.
Yeah,
Now.
it looks good now. Yeah.
So go ahead.
Cool. Thank you. Thanks everyone for being here. Yet another talk about firmware dev link, but I think that has a lot of issues that we want to try to solve and make things better. So here's another one. So just to kind of give a really quick intro or short intro. Firmware dev link, for those who don't know, it stands for FW dev link stands for firmware dev link. It parses DT, potentially other firmware in the future, and it creates a dependency graph between the device tree nodes and eventually between the device nodes itself that get created. The goal is to enforce all kinds of ordering, probe ordering, suspend resume ordering. It has a lot of, it'll help you figure out which modules to load in what order. There's a lot of benefits to it. I have given multiple talks on that. You can go look at them. But the way it figures out the dependency today for device tree, for example, is it looks at a property. Let me see if we can get a marker going. So it looks at a property, and then within the property, if it sees a p handle, then it says, okay, this particular device depends on whatever p handle you're pointing to. And then the same thing happens for so every property has a p handle in a different location potentially, right? So power domain, it's a first entry, and then depending on power domain cells, you can have 0 or more values here. For IOMME map, you have an integer first, and the number of integers before it can be different, and then the p handle, and then a few more integers. So the way firmware dev link handled this today is we have one function, fairly small function still, but it's one function per property that it understands. And the list of properties are in drivers of property. That's where all of those functions are present. And yeah, it's a part of drivers of property because firmware dev link is meant to work when every driver is a module, and it shouldn't depend on the drivers for correctness, right? So that's kind of the intro. So what's the problem? By the way, I have only like 3 slides, so it's a pretty small set of slides. What's the problem is that the list of functions doesn't really scale, right? We need to keep adding more and more properties as new bindings get created, new common bindings get created. Or if, it took me a while to get to the current list of properties,
So I don't know how many of them are missing, right? And then there's also too many bespoke properties. So like every vendor, every specific IP block, they might have their own properties saying, I don't know, something, something, something equal to, and then they point to some other p handle. And if you try to include all of them, you're going to get into hundreds and thousands of properties that you parse. So every time firmware dev-link works, it takes a node, looks at every single property, and says, "Hey, does this match with any of the properties I know?" Right now, it's fairly fast enough because only 40 properties. But when you start adding more and more, if it becomes hundreds and hundreds, it's going to start slowing down. So we have parsing overhead too. So this doesn't seem to scale well. So how do we fix it? I don't have that great of a solution, but a couple of random thoughts. One of them, within quotes, the simplest one would be you could change the DT compiler to generate underscore references underscore property that'll just list all the p handles that all the other properties of that particular node refer to. Right? It's a really hacky one, clearly. And then firmware dev-link can just parse this references property to just get the list of p handles and be done with it. So you don't have to understand every property. The other option, this was like a prototype that Rob suggested just to hack it up to see if it would work, which is if you add the plugin directive that's used for DT overlays. One of the things the plugin directive does is it creates an underscore local fixups node for that. So if you add it to the base DTS file, not the DTSI file, if you add it to the base board file, then it's going to create the local fixups for every node in the base file. So this local fixups basically for every property. So if you have say clocks property, let's say clocks, and it lists the list of p handles in the clocks property. At what offset you can go look it up. Long story short, it effectively creates a copy of the device tree nodes, but only with the list of properties that point to other p handles. So if you do that, then firmware dev-link can just go look at the local fixups, root node and every other node under it, and that'll kind of give me all the references and dependencies. So that's another idea. A third idea that I didn't have time to put in the slides that Rob was talking to me about was trying to change libfdt, flattened device tree, to. Oh, I'm getting a lot of feedback, I think, or some kind of sound. Is to change libfdt to add the type information to the DTB files. So for every property, the DT compiler will then encode, okay, this property has an integer, p handle, integer, or string, whatever, right? It'll just kind of describe the types of the values inside a property. So those are the three options that I currently have in mind. I'm not necessarily sure which is better. Just want to hear the community's thoughts or any other better ideas than any of these. But the main goal is I don't want firmware dev-link to have to explicitly know how to parse each property. Any thoughts or questions?
Are there any drawbacks with using the plugin way, like any issues?
I think the biggest one is Rob worries about is the size. So it's going to add for every single property, you're effectively making another copy of it. I mean, in real DTB file, the size doesn't increase for every property. If the property name is the same, it just kind of points to the same string. So it's not like you're repeating the string multiple times. But maybe the device, you still capture the tree structure inside the local fixups node. So maybe that causes some extra data usage. I haven't quantified how much that it's going to be, but that's the main thing.
With any of these, we're adding a second copy of the p handle to the device tree. So if there's any runtime patching of the device tree, how do you keep those in sync?
So for which one? For the second one I list here, it's actually not creating a copy of the p handle. It just tells tells us where the p handle is located within a property. So the main point of the plugin directive and the local fixups is to help with the DT overlays. So this part doesn't, like, this one is not affected by, this option is not affected by having to fix up the same p handle multiple locations. This one would be, but I don't see this to be any different than, say, any other property, right? So you can have like multiple properties and multiple device tree nodes pointing to the same clock provider. So it's like not any different.
Right, but
Does
I'm
that
talking
answer your
about like
question?
when, say, if a bootloader changed a p handle to reference a different p handle, right? Then the bootloader would have to know to also update this references property, or else
True.
firmware definitely
Correct.
might have the wrong dependency.
Correct. That's a good point. That's a very good point about that particular option. So in that sense, the second option is slightly better because you're pointing to where the p handles are, not actually making a copy of it. Yeah. Any other thoughts, anybody, or any other ideas?
Did you try, I mean, did you parse all the p handles and did the firmware links were still properly working? Because now you said you're parsing only specific properties, right? But if you parse every
That's
p
a
handle,
good question. I didn't implement that. We will. I'm sure we'll find some issues there, but there are already some ways of saying, "Hey, don't worry about this dependency." Right? We have post-init providers. If that is needed, there's a way to kind of break those dependencies that it might create. So, by the way, one of the other benefits of if you get this working, in one of my other talks, somebody asked, "Hey, can you enable asynchronous probing by default for everybody?" The reason we can't do that today is because there's so many bespoke properties that we don't parse. So the dependencies are as strictly enforced, so you cannot enable asynchronous probing by default. But if this works and it's not going to break, something, then we can definitely enable asynchronous probing by default. That'd be like a huge win for the kernel.
Does that imply then that the dev links are not an optimization, but actually a data structure which will ensure that we always probe things in the proper order?
Sorry,
So
can you
if
repeat the question? I missed the first part.
So if we move to, we enable async probing and I disable dev links, should I assume that my kernel boots? Can I
If you
assume
disable
that my
dev
kernel,
links, probably will not boot.
but that means that dev links is not an optimization. It is a fundamental data structure keeping track of the dependencies. And I think right now it's an optimization. We still rely on eprobe defer, and then we optimize that with dev links.
Wait, I understand what you're saying. Okay, if I understand the question correctly, you're saying if we enable asynchronous probing by default, and you're saying firmware dev link changes from optimization to a functional requirement. Is that what you're trying to say?
Yes.
Okay. Yeah, that's true. But if it works, is that a problem? I guess.
No, but because it has an importance in how correct does the dev links need to be. So today, where we have some of the dev links, it becomes an optimization.
Correct.
It seems like you're pushing towards a point where we rely on the dev links to make a functional system.
I mean, you can always. I mean, if you want asynchronous probing, if you don't have to. But yeah, that'll all. Yeah, if you can basically track the dependencies correctly, you can do a lot of things more efficiently, and less chance of indeterminism.
It's optimization. When you say it like that, it's an optimization. So we need to decide whether it's an optimization or we have to be 100% correct.
I think we already passed this point because the dev links are used for the unbinding of the consumer-producer relationship, right? For the proper memory. One of the talks of Bartosz was exactly pointing that you need dev links for the proper unbinding of the consumers.
Actually, you mean the talk from earlier, where I was mentioning the fact that actually we have some instances where devlinks are simply not created because you have, for instance, an auxiliary
But they should be
device.
created.
Yeah, oh yeah.
So they're already.
But they are not. So
Yes. So the point is
something that doesn't work.
they're already a functional requirement for proper operation. So they're not our only optimization now. Yes. The question was that we have to fix this, and answer is yes.
For your question, Bjorn, I think if we turn off the firmware devlink, we should also disable the asynchronous probing. Otherwise, we'll run into this issue, right? So.
Correct. It's almost like a dependency, not correct. But can we maybe? I mean, I'm glad there's some discussion, but if you can share towards suggestions on how to make the dependency more complete, that will be nice. Any other ideas or poking holes at existing ideas?
Yeah, but my concern is that it's not a question of making them more complete. If we say they have to be there because we depend on them, then they can't be more complete. They have to be fully complete. And we have to really squash all these holes.
Sure. I'm not fully seeing the point. I'm saying. I mean, like I can say whatever I want, but doesn't mean it's going to happen, right? Like we need to figure out how to make it happen, and we'll have to kind of, at least based on my experience, you have to kind of code it piece by piece, right? You may try to do complete. You'll realize in some cases you're putting a dependency where it doesn't exist and it's breaking something, and we might have to figure out a way to fix that particular board by taking that weirdness into account. So that's kind of how it's been going so far. So I'll assume that's how it'll continue going.
And that makes total sense, except that we can say that and say that we can trust them.
I didn't say we can't trust them though.
You're saying that we can trust them, but they're not all there.
Whatever is there is trustable though. Okay, I feel maybe we can take this offline this particular point. I don't necessarily disagree with anything you're saying, but I'm kind of struggling to figure out how to move forward on that.
Any more ideas here?
If you're going to change, the third option, like I said before, is trying to change the DT compiler to include the type information. Honestly, thinking more about it, I don't know how much space savings is going to be compared to the second option. Also, is the second option palatable to people, or people are going to be like, oh, that's terrible, don't do it? We literally have to go just add the plugin directive to every DTS file effectively.
And I'm assuming even with this, you can't get rid of any of the existing firmware devlink property parsing because you have to support device trees that don't have these additional information, right?
Yeah, but I can always make sure, like if this, I can basically for nodes that have this, I can short circuit it. Meaning, let's say you have this plugin, then I won't have to do those things. Yeah.
Except
But that's
that we
okay.
at the same time, that if the information isn't complete, then you're not guaranteed that the kernel will boot.
No. If the plugin stuff is there, every single P handle will be acquired.
Yes, but for these cases where you're loading an old DTB that doesn't have these things, then we're saying that devlink information will be incomplete. And at that time, we can also say that we trust the devlinks.
Yeah, so basically the point you're saying is we can never enable asynchronous probing by default. That's basically what it boils down to.
Right, because you can't know that this information is like, how do you know unless you see that every single node in the device tree has one of these local fix-ups corresponding to it? How do you know that there isn't some, the bootloader added a property that contains a P handle?
Which kind of is the way that also Rob mentioned some time ago that maybe we need DTS format version 2. And then you would enforce it, right? So all the new DTS version 2, you already have this or another few things which Rob mentioned that we miss.
And then things like async probing would have to depend on that. And whatever other mechanism we build upon that promise.
Or just accept the fact that it will never be the only way, and you will always have to use probe defer as the last resort and just live with it. So you have asynchronous probing to a degree until it fails, and then you just fall back.
That's true. Yeah, technically, right? You can just if you do all your error checking correctly and you do eProbe deferral correctly, firmware dev-link should not be a functional requirement. But lots of drivers don't.
I think I agree that a DTS or DTB whichever it is, the DTB format bump is probably the only way to ensure that the information is complete. If we enforce the p handle type information, whatever it looks like, if we enforce that as part of the DTE version, that's probably the only way to ensure that the final consumer is actually getting complete information.
True.
And then we have to implement the probe function so that we can actually do async probing without this information. I mean, the only reason why it doesn't work is because it's hard to get right and we haven't tried it.
You're talking about how to get all the dependency right?
No, the order of acquiring your resources and whatever in your probe function and making sure that we can probe things in asynchronous and in parallel and so on.
Yeah. I mean, at least a lot of Android devices, they do fully asynchronous probing. Or at least asynchronous module loading, which is effectively asynchronous probing. It's at least in Android devices is common enough, I suppose. And by the way, at least for Android, firmware dev-link is a functional requirement because lots of drivers don't do sufficient error checking, and without firmware dev-link, it's just a disaster. It doesn't even boot.
Yeah, but your dev-link is still not complete, so you're using.
I guess it's complete. It's complete enough to prevent it from crashing at boot.
It's dev-link and luck.
Yeah. Dev-luck, yeah.
We agree that in DevLink you trust, and any more questions? Oh, there's
one last comment, maybe.
Does your proposals here? I assume it does because you list in one of your early examples. You listed one of these I think it was IOMMU mapping, right? Will this second proposal work for the? I mean, you can have several layers of indirection with these mappings, right? Yeah,
it'll still work because because it's still going. The several levels will happen at the node level. You go to another node, and that node will have another reference.
Okay.
You're talking about IMMU map, right? Yeah, it should work there.
Yeah, but there's several types of maps, right? So I mean, you need to kind of follow them to their end, I guess.
Yeah.
And DTC is going to. So DTC is going to do this and then create your new nodes. Is that the proposal?
No. Right. See, everything's already working for these properties are listed, right? All I'm doing is I know explicitly how to parse IMMU map. But the point is, I don't want to figure out every property. I'm saying, hey, just DTC, just tell me all the p handles you see. Right? Because right now, the way DTC works when it compiles into DTB is all these just become numbers. Every p handle has a unique number, and it just replaces a p handle with a number. So when you go look at the binary, you can't tell where the integer is ending and where a p handle is starting.
Yeah, I just mean I got that. So all of the maps are going to be fully followed, and those are going to end up in your plugins node as well. The multiple level. Okay, good.
Correct. You'll have multiple nodes listed inside local fix-ups, and they'll all be kind of. But within those nodes, they'll just point to where the p handles are. It doesn't tell you more information on what the connection is. But I can go back to the original property, figure out, and just read that particular offset.
Okay, good. That's what I want to know.
Okay, folks, we need to wrap it up.
Thank you.
So thank you, Savannah. And we jump immediately to the next session from Bartosz. And this should be this one, I hope. Pytanie, tak.
Hi. I've already asked, yeah. Okay, so when I submitted talk, I wanted to actually discuss what I was about to do, but then several months passed, and most of what I'm going to present is either upstream or queued for 619. So this is about situations where device tree says one thing and driver code says another. So sometimes you see, well, so, okay, let's look at this bit of device tree. So one thing that stands out is that the speakers in this snippet use the same GPIO for their reset, and they have they are effectively separate devices. But the code, the C code says that if you have requested a GPIO, you cannot request it for the second time. So far what we're doing is just nothing, and we allow drivers to request the same GPIO more than once with a special flag that is called GPIO D flag, flags bit and non-exclusive, and interested driver can simply get the descriptor and fight it out. So there is no synchronization, there's nothing, they just use it, and it's up to the driver to figure out whether they need synchronization or they don't, and there's nothing behind the scenes that makes it consistent. And also, the problem with this is that the driver needs to know that it is requesting a shared GPIO, which it has no business knowing that. So someone added a fix me in the code, and I figured out that maybe we should tackle that problem. So before I got to it, Krzysztof got to it and handled exactly that case with something called reset GPIO. So this is something that when it sees a GPIO that is also that is called reset, and the interested driver is not requesting a GPIO but a reset control, it will do some magic behind the scenes because the reset subsystem already counts references, or rather the enable count. It provides some synchronization. So and the reset GPIO use case is very simple because you either it's an output pin, and you either assert it or deassert it. And also, some people are not aware of it, but device tree is not the ultimate description of the logical of how the logical tree of devices in the kernel is represented. So you can actually create devices which don't have a corresponding device tree node. This is what the auxiliary bus is for, among other things. So what Krzysztof came up with was simply when a driver wants a reset and the relevant firmware node does not really have a reset controller p-handle but a reset GPIOs p-handle, let's just create a dynamic auxiliary device that will become the provider of the reset control to the consumers, while on the other hand it requests a single the GPIO once, and it's still an exclusive resource. So instead of doing this, where the same GPIO is being consumed by two devices from the same GPIO controller, which is a hack, you do this, where both speaker devices consume a reset control from the reset GPIO driver, and this in turn consumes the GPIO for just one time. Yeah, so this is upstream. It's still being reworked. I'm still reworking a couple of things, but this works, and it's used on Qualcomm platforms. But there is an issue when the device tree says this, for instance, where it's not a reset GPIOs, but a more generic function. So whether it's power down or chip select or whatever else, some device trees have shared GPIOs which do something else. So with GPIOs, there is a problem because they are a bit more complex than regulators, for instance, the resources that can be easily shared, because they have direction. So a GPIO can be input or output. You have different configuration options, and well, they can be used as interrupts, and you have to take that into account when sharing them. So let's consider this. You have the same situation, and how about having some abstract proxy in between the consumers and the GPIO control that is not just a reset, but a more advanced intermediate. So I came up with this idea where at init, when we're booting, let's just scan the device tree, look for all GPIO handles, and determine which ones are shared. Then, when the GPIO controller for which we detected shared GPIOs is probed, let's create those proxy devices, dynamic auxiliary proxy devices in between. And let's make the users behind the scenes, they don't really know it, but the drivers, instead of requesting shared GPIOs with the hacky flag, they request a regular GPIO, and behind the scenes, the core will just say, okay, this driver needs a shared GPIO. So let's take this one GPIO, share it behind the scenes in the proxy driver, and expose regular GPIOs to actual consumers. So to that end, there is this new auxiliary device called GPIO shared proxy, and its logic is basically count the times that consumers want to enable GPIOs, and the first user to get them will get to set direction. The subsequent user cannot change the direction because that would make no sense. And then the function changes a bit depending on the mode. So in input, it's really easy. You can just read it, and the proxy driver provides synchronization. In output mode, it's a bit different. So we consider a enabled GPIO to be, or rather, the GPIO that we consider to be enabled, we drive high. And users, if we have multiple, will vote for enabling a GPIO. So whenever the first user does a GPIO the set value to 1, GPIO will be driven high as long as at least one user votes to drive it high, and then it will be driven low when all of the users that currently requested vote to drive it low. For configuration options, there are 2 types. So there are the shared options, and there is no good solution for that. But the per user options like active low, which is logical, or GPIO name, these can be freely changed. And this has been queued for 6.19. There were some bugs, but most of them have been fixed, and Linus just pulled my pull request with the fixes, so it looks like it works. We'll see about it during the cycle. And there is one remaining thing in the interaction between GPIO and pin control in device tree. So let's look at this. You have a GPIO that is being assigned to a user, and the same pin is being. Sorry, is there a question from? No.
I think I'm having audio issues. I'll get to it later. Thank you.
I can't really hear it. Can you come again? Oh, audio issues. Okay, no problem. And the same pin is being maxed to some function. Well, in this case, it's a GPIO function, but the pin control subsystem doesn't really know it. And it turns out that if we use something so the preference in pin control is to set pin controllers to being strict. And by strict, it means that if you max the pin to a certain function, you don't allow in this case, you don't allow the GPIO core to request it as a GPIO. The problem arises when the function of the pin actually is GPIO, but because for Linux it's just a string, it doesn't know it, so it doesn't allow GPIO core to request it as a GPIO. And this has caused many pin controllers to not be marked as strict in the kernel, which they should. And to that end, I added a thing in pin control where, well, this is what I explained, but basically, yeah, so the idea was to add a flag to pin functions where a function is said to be, this is a function that works as a GPIO. There may be multiple functions that work as general input-output pins, but we basically say, okay, this function can be used as GPIO, and this allows us to both max a pin and use it as a GPIO and set pin controllers to strict. And this also is now upstream in 6.18, and that's what I've been up to. And so yeah, questions. There's a question.
So my question is why the shared GPIOs should be modeled as GPIOs, because GPIO naturally is an exclusive resource and the driver expects to be able to control it exactly as it wants without additional voting on it, that it really is not aware that it might happen. If I'm driving my reset line low, I want it to be low because I want to reset my device. I really don't want to, get into a situation when the device is not reset.
Yeah, so we have GPIOs used by regulators or resets and whatnot, but turns out that I've counted around 30 different functions that don't fit any of the abstraction layers that we have in the kernel, and they are being used. There are device trees out there that do assign the same GPIO to multiple devices, and the function just doesn't fit anything that we have. And this is why so far there was this non-exclusive flag that just allowed drivers to, just request it and do whatever. And,
so why cannot we introduce another abstraction for the shared GPIOs so that the drivers that want exclusive ones, they not get surprised in a design when there is something different happens?
But they already do. Like if a driver requests a shared reset, it says, okay, deassert the pin, but it doesn't get deasserted because there's another user of it.
We'll have to fix it.
So if you have your multiple devices, depending on a GPIO, for example, for a reset line, there is no way other than writing one driver or one device instance to cover both of those two. So this is something the hardware guys have to take in consideration. If you actually need to time it or to have some sort of a sequence where reset happens in the middle there, then you need two resets, or you need to have a combined driver state. So
also, I would love to for you to hear Hirt's use case that he presented. Like he responded to one of my patches on the mailing list, and there is a very good use case that absolutely has no chance of being addressed with any of the abstraction layers.
You want me to talk?
Yeah, please do.
Yeah, so on some of the Renesas boards, the development boards, so they try to provide all functionality. There are a few GPIOs, and each of these GPIOs is connected to both a switch button and an LED. That means if you put it in output mode, you can enable the LED or disable it. If you put it in input mode, then the LED goes on thanks to a pull-up resistor, and if you press the button, it will be pulled low. So that basically means that as long as you turn on the LED, you could read key presses if you put it in input. If you disable the LED by putting it in output mode and putting it low, the LED goes out, but you cannot use the key anymore.
It just goes to show that hardware designers don't really care about all our nice abstraction layers and software.
So basically, it means you can use it as a controllable LED if you don't care about the switch, or you can use it as a switch and don't care about the LED. Then it will be on all the time unless you press the button.
But in this case, you're not loading both the modules though, right? You're probably only loading one of the drivers, so it's not really an issue.
Yeah, it's GPIO keys and GPIO LEDs, so these drivers, yeah, if indeed if you don't drive in your kernel, then the other use case works.
Yeah. Also, you can't obviously. My comment was wrong, completely wrong. So ignore. Yeah.
Another nightmare use case. I've had a board with two different camera sensors, but connected to the same input port for the camera data and the SoC. And then they both connected to the same GPIO line for the reset signal, but with an inverter on one of them.
So wait.
The solution is not going to work, Marcos.
No, go on, sir.
Could you go kindly to the last slide of the GPIO reset block?
No. This one?
GPIO reset.
Oh, yeah.
So the device is created ad hoc when a first device will have the time I wanted to use it. This included that the kernel config has to explicitly enable the reset GPIO driver, otherwise the core would not do it. And we had like a pretty big argument on the mailing list, and I still don't understand why. If I need to enable this driver to have that core functionality, I cannot rely on the core functionality. Why is this not in the core? So I have this always as a core functionality.
Goes to Philip, I mean, the reset maintainer. This is his call, whether he wants it as a driver or part of the core. I don't mind to be core.
Oh, I thought you did mind. Got you wrong then.
No, I only minded that you broke platforms, but making it not default enabled, or so the existing platforms would lose the functionality. That was the only problem, right? But if you keep all the existing platforms working, that can be core, it can be module, just there cannot be regression. That's the only.
And what do you mean by?
Sorry, I want to comment, but I'll let you finish your response to him.
Can you come again? I'm not hearing the loudspeaker very well from here.
Okay.
What was the question?
Yeah, I'll try to repeat it this time. Hopefully, you can hear me better. I'm having audio issues. But one of the things you mentioned in the shared GPIO, I believe, is you parse the entire device tree to figure out how many references you might have.
Yes.
Maybe instead of that, can you please try to just follow and look at all the consumers instead, so that you don't have to parse the entire tree? Because firmware devlink will already kind of give you all the multiple devices that might reference your device. So that might help you reduce the amount of parsing.
That was my initial idea, to go through devlinks, but then Greg is like, nope, you don't get to access the devlink structures in struct device from anything but the driver core NPM. Or am I not misunderstanding?
I don't think I was in that mail, or if I did, I didn't get to look at it. But I've always wanted to give something like for each consumer kind of function. So I think that would be a reason.
I would love to have such an interface. Yes.
I think we should definitely have it. I think there'll be multiple uses for it.
You actually have something, it's called device is dependent, but again, this is not exported, and Greg is against anything but the PM and driver core using it.
Okay, I don't remember the device as a dependent one. I think it's one that's checking for cycles. That is too much, but we can definitely create for each consumer and for each supplier. If you want to do that, it should be fairly straightforward to do on CC me. I'm more than happy to review it by it, but I can get to it when I can too.
Okay, yeah, that would be useful.
Cool. In your logic, you had a scheme that looked quite suitable for a reset type shared usage. And you mentioned that you had a few other different use cases for the sharing. Did they map well to that same logic, or is it a bit of a sort of shoehorn situation?
So even if they do, I don't think it. So most maintainers will frown upon just shoehorning logic that just happens to fit a given subsystem into that subsystem. So it used to be that we try to share GPIOs via fixed regulators, but yeah, that's not really the right thing to do. So, and Mark would complain probably. So.
Are there any users for this exclusive GPIO? New patches which is sent. Are there real users right now in the kernel for this?
For the non-exclusive, the old flag?
Yeah. No, I mean the support which you added, are there any users right now?
All Qualcomm platforms, yes.
Any drivers? Do you remember?
So mostly audio, and I like for 6.19, I removed this non-exclusive flag from all Qualcomm audio drivers, and now they switch to shared GPIOs. And my goal is to do it for everyone and just remove that flag. But obviously, it's easier for me to do it.
I think those changes should actually be done and use it as a reset GPIOs rather than actually using it as a shared GPIOs, because that's where they belong to.
Oh,
right?
so
yeah. And my question was more of, does this functionality actually go to the frameworks rather than actually sitting with the GPIO? That was my question. So because GPIO, we will have a functionality on top of GPIO, for example, reset, or it could be something else. And in this case, it clearly demonstrated the reset GPIO already abstracted something what you did with GPIO, and it covers the use case. But do you see any other use case other than which actually directly uses GPIOs?
Yes. So like the thing I showed was power down. So that's not reset. Can you use the reset framework to service power down GPIOs? That was one thing. And I should have probably included in the list, but I basically parsed lots of different DTs to figure out what the shared GPIO functions are. And I had like a list of 25 of different functions. For the majority, I couldn't even tell you what they did, because it would be like some long name and very platform specific. So
we have a fair amount of platforms where we have not represented all the regulators because they share the same enabled GPIO. And in some cases, we have the fixed regulator, but we commented out because we couldn't request the same GPIO. And in some cases, we should go back and make sure that the regulator tree is correct now that we can properly represent this.
Yeah, I've been thinking a bit more about the use case I had with the LED and the switch, and I think it can indeed be fixed by having some intermediate driver, which is its own GPIO chip and provides GPIOs, one to connect to the switch and one to connect to the LED. And I think you could use the same thing as well. So I was thinking about calling it something like a wired GPIO. Compatible equals wired GPIO. And then we could also handle these multiple GPIOs connected to one physical one. Probably.
Or logical GPIO.
Yeah, I don't know how you want to call it. Basically, in my case, it would be a wired or wired AND bus. But in a generic case, something like wired GPIO, which can also be used for sharing one GPIO connected to multiple devices, all of them in output mode or mixed in output use cases.
I wanted just to go back to your question because I thought about it. So clearly, we never got to use there are some use cases where we can't use existing abstraction layers, and we just hacked our way around it. And I just figured, okay, let's just do it at least kind of properly, so that it stays at least consistent. Because right now, what we had previously was totally inconsistent. Now let's at least count it and synchronize. There's.
My concern.
I'm sorry for.
Sorry. My concern is that we are actually probably duplicating same things. Like we duplicated the similar functionality in the reset GPIO. Now we are duplicating the same in your patches, and in some other case we will duplicate in new framework as well. So it's duplicated everywhere, providing similar functionality.
It's not duplicated. It's answering to Dimitri's question that the reset the GPIOs have a meaning, and in the reset, this is why reset framework is suitable for that case, because the devices know that it's the reset GPIO, right? For the regulator also, devices request regulator, right? So this is why maybe it has to be device specific. But I think, Dimitri, you had a hand.
There was another question over.
Yes, so I guess going to reset GPIO, is the recommendation to convert the drivers to reset framework for the ones that are using currently naked GPIO for reset?
I have an answer to that. So there are two groups of users. Ones that are simple, and there is no recommendation, but they could use reset GPIOs. And there is another group of users that I've identified. They have entire sequences for reset, and that includes delays, asserting, deasserting. And to that end, I have an idea, but I will probably present it next year for plumbers. It's a conjunction between the reset GPIO, shared GPIOs, and power sequencing. But that's.
Are you gonna work in regulators in it?
I'm sorry.
Regulators usually also, I guess, participate in the power sequencing.
I have just an idea, so I still need to sit down and figure out exactly what he's doing. Okay. There was another question. I'm sorry. Yeah, it's good. Okay.
Last. Extending the suggestion of representing the logical meaning of the combined GPIO, presumably in the device tree. Like, my question was like, would that then have some way of specifying the voting logic, right? Because right now it looks like shared GPIOs all have the same voting logic, but that might not necessarily cover all cases where you might need a different voting logic based on the specific use case of the shared GPIO.
Thank you. So we have still one talk, and after this talk there will be break. So stay alive.
So hi everyone. Sorry for the mask. I got a cold during the first evening event. So we'll talk about power sequencing on enumerable buses and what's still missing from the device tree and or the kernel. So my name is Chen Yu. I work on Chromebooks, ARM specific at Google, also maintainer of the wireless RegDB project, and on the side, maintainer of all winner SoCs. So an enumerable bus is a bus that devices connected to it can be enumerated if provided that they are operational. Now, making the device operational requires some additional setup. Now, on x86, this is done by ACPI. On device tree platforms, we have to describe it. Now, the buses all covers are SDIO, USB, PCIe, and MDIO. I'm not sure if there's any others. So what's the problem? Device tree has some support for describing power supplies, clocks, resets for some bus types in a generic fashion. So you can have clocks or reset GPIOs or some supply under the device node, which is under some bus like PCIe. But the implementation or Linux doesn't really work for all of these cases. And there are some device bus types that don't really have this generic thing. So we'll look at some examples. First of all, SDIO. So this is what the MMC power sequencing bindings look like. On the left, you have a power sequencing node, which there's like two types, simple and eMMC reset. There's also a special one for some special device. And you describe the reset GPIO, a clock, and there's a specific driver for this, and it turns on the clocks and toggles the reset when needed. And under the MMC controller, you specify the supplies, and also you point to the power sequencing node, and that works pretty well. It's the MMC controller requires control for both the MMC core. MMC card core voltage and IO voltage, and eMMC pin chips do have a reset pin, and some SDIO devices like Wi-Fi, Bluetooth, they require some extra clocks and pin toggles. And the support for this was done in 2015 by Ulf. Supports SDIO-based Wi-Fi pretty good, and it works well unless you forgot to build the driver. So next one, USB. So there's this generic USB connector binding, USB connector. It has Type C, Type B, and Type A. Type C is parsed and handled by Type C drivers. We won't go into that. Type B is basically your OTG connectors. There's an ID pin, there's a VBus regulator, the GPIO for detecting VBus. And this is basically handled by PHY drivers. There's a GPIO USB-B connector binding, which is also mapped to a PHY driver. Now, the last one is type A host ports, which is like the most common thing, but the USB-A connector binding is not supported in the kernel. There's no code that actually handles it. So you could look at this binding, write up your USB type A port and expect it to work, and it doesn't. Okay. And there's this other thing called onboard devices, which handles things like soldered on switch USB hubs or other USB drivers, which we probably won't go into. So the problem is these type A ports, the VBus for these need to be enabled for USB to work. Now, they're handled in some ad hoc ways. We do have things like VBus supply under the HCI node. We have VBus under the USB PHY. We also have a combination of both, or we have none. The U regulator is set to always on. So that's like very ad hoc, and there's no generic solution for this. And like everyone's doing their own thing, and probably want to fix that. Yeah, so this one is the PHY has like two actual PHYs, and then each PHY gets like its own supply. But PHY supply was supposed to be used to describe the power supply for the actual PHY and not the VBus. So that's also an error here. So that's USB, and it's mostly the type A ports that aren't working. Now PCIe, as Manny mentioned in his talk this morning, currently some of the device drivers, the PCIe controller, they have reset GPIOs or supplies under the host node. On MediaTek, we wanted to add that, and we got shot down because there's this new power control thing coming up, and so that was kind of delayed. And recently, I wanted to okay, now it's in. Now I want to use it. So I wrote this thing. The PCIe slot description represents the PCIe slot as a PCIe bridge, and you can give it supplies, and it just looks at all the dash supply properties and grabs all the regulators, and that works, except it actually violates the PCIe specifications. So the current status quo for PCIe is that standard hardware sort of works. There's some violations of the spec. Device-specific power sequences, like for Qualcomm, they actually work properly because there is specific drivers for that. Now, new users are supposed to use the PCIe power control framework and the power sequencing frameworks that were added recently in 6.11 and 6.15. However, if you're using the PCIe slot bindings, the way it currently works in the kernel is that the driver will do, the PCIe controller driver will do some sort of setup and power on its own regulators or PCI, the PERST reset pin, and then it'll get into the PCIe power control framework, and then that will create the device for the framework, and then defer probe. That device probes and then triggers a rescan. But in some drivers, there's actually they do link training before jumping into the PCIe core, and if the device isn't powered on yet, the PCIe link training just fails and it just errors out. Workaround was to ignore the link training timeout and let the power control device probe and yada yada. But again, it's like a violation of the PCIe spec, which requires you to hold the PCIe reset until the power supplies are stable. As I just mentioned, sorry. So for PCIe, Manny has proposed some changes for power control APIs, and Manny has also proposed bindings for M.2 E key and M key slots, though USB isn't covered in this yet. And that's for PCIe. And last is MDIO. So MDIO is basically a bus for controlling Ethernet PHYs and Ethernet switches. So currently there would be an MDIO bus node, and then under that there would be PHY nodes. So right now you can write the MDIO reset in two ways. One is under the Ethernet PHY, the other is under the bus, and you would expect both to work. However, it doesn't. So this is a direct quote from a commit I found. Basically, how the network stack works is it scans the MDIO bus first, and it reads the PHY IDs, and based on those PHY IDs, it creates PHY devices, which you then attach the reset to. Now, if the PHY device is held in reset, then you obviously can't read the PHY ID, and then you never find it. And the workaround is to move the reset into the bus and not under the Ethernet PHY, which is kind of backwards. And this is another response from Russell King saying that basically to make it work in all cases, you need to put it under the MDIO node.
Yeah, note to Christoph, adding the PHY ID in the DT causes a warning and would fix half of the classes of the warnings we currently have in the Renesas ARM32 DTBS check. Just for your information.
Okay. Also, there's also descriptions for clocks to the PHYs. That's given in Ethernet PHY YAML. But it doesn't work for all drivers. It's only supported in some PHY drivers, and it's not in the core either.
I recently ran into this kind of a weird problem that some of the PHYs actually require clock during reset. So the PHY drivers sometimes enable the clock, sometimes in probe, sometimes they cannot do power management at all because they have to keep the clock enabled. Some Macs do not even expose the clock. Is this being somehow sorted out? Because it seems to be a serious mess.
It's not. I counted like 4 or 5 drivers that support clocks. Yeah. Last is power supplies for the PHYs. And you'll see like random properties for these. And it's all under the Ethernet controller and not under the PHY node, which is again wrong. It's not the correct description because the supplies feed into the PHYs and not the Ethernet controllers. So there's basically nothing generic for like power supplies for MDIO devices. And for most of the PHYs, it just requires like one core power supply and then one optional IO voltage. So I'm thinking maybe you could do something there. Now I have some idea on how to like fix the reset, handling the reset before the PHY ID scan thing. Just haven't gotten to it yet. And then we could add like power supply and clocks to it if it's wanted. So to recap, for some buses, this generic description worked well for SDIO, for Type B and Type C USB connectors. There's some that sort of work but has issues. PCIe, MDIO, then for USB Type A, it doesn't work at all. There's also some custom descriptions. So the question for everyone is, do we want more generic descriptions? And yes.
Especially MDIO is such a pet peeve because we often end up having multiple device tree targets, and the only difference is the hard-coded PHY ID. Yeah. And we could easily detect it dynamically. We just can't because we cannot enable the relevant power supplies. And something generic like a stub driver that would bind to the device parse its supplies and enable them, and then we could. I know.
But even it, like the question from Eric was like, you do not know the timing for the enabling the power sequencing. But in the cases that I showed, basically it's the Ethernet driver that's enabling everything, and it doesn't really care either. It just enables them all. Yeah.
Something that works for most cases is still better than something that works for no cases.
Yeah.
So I think you missed two other things here.
Yeah.
There's like we have two other buses which actually do the same thing. That's SoundWire and SlimBus. We got to write the new bus. That's why we actually incorporated this power sequencing in the probe itself. So typically, all the drivers which use these buses, they have to power in the probe, and they get a callback when it gets enumerated. So that's why we solve this problem neatly with the new buses. The problem I see here is because we are using a generic bus or a pseudo bus, platform bus in this case, which doesn't well define the power up use case, right?
Yeah. So it's two problems. One is there's no generic description, and the other one is core support for handling these generic descriptions. Yeah.
So yeah, if there's no API, I guess, to be honest, for the driver to actually power up your device, and the driver framework doesn't provide that kind of API before the probe. So
yeah, it's a chicken and egg problem. You have to enumerate the device first to actually match the driver, and then the driver does the power sequencing. Yeah. So we want more generic descriptions. Now, if generic descriptions exist, should we migrate everyone to it? That's a bigger question, especially for like DT and platform maintainers. And if the generic descriptions exist but don't work, should we fix them? I want to fix them.
Yeah. That may be super naive from me, but for USB Type A would be more difficult than just powering on VBus and only perhaps disabling it if we go into suspend and the controller cannot wake up.
I'm not sure where the question is. Sorry.
For USB Type A, would it not be as simple as just leaving the power on, maybe disabling it if we know that the platform is going to suspend and the controller cannot wake up upon?
Yeah, so that currently works if you describe the VBus supply under the controller node. It's just not the right description.
Right, and I'm asking whether there's more to this problem.
No, it's just the wrong description.
Proper hardware description. The problem is how to describe it properly, the DT.
Maybe something that's worth mentioning, the power sequencing bindings for SDIO are actually deprecated. I don't think they are a considered generic solution anymore.
Okay. I haven't worked on that for quite a while.
That was close. For MDIO, I spent and actually wasted countless hours due to the fact that we don't have a generic solution, that they actually implemented differently in drivers in U-boot and in the Linux kernel, expecting different DT properties. So I think that if we can fix that and migrate DTs to that, it's not just going to give us something easier for drivers, but for integrators, they will save lots of time not trying to figure out the differences between platforms, between drivers, and sorting on the mess. So I think would be really, really nice to do that.
I have a feeling that the supply description, the block description, and so on, this is already in the DT-PHY node, and it has to be the PHY driver that knows how to power on the PHY. Because when you look at the PHY datasheets, they all have their little obscure quirks. So I have a feeling it has to be the PHY driver that does all this special case handling. There is no real generic way to do it.
I think you're talking about like turning on the supply and then waiting for a certain amount of time and then toggling the reset.
I think it's two separate questions. So one of them is how should we do it? What should the generic solution be? But the other one is, should we have a generic solution?
Yeah.
And currently we have DT bindings for different PHYs that are structured very differently. So when trying to integrate a file in a device tree, bring a board, taking something, especially taking something from the BSP and upstreaming it, they also use different DT bindings. And I found myself trying to figure out why the Ethernet controller wouldn't work in U-boot when it's worked in Linux, and that's because drivers on both sides were expecting different things. So can it be done in a generic way where we can power things up, read the ID, load the right driver? Do we have to put the PHY ID in the DT? That's an interesting question, but I would like to have one way to do that that would then be used consistently by different platforms and different drivers.
Yeah, I think we're out of time.
Standardizing something is important. What we should standardize, that's maybe a bit of a more complicated question.
So I think we're out of time. Thank you, everyone.
So let's have a break and we'll be back in, I think, half an hour.
I should have done my homework and run DBS check before the session instead of after. Yeah. Because even 2 or 3 weeks before, because I started collecting data.
Just a standardized machine.
Other class of devices is actually something for your previous employer. And at this time we have power domains and blocks on caches, ETM3 debug blocks. Things like that.
Our domain is on caches, like L2 or L3.
Yes. Well, if the SoC also has some other CPU core, it can be moved from the other CPU core, and the other one is responsible for bringing up the main one. So it's perfectly logical that it can. So for the gig, I had a hard find, and I could add the clock and the power domain. So those don't give warnings, but there are still some other ARM-specific blocks. But the ARM people say, "Oh, the ARM cache all, it's running all the time. Why do you want to add clocks?" Power domains. Actually, the SoC has it.
Okay, it's valid device description, right? So they should accept it. I mean, if it has it.
Yeah.
There are so good PDA, you can actually reset the L2 cache, and then your CPU gets cut off from the interconnect. It's very interesting. But then,
there should be something different question, but the hardware description should be complete and correct. So that's that.
Yeah, but then you have to add it to the bindings, and then the binding, the maintainer of the block says, "No, I'm not going to add it because."
Well, maybe
you don't need it. This clock is fixed apparently on some ARM designs. It's the same clock as the CPU. It's running from, but on the.
No, you cannot have L2 cache on the same clock as the CPU.
Yeah, it's half of the clock speed on the Cortex A9s, for example. But still, they say no, it's this fixed clocking. Look at the hardware manual. But apparently on our SoC, it's gateable.
Only from there. Then you maybe dedicate a compatible for your cache.
Everything runs on power, so you can have a power domain. Everything has a clock. Everything has a reset internally, but it's controllable. Then something else. If it's there, then we tend to put it in DT, and then we don't get these warnings.
I don't think that the best maintainers object if it's really kind of representation.
I'll try again.
We usually
give up.
Object when people hide stuff. The true case is to find the true answer because they case of abstractions and work around.
Most of these date back from the time that we were text bindings, so it was less obvious that there was an issue. Then it was just okay, they cannot add it to the binding. We keep it in the DTS, and then 10 years later, it ends up in your presentation.
You want to talk, right? Yes. Let's grab a coffee and some coffee. I'm not really expert. So, and as I said,
current implementation is incomplete. It's a good optimization because we have all those extra cycles and retries. Yeah, but there is things that avoids most. And I think the coach really helped us. And that's what I was trying to say would be. And as foresight, where you have all the different forces they depend on each other. So I have one platform. I think there's 200 lines in the kernel log when I do where it says that, oh, I have this cyclic dependencies that I'm allocating to ignore. So that all of it has or some of them stuff that there is cycles that solves it somehow. Then it's going to be incomplete. And therefore, I can't then say, oh, trust it. Oh, wow. Oh, wow.
Yeah, when you how everyone's working. We have some more people ready to.
Thinking about a patch series that's been sitting on the list for a bit. Yeah. Which Christoph had some cleanup stuff just touching RP message and or remote control or something. And ASOC. Which he figured should go through ASOC, which seemed reasonable for me.
Okay, so you want an act?
Yeah.
Okay.
So I'll just pick up the first bits and then I'll sort it out later, but you know.
Okay. Yeah, I'm not aware of it seriously, so I must have missed it or something. I'll take a look.
Yeah, I've got maybe in the future right now, but
yeah, I'll take a look. And,
yeah, it was like a week or two ago he sent it. It's been sitting for a bit, that's why I was thinking.
Yes, it doesn't ring the bells. I'm not sure.
Yeah, it's like const breakfast or something. I need to check exactly what it is, but it's a cleanup thing. It's not.
And it actually there was an actual dependency.
Yeah. Yeah.
Okay. Yeah, I'll take a look.
Okay.
But speaking of regulators.
Yeah.
So I see my regulator nodes or my regulator provider.
Yeah.
I have a whole bunch of regulators.
Yep.
And I have the supplies.
Yep.
For my device. And if I have one of the earlier regulators that has a supply, which is one of the later, I'm pretty sure that that used to work. And now I get a probe referral.
Yeah, it got converted to use probe referral because the custom stuff was causing problems. Some dude from Google has an issue where he's got interdependence between two PMICs, like both directions. So he's working on, or he said he was going to work on, I assume he actually will, series that will make every regulator get a dummy device registered so they can individually probe defer, which will get us back to where we were originally.
Yeah, because I had this problem 10 years ago when you merged something I did
to
make it work.
Yeah.
And now it's on board where, or now I work in you DTS and I couldn't get it to work.
Yeah.
No one has reported regressions.
No, we took it out and well, maybe nobody's, we couldn't find anybody who's actually still using it.
Yeah, no, but we definitely have the. I ran into that part where I have regulators where I define the supply to be a regulator from the site provider.
That Google series should sort it whenever they actually. It was like this recycle he asked about it, so we came up with
it. But I'm surprised because
I was kind of surprised we got away with.
I don't understand why people haven't complained to me.
So it's relative because of the way people tend to change these things. It tends to be you get a buck, all the bucks get registered first, and then the LDOs. And all the LDOs are that sort of supplies. So it tends to just work. You tend not to.
Yeah, but that's why I'm wondering why no one has complained, because all our PMICs is that, targets we have PMICs which are a mix of a buck and switch modes, and they have that interdependency on them.
Yeah.
So I don't see why any of them works.
So if you put the DC-DCs first,
yeah,
and the LDOs all depend on DC-DCs, not on each other,
yeah.
and there's no other.
But for some reason, we typically have the buck last.
Okay. In that case, yeah, you'll have trouble. It's just people.
Yeah, but that's what I mean. I don't understand why.
Yeah, I don't know.
I haven't had problems with this.
I don't have any Qualcomm boards. Well, I do have Qualcomm boards, but I don't have any of them plugged into anything. So,
yeah, no.
So I don't know. Yeah, no, it's most vendors just call them DC-DC and LDO, and then everything alphabetical order.
Yeah, we call them bulb for some reason. Yeah.
What's their bypass?
Bypass. Yeah.
I wouldn't.
Buck or bypass.
Okay.
Right, it's buck boost, either way.
Buck boost.
Down or up.
Okay.
Buck down, boost up.
Okay.
At least that's my understanding.
No, I think it's boost unless the input is sufficient, so you can just pass that through. So boost or bypass. Well,
or somebody just thought it was a cute name and then made the acronym to match it. I think it's probably more likely if it's that simple to tell.
Yeah. Okay, I'm happy to hear that someone's working on that because.
Yeah. It's not your specific use case, but it'll solve the same problem.
Yeah. And I'll take a look at my inbox, see what I missed. But
cool, thanks.
Coffee break now?
Yeah.
Yeah.
Oh, nice.
It's predictably busy. And you've been talking into the queue for the whole time.
Huh?
You've been talking into the queue for the whole time.
Oh, there's no one there. Dog fell asleep.
Thank you. So that's
2 minutes.
Hello? Yep. Okay. Okay. Hi, everyone. Hey, everyone. Recently, I started looking at SDCA, which is a soundwide device class specification from MIPI, and I hit an interesting problem on a platform which I was working. So I thought I'll share the problem statement, and I found some interesting solutions which are pretty controversial in some ways. So maybe we can chat about them and see how best to move forward. Yeah. So before I deep dive into the problem statement itself, I think many might not be aware of what the MIPI specifications I'm talking about. So I'll probably give a brief introduction about some of the specifications which might be relevant, which are relevant for the problem statement itself, so that you can actually get the context. Right. So MIPI has like a series of specifications around audio, and the most interested specifications which matter for this problem are these. So let's start with the first one, which is a MIPI Disco. MIPI Disco is a discovery and an enumeration of devices on the MIPI protocol, MIPI compliant protocol specification. So they're most heavily written for in the ACPI based, and then there's a next soundwire, which is as an audio specification written by Audio Working Group. Just to, it's another other audio bus specification, and there's a MIPI Disco soundwire, which is basically saying that you can it talks more about discovering soundwire devices on the soundwire bus. The last one is the interesting part, which is the new specification, which is MIPI soundwire device class for audio. The purpose of this specification is more around how can we actually get an audio functionality out of your device without writing any drivers. So means having a pretty much a generic driver, and MIPI has come up with the specification saying that, okay, if you define your device in these tables and in this format, you could actually use a generic driver. So currently, whole of the implementation is, whole of the specification is pretty much aligned to ACPI, and that's what its purpose. And currently, we have some the drivers written using FW nodes, and that means that we could reuse that same driver for DT as well. But the problem is, what does it mean for device trees? So how can we actually use the generic drivers for device trees? That's where the actual problem starts. So yeah, so We have these generic drivers for right now for Intel. Recently, it has been merged, and as I said, it is mostly ACPI, so it uses ACPI tables. But how should the device tree evolve? Device tree based devices drivers evolve. Should they be using these generic drivers, or should they be writing their own bindings? And should they actually follow MIPI specifications to start with? That is a basic problem statement. I have a few proposals. This is where I think the real discussion is. I hope you understand the problem. If you have any questions, please let me know. I can clarify. So the options we have is, should we replicate the SDCS specifications device tree bindings? That's the first question. And if so, the advantages is the generic drivers will work out of the box. The disadvantages is the SDCS specification has register sequences. So it also defines topology of the audio subsystem, including the entities, buzzers, and everything. But also it defines init sequences for the particular codec. So should we actually define a binding in a way that we actually encompass those register sequences? That's the first proposal. But yeah.
That's a question, or
no? That first option would work as well. But should we go into that direction? That's my question.
You say register level sequences. This is basically encoding some sort of register behavior in ACPI at the moment, right?
Yes. So the specification defines that you could actually encompass your register sequences in an ACPI table. And if you want to implement the same specification, the SDCS specification, that means we should also implement the same register sequences as the device tree bindings.
I'm just trying to clarify what you mean by the word sequences.
Sequences is init sequences.
Right. Okay.
Right.
So probably we would hate it to see the register sequences in device tree.
Yeah, we never did that, so I don't think that's the right way to go. But and the second option I have is, should we totally ignore the MIPI specifications and write our own device tree bindings?
I could live with it.
But so are you saying that we don't comply to the standards?
But does the standard
device trees?
But does the standard describe how the device tree should be written?
Nope, it would never do that.
Yeah, so I could see a compatible in device tree, and then you have a driver which implements everything based on this compatible, what's necessary, and this translates to whatever you need in your.
So we are not going to use generic drivers as the.
Yeah.
So
that I said that I could live with that, because my job, this device tree binding maintenance would be fulfilled, right? So that's work for me.
That's I think that means we're going to reinvent the wheel, and we're going to reinvent another driver which is probably specific to particular vendor, and that defeats the whole purpose. I think Mark wants.
Probably worth mentioning that there are generic class drivers for SoundWire codecs. So we may just have a generic driver for the thing, modulo the runtime patching that SDCA essentially allows.
Something similar we've faced with cameras and with MIPI Disco as well, was solved by having those init sequences in a firmware, a slow debugger driver. Is that a solution that could be possible?
Yeah, I think that's the third option that I was thinking of. So we have something called secondary firmware node. So as Mark was also describing, we could we could update the secondary firmware node to point to that firmware blob. The firmware blob could be an ACPI blob as well. Luckily in my case, it is an ACPI blob, which I can read, and I can tell my codec driver to point to that. And with that, everything works out of the box, and the generic drivers can be used.
So what would you put to device tree bindings? I mean, the actual ACPI data, or you would read this ACPI data from the firmware some other means?
So I think this is what I didn't try myself, but what I'm thinking is the codec driver will be probed from the device tree, and in the probe it will look up the ACPI table and set the firmware node, secondary firmware node.
And from the device tree bindings, it looks really nice.
It looks exactly as it is. It doesn't change anything. But the question, more of the question is, should we mix device tree and ACPI? That's a big question that I think if device tree maintainers are happy with that, then.
Isn't that describing a bit of a special case where we have a platform that has ACPI, which is for reasons unused in Linux, but then we use the DT and can read the SDCA data back from ACPI? What about platforms that do not have that situation?
Yeah, Mark has a comment there.
Sorry. So to me, this feels kind of analogous to the way we use PEP in ACPI to allow use of already defined DT bindings in a mostly ACPI system. It's doing the reverse thing and allowing us to use a binding that ACPI or people who care more about ACPI, it's not really ACPI themselves, have defined on a mostly DT system.
What about platforms which doesn't have the ACPI tables?
Yep. So that could come as part of your firmware from any firmware.
Any firmware. So we don't need to have the device tree binding for those cases?
No, we do have. So the way it's supposed to work is you have a device which it gets normally populated in your device tree, but the other properties which are not part of your device tree can be part of your firmware. And that firmware could come from ACPI, or it could come from another blob. I don't know what other blob would look like, but in this case, I'm more referring to ACPI blob.
Taking a step back, how different between different SoundWire devices those init sequences are? Because if it's just
they will
enable to the specification specified register, then perhaps there's no issue. But
no, there are. So the specification has vendor specific bits as well, so they are not going to be common across multiple codecs. They will be different. The topology will be different. Everything will be different. It's not.
Are there any common parts where there could be a stupid driver that gets some sort of sound working?
No.
Okay.
There's the class. There is the option. There's a spec for a generic device, which is implemented, and so you can get custom devices that need their own driver, or you can get generic devices that will work similar to USB audio.
I don't want to see us venture into the world where we boot at Linux, we detect there is a device tree, then we have drivers trying to peek into ACPI tables and extract bits and pieces of information. And I'm not the first one with that opinion, given that the specification says that you load one or the other. And the only reason why the specification says that, the system specification says that, is to avoid this thing.
But
and in particular, when we have, say you have an IoT device, in our case, where you boot off device tree, there's not going to be an ACPI table, and then forcing the product folks to write some parts of an ACPI table just so that it will fulfill those pieces. I mean,
that's a design. By design, the MIPI specification says that has to come from your firmware.
But then you need to define what firmware.
That's exactly the MIPI specification says. It has a set of properties that need to be part of that firmware, and set of sequences that need to be part of your firmware.
So are you? So you're talking about ACPI a lot here, but do you really mean the ACPI, or do you just mean pointing at the particular table in the ACPI that is the MIPI specified blob?
I think I'm pointing to that particular entry.
Right. So you're not actually suggesting parsing the ACPI, or something will parse the ACPI to make your device tree up on the platforms where that's a thing. but it could be if it's a pure DT system, then it could just be pointing to some memory mapped flash or something.
Yep, that's absolutely, that's possible.
So this could be also a firmware file on a physical disk, right? And you just have a firmware property in the DT.
Yes. Yeah, and somehow we need to.
But this, when you mentioned that the MIPI says that it should come from the firmware, the firmware is device 3, and device 3 says that data is on the disk because the firmware name is property is just
Yeah, that we need to work out this how the firmware file is updated. Should it come from dynamically from the ACPI table on the systems where it has some level of ACPI awareness, or should it come from a file if it doesn't have that awareness?
Do those sequences differ on platforms utilizing the same SoundWire devices?
So the sequences are specific to the codec. So if you have X codec, the sequences will be identical for X codec.
Okay, but you mentioned topology. Does that change between
the codec? If for a given codec, it will have the same topology.
So it's not a system topology, more of a codec topology.
It's a device topology. It's a codec topology. So that's what the codec has, its own topology, how things are connected, how entities are connected.
Right.
So
okay,
that is more of you're defining a codec in that blob.
Yeah. Thanks.
So when you say it defines the device or the codec,
it defines the codec device.
But what does that mean? Do you encode in that information how the PCB is routed?
No. It defines how the codec has been wired inside it. So, for example, you have a PCM decoder or volume controller, or XYZ mod entities, how they are connected, and what kind of control mechanisms do you have on those each entities.
So if I go to DigiKey and I buy a particular codec,
yeah,
that will have a certain set of that will have a static set of data.
Yes.
So
I mean that will not come a part of your codec, but it is available in some form in the ACPI content or somewhere.
But that's even more static than many of the cases where we today have put it in the drivers. For example, our 5 sequences, we have forced those into the drivers, even though many of our vendors wanted to put them in device tree, and that is in practice not static information. But we told the vendors that, hey, you have to put it in the driver, and then you have to invent all these extra properties to tweak your hard-coded values. But if what you're saying is that there is, for a given codec, there is a set of hard-coded values and they never change, then we should put that in a driver by device tree design.
So
I do not consider it plausible that vendors faced with this option will not put any system-specific or instance-specific tuning into those blobs. I do not consider that credible.
So you mean, Mark, the third option, right? About the third option, not credible.
No, I mean, like he's saying that the register write sequences will be identical. Like the topology, yeah, that makes sense. But the register write sequences being identical for every instance of the codec in the world. Yeah.
So I have not investigated, to be honest. I have not investigated all the register sequences. There could be some vendor-specific register sequences in there, and it could be. So there's.
But that's a rather critical part of us making a decision how we should design this. Because if it is static, then for all other cases, we have put it in a driver. And that would make sense. If it is something that depends on PCB or tuning or anything like that, then we maybe want the driver with some tunables or fully option 3.
So putting it in a driver, how are we envisioning that to go into driver? You're going to write all the register sequences in the driver with all the properties and topology definitions into the driver, and
exactly like for example, the PHY drivers.
So that means you're actually going to write a firmware inside the driver and pass it into a generic driver.
Yep.
Why not commit from the firmware itself? Why do you want to
There
put
is
it in?
no firmware.
No,
What you're saying is, how can we create the firmware so I can pass that to my driver? And what I'm saying is, take that firmware, put it in a C file, and commit it into the kernel.
I mean, that's how like all the I2C and SPI codecs work. Is they're in 90% of the drivers is enormous data tables that we pass to the core, and the core does its thing.
Okay, I can try that. I think that's another way to solve the same problem, I guess. But it will be in a pretty much ACPI tables, and that's what it will look like. The driver will look like.
It's not only about the static part, but in device we kind of don't want to duplicate things in the DTS, which are implied by compatible. So the compatible tells you that this is a microphone from whatever supplier, right? So
yeah,
this compatible defines all the other sequences. Therefore, the sequences should not be, or it is functions, right? You will not, if it's microphone, you don't need to put information that it's a microphone second time, right?
Right. So there are two parts, right? There are the topology definition as well as the init sequence and other stuff. So are you saying that we're going to write all the ACPI tables in the driver and pass it to the generic driver?
I mean,
okay. If that's what acceptable, I'm fine with that as well.
No, I'm not saying that you should write ACPI tables in the driver. But I'm saying that you should take the structure that we normally put in ACPI table and you write C code that encapsulate that structure. And the benefit of that is that it will be readable. And it follows our how we typically deal with this. If you, on the other hand, you come back and you say, no, but all this is just dynamic. Then we need to look at how can we pull this out of a firmware.
Right. Again, the question back to generic driver: how are we going to feed it into a generic driver? So the generic drivers accept the firmware interface. That's what it expects. So we need to somehow convert all of this data into a firmware node or whatever software entities or software nodes.
But does the generic driver operate directly on the ACPI data?
No, it works on firmware APIs, FW node APIs.
Yeah, but does it parse out the ACPI, the information from ACPI, create some representation, and then operate on that?
Yes.
Because in that case, you can write C code that generates that intermediate representation.
So it parses out the firmware node, and it creates some audio entities based on whatever the values are as part of that firmware node.
And what if you write C code that creates those objects?
And then pass it as a firmware node to the generic driver, or how do we do it?
No, I suggest that you extend the generic driver with an API that takes your objects that you have created. Or
okay, so you're saying that you somehow extend the firmware. So right now it calls firmware FW node APIs, and if I pass an arbitrary structure or something structure which belongs to this particular driver, then I have to modify all the stuff. Yeah, that's.
I mean, there was a talk from Bartosz on OSS, and maybe the talk answers here.
The software nodes will work. Yes.
Yeah, but you have a parsing stage into some sort of representation. Then you walk the representation and program the hardware.
No, we have a parsing state, and then we directly initiate the ASOC.
You loop over the firmware node properties, and you just shove that straight into the hardware. That's
yes.
the generic driver.
Yes.
No intermediate representation. No.
There is no intermediate representation.
Okay.
There's no point in intermediate representation. Why?
Well, there is totally a point in some
case, but yeah, in this case, it doesn't need to do that. Right. So right now we don't do any intermediate representation.
Yeah. No, I don't think that you should rely on, or I don't think you should try to create the representation such that the current parser will just magically work.
But that's the point of the specification, isn't it? The generic drivers are supposed to work.
It doesn't say how Linux should write that, how we should write that driver in Linux. It specifies how we should define the data in an ACPI system, and it should specify what the OS is supposed to do. But it doesn't specify like exactly what the call sequence in our driver should be.
To some extent, it does. How do you parse the data is defined in the MIPI specification. The parsing logic is also defined in the MIPI specification. How we should iterate the complete data structure. I mean the tables that is defined as part of your ACPI. As part of the MIPI specification. Okay, any questions? Lauren, I think you had similar issues around the Disco side of things. So it will be interesting to understand a bit more of how that was solved. You said you passed it as a firmware blob or a binary blob.
Right. So there are two things actually. There's a MIPI Disco for imaging, and that describes how the camera sensor is connected to the SoC and all the things that go around that. And then in the MIPI CCS specification, the camera command set, it specifies that initialization sequences, and even more than that actually, can be stored in a platform-specific way. It doesn't tell how it's stored, but can be provided by a platform in a binary file. So the generic CCS driver will identify the sensor, and based on that identification, we'll use the firmware API in Linux, or request firmware, to load a firmware from the file system that contains an initialization sequence. When it comes to the MIPI Disco for imaging, which is a bit closer to what you're doing here, the trouble with that spec is that it's not really widely implemented, so we haven't done much with that. Intel typically on their systems do something that's very custom, and they said it would use Disco for imaging in parallel to the vendor-specific ACPI data because they didn't want to modify the Windows drivers, which means that having two copies of the same data in ACPI, one used by Windows and one meant for Linux, means that the one meant for Linux is completely incorrect and unusable. So we haven't really tried to do something with that because there's no system there in the wild where it can be used at the moment.
It'll be interesting if they come up with something like camera class specifications or something like that, which will be interesting case. Yeah, thank you.
But the specification states how a vendor should describe this system, and the premise for your solution is that you're not going to consume that vendor description anyways. So, are you really following the specification, or are you really implementing the specification?
Yes. That's what generic drivers implement, right?
I mean, there's two ways. So one is it says that we should encode this information in ACPI.
Yep.
And in the platforms where we don't have ACPI, well, then we're not following or that platform isn't following the specification. Or when it's if we're using device tree and it says it should be in the firmware representation, then we need to put that information in device tree. But if there's that definition, so I don't see that we're implementing a specification anyways, or we're not consuming a specification anyways in a device tree system.
Yeah. Okay. Thank you. Thank you all, and it was interesting. Cheers.
Konrad, I think it's you now, right?
Are we good with the recording?
The recording is actually working.
So okay.
It's just the clock on this machine is stopped.
Okay, so I'm Konrad, and some of you probably know me already. Work for Qualcomm, a lot of DT review, and I assume most people in this room either read, wrote, submitted, or reviewed DTs at some point, and you probably know that it's annoying from both perspectives, being a maintainer, being a contributor, or just trying to do anything with it. And it's really a shame that we don't have any tooling to make it easier, because that sounds like a great job for a computer to do. So I have this short agenda. I'll reiterate the problem in case it's not, or to make sure we're on common ground, and then the other points. As of 6.18, there's over 3,000 DTS files. And that's DTS, DTSI. They all suffer from the same issue. It's not exactly the number of targets, but it's more than the compiled ones. And it's all the normal problems that come with a language, essentially, that has no standard format, because the DTC only makes sure that it's syntactically correct and that it can be compiled. and the specification itself does not really make any assertions on style. And so everything is left up to humans, which is a problem because humans have opinions, and very often they have differing opinions. And it may be that on one day you're asked to do X, on another day you're asked to do Y, and when you switch workspaces to work on another SoC, you're asked to do not X and Z. And that happens a lot. I admit I'm part of this problem. And yeah. We really should get rid of it because there's a lot of problems, as you've seen throughout the MC today. There's more important issues to solve, and it really turns down contributors I've seen. We've lost at least a couple on Linux ARM MSM just because they were not having it with the review process. So there was a case where someone had quite a functional DT for a laptop that no one else had, and they simply stopped responding on the grounds that they felt that the reviewers were not taking them or were not interacting with them sufficiently nicely. And it was all around those comments that would come that are to some meaningless, but to us rather important, about the style being coherent. Because if we again maintain a couple hundred device trees per sub-architecture, it really becomes a mess if anything diverges. And that, of course, happens because we have device trees introduced in 2015, we have devices introduced in 2025, and no one goes around fixing the old ones, partly because the rules keep changing. And those are some of the most pressing issues that come up during reviews. So white space, ordering new lines, general file structure, and ways of using the DT syntax. Parts of it that are allowed by the spec and the compiler are really not to be used. There's a way to reference a node by its fully qualified path. So we can do ampersand, pretty sure it's curly braces, and then you can write out the entire DT path / SOC at blah, 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 /node / you can go on forever. And if we allow that, there's just too much room for error unnecessarily. I was thinking this should be implemented as some sort of a tool that could be ran both like cargo format or cargo clippy from the command line, but it should also integrate with the IDE so that we kill two birds with one stone. Both the contributors know where to look, and the maintainers can check that the contributor has done any minimal work, or we can throw it in the CI and have it check it. And hopefully we can, by coming to a set of rules, for example, we have a couple ones in documentation / blah, 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 / DTS style guide, but it's rather not fully formal. And some people have different interpretations of it. If we come to agreement of using only a certain subset of syntax or whatnot, we can then contribute back to the DT spec perhaps, or at least have some common best practices across projects. Yeah.
So I think that when I was writing the TS coding style, I already noticed significant difference between these different subsystems of SOC. And I think that we can make them together. I mean, the tool will be working fine, but you have to encode these differences per subsystem. So let's say I could imagine that each SOC maintainer will have a ini file or whatever that would be the file, which defines the style which he wants in his DTS. Therefore, you still be running one tool, right? But the tool will be operating differently depending on the SoC vendor. And that's the only way how you could agree on the style, because we'll have here all the different styles.
That's the whole point of the common style, is that nobody likes it, but nobody hates it either, right? So like, ideally, we wouldn't have to have something like a customization of the tool per subplatform. And sure, like it's going to be annoying, and we're going to create a bunch of Git changes, Git churn if we convert everybody over. But after that, then everything is consistent, and you don't have to ask questions of what are the differences between platforms, and everything is easier to read. Everything's easier to compare between platforms. If you want to compare, like, I have a device integrated on platform A and integrated on platform B, let me diff the device trees. You can actually do that because everyone follows the same rules. Even if it's nobody's favorite rules, it's the same.
Yeah, that's exactly my point.
That's for new stuff, but we have legacy stuff. Like some SoCs have like this structure: first SoC type, then name of the IP core, say SoC/minus I2C. The others have it exactly the other way around, and you cannot force them to this agreed style.
No, that's not this layer. So we're not altering the contents of the DT that are compiled, only the style of the DTS, because that's also a point of contention.
And we don't have to enforce all the rules on existing DTS, because this also might cause huge rewriting, which is kind of pointless, because some of the things are like just pure ordering. So backporting will be a pain, right? But the new one could follow. The question is whether you will agree, or Renesas or someone else would agree on a common style, let's say. Oh, comment was gladly.
Common style would be fantastic, especially when working with multiple vendors, because then potentially even DT overlays would be easier to handle. Like if you have a development kit with SOMs and you can plug in different SOMs into it, it would even simplify the DTOs.
Right. And in the Qualcomm tree, we've been sort of trying to enforce a style that has come out of many discussions back and forths. And it's still easy to miss. One, because it's humans taking a look at it. And two, because Git can try to be smart about resolving merge conflicts or rebasing, but it sometimes fails. And now we had this nice 3,000 lines sorted DT of nodes in the quote-unquote appropriate order. And now we have new entries that came out of an older submission that was not properly rebased and is broken again. And we only find out 2 years later after somebody else comes back to that platform.
Stupid question. So have you actually seen difference of opinion among the SOC maintainers about the style of the DTS?
Oh, just open any file.
So I was writing DTS. We have here one representative, which NVIDIA, which for example does not use the override by p-handle label in the board. It's full path. And
which should be forbidden.
I have just one comment about this detection of breakage after merges. Okay, so with device tree compiler 172, if you do DTC from DTS to DTS, the p-handles don't get resolved. So if you do like a DTC before your merge, after your merge, and compile from DTS to DTS, you would be able to make a diff between the resulting DTS and see whether they got merged correctly. I mean, with up-to-date device tree compiler, you can actually do a DTS to DTS and then diff the result.
Are you talking about using it with the inbuilt sort option? Because one exists, but it's not doing what we want.
Which one?
--sort or --sort in DTC. It exists, but it doesn't.
You actually will want to do a sort, but like what you will probably want to do is compile the device tree before your merge and get a DTS out of it, like a fully assembled device tree, but a DTS without the p-handles resolved, and store it somewhere, right? Then do your merge, and then do the same process again and get an updated device tree, and then look at the diff between those two fully resolved device trees and see whether your merge has been done correctly.
That would solve a different problem. I feel like.
Well,
Yeah,
once,
but the
once I've done
merging,
that, then so if I do that or add that to my procedure when I merge the patches, that means that I need to look at that and determine that this looks good.
Yes.
So
If you have a merge conflict like this.
no, but so one of the, well, yes, there is the case where there's an error in the merge, but it's fairly often that I get patches where when I apply the patch, the Git complaints, and then I see that, but the content looks good, so I add it, and then I failed to sort the nodes on their node address, for example. So the content is correct, but style-wise it's wrong. And then a week later, Christoph or someone sends a patch to me and say, hey, you can't sort, or your manual sort function is broken again.
Yeah, my point.
Yeah, no, and so I spend a lot of time with these stupid things that I would love to have a tool for. And also we have, I mean, all the engineers that we have that send patches, if they could have a check patch-like tool that tells them, hey, these nodes are wrong incorrect ordered, I mean, that would save us 2-3 revisions on any device tree patch. So that would be very helpful. And regarding the NVIDIA's full paths, I mean, I used to have that in the Qualcomm tree, and there were so many cases where it turned out we applied properties in the wrong nodes and so on, because we spelled things differently in the DTSI and the DTSI and the DTS, and yeah. So I would like us to just adopt a standard that works and don't have those kind of mistakes possible to happen, and then yeah, convince NVIDIA to take that.
Thank you. I would like to say we should have the truth earlier, like 2 years ago. It will save my team a lot of time. You know.
I would know.
Yeah. The question is true? It can do the check. I know. Can do the auto correction.
This talk is about our collective wish list for this tool.
Yeah,
we don't have a tool today.
Yeah, I would like that tool to have the ability to do auto correction for the device tree.
Oh,
my
yeah,
team
yeah.
can help for that.
That's the number one request.
That will help us a lot, save a lot of time to do the meaningful work instead of to formatter.
Yeah. And answering your previous point, generally when we have merge issues, the device tree doesn't compile even, because it inserts, for example, it may insert a subnode at the wrong point, and the DTC just refuses to work with that. Or the binding check fails, yeah.
Yeah, if we're adding a wish list, can we have the language server check against the binding and tell you that, you know, under highlight in your editor that this property is not valid for this binding, so you know you had a typo?
If we're parsing the tree already, I mean, might as well.
Doc is not called wish list. I mean, slow down.
Yeah, with Git conflicts are actually multiple issues. One of them is that Git does not have a proper strategy. It doesn't know that, for example, that the closing curly brace should, when there's a conflict, it puts it outside the conflict markers. While if it would be aware of DTS, then it could put the curly brace inside the conflict markers, and then there would be no conflict at all. And the other thing, of course, is I'm used to fixing and sorting all the time, because you have 4 developers working on the same SoC and they're sending patches to me. And of course, they base that on my tree from yesterday in Linux Next. And then they're all at the same place. And then I have to sort them all.
We at Qualcomm had this day one announcement, huge series with a couple thousand lines of device tree. You could imagine what went on internally when we're rebasing all of these patches. It was not fun.
A DTS-aware Git merge strategy could also, if you add 2 nodes, if both branches add 2 nodes, it could take into account the rules you have here. And sort if it notices you are adding this node and that node, that it could put them in the right order as well.
The imaginary formatter will already be parsing most likely device resources. I have a somewhat related need where I often find myself trying to, visually look for certain patterns in device tree. It would be awesome if this thing could also allow you to query device tree, find all the nodes with addresses from this range to this range, or with this and this property. Because right now it's just manual grepping for this kind of.
I assume that if they are sorted properly, meaning generally by address, it should be fairly simple to just.
Yeah, but sometimes they aren't. That's the thing. But, yeah.
Replying to what Geert said, there was recently an article on LWN about merge conflict resolution tool that's language aware. So that could be something interesting to look at. I don't know if it would support device tree today, but it does support a set of languages and improves the merge based on the syntax.
So it turns out that there are already 2 tools in development, both of which have 5 GitHub stars and maybe 2 users at most. One of which is made by Krzysztof. He didn't really announce it publicly other than maybe mentioning it on LKML once or twice. It's an extension to the DT schema repo, and it does the things that it says it does on the slide. And the other one is, and that's a funny parallel, a Finnish guy with no publicity decided to just solve many of our problems and didn't announce it to the world just yet. Perhaps it's just a hobby and wouldn't be big at all. And it has the features like you see. It's work in progress still, but it's written in Rust. It has a NeoVim and VS Code integration. And if I recall correctly, it also has a CLI. It's basically almost a compiler and more. And it really seems like a good base to take. I have not contacted this person regarding this tool, but perhaps that's what we should do, because that seems like a good starting point for us.
I have a quick comment. There is apparently another tool from Peng from NXP that does also some sort of something like this.
Could you say that again?
Peng Fan from NXP did something like this as well. Apparently, he's been developing it for a while. It's, I believe, in Python.
Okay.
And there seemed to be another Python tool, which at least is a tokenizer for device tree /parser. So I believe people are trying to solve this, but nobody really gets it to over the finish line.
Right.
People give up because it's more complex too. So PengFan stuff is written in C. It uses DTC compiler libraries to parse it and then output, and it's your task as a user to compare original with the output. So the tool outputs how it should look like. And this was, but he didn't finish this work. I started doing something, and then of course ran out of steam because it's much more complex than spelling. So I'm for the guy, Finnish guy.
So the way I found out was he contributed to one of my projects, and I just went on his profile, as I do for new contributors, and there's a repo called DT Tools. Huh, interesting. And well, perhaps we should finalize the DTS doc in the kernel documentation and take it from there. Because currently it's still, as I said before, it's not formal and possible to interpret only in a single way. So it still allows for some modification. It also has a clause that says that every sub-architecture may have stricter rules, which is totally not what we want. And being completely unbiased, I would like the rules to mimic what's in the Qualcomm tree, but we shall see where we land.
So any more questions, comments?
You have here chair. I see Jan, right? Is NVIDIA going to abandon the rule of overriding by p-handle? I mean, not.
Unless we make you.
There are reasons for that, so yeah. Well, the DBS check accept this, so I will not shame them in the next year's talk.
I would imagine that if when it's ready, we could have something like Rob's bot for checking compliance, perhaps as a running it for a Git commit hook. That sounds like it could make sense. So if there's nothing more, then I suppose thank you.
So I think time for Chen, right?
Should we wait for
What's the time? No, it's 1 minute. Keep going.
Okay, it's me again. So we'll talk about device tree metadata and how bootloaders pick device tree blobs and apply overlays. By metadata, I mean properties or IDs that you use by the bootloader to match specific device tree or configurations that it wants to use. Okay, let's skip this. So we're not going to cover the development kit expansions. I think talking in the hallway, it's a known problem. I think the bigger problem within this is identifying which expansion board you have on your development kit. And once you know which one it is, applying an overlay for it is pretty much solved. Now, having overlays, generic overlays for many baseboards is an open problem, but you can check out Bootlin's talks about hotplug of non-discoverable hardware, where they talk about some level of indirection for handling buses, bus naming stuff. So we're going to talk about consumer electronics. Consumer electronics, your phones, your laptops. Vendors love to do second source components. You can have 2 kinds of speaker codecs or 2 kinds of headphone codecs, 3 kinds of panels with or without keyboard backlight. And this kind of all explodes into like many dozen of SKUs. And right now what we're doing is like having one device tree file for each SKU or a set of SKUs, which gets pretty ugly. So the plan we have is to decompose these into overlays based on the components. So we'll have a base device tree blob for all the common design. We'll have a couple of overlays covering each of the components. And that's easy to do. I've sent a patch series to the mailing list about this because I only sent it this week. I'm sure no one has ever seen it yet. So it's easy to decompose your whole device tree blob, but then the question is, do we keep the SKU specific model names and compatible strings? Now, for boards, we use the top level compatible string to identify each board. Now, do we have to cover SKUs with that? If we do have to do that, then we end up with 1 file per SKU, which is like even more files, and we don't want that. So what do we, yeah.
I suppose a good high-level answer would be depends how much the SKU changes, because we've seen in some laptops that just changing the panel alters the power grid, which is a more invasive change.
Mm-hmm. Yeah, so
Hey, so if you have a base DT and apply a bunch of DTOs on top of it, don't you have a unique DT as a result from which you can then again infer the SKU?
Yes and no. So we know the combination, but we need some sort of identifier for this combination. And I'll get to that in a bit
You
later.
can only override the top level compatible value. There's no way to append to it. For
Yeah, that's the other
if
problem.
you have three sets of different options each, then yeah.
Yeah, that's why if you do want like a SKU specific compatible top level compatible string, you need to like have a final overlay for that.
Hey, so I've been prototyping something for U-Boot, but this was a really early prototype. The idea was to actually collect all the DTOs that were applied in a top-level node in the device tree, and like when you apply the DTO, you would get a new entry in this node with the name of the DTO. That could be an option, but I'm not sure if this is acceptable.
Yeah, I mean, that's possible, but I think someone mentioned on the mailing list that we don't want the file name to become API. And there was also this proposal about having top-level compatible strings for each overlay that you could identify the overlay with, right? So the compatible string is important for the bootloader. It's not so much that important for the kernel. And for our cases, a more generic or base device compatible string could be enough. The model string pretty much isn't used anywhere. It's just like one line in the kernel logs. So can we decompose the board DTS files into a base design and overlays for the components? Yes, there are actually in-tree examples for this. I think it was an XP device. The extension to this is, can we move from SOC DTS include files to SOC-based DTBs? And that's a proposal from Doug. We probably won't get into that. And can we accept a not so accurate top-level model or compatible string in the DTS file? And given that we need some sort of identifier for like the overlays or for the whole combination, can we store this identifier within the DTS files or nearby, like in a YAML file or something? Because right now, what we only have is the makefile rules to do composite DTBs. And it sort of works, but then you have to like parse the commands or the makefile. Yeah. Any questions?
Yeah, back to the previous discussion we had. So why do you want to know the composition afterwards?
It's so to basically to build your kernel image or your DTB image, and then you need some sort of identifier to let the bootloader match to this configuration.
That's the problem you described now. Like, how do I select my different DTBOs? But when you have determined which 8 DTBOs you're going to compose, or you said that you wanted to encode that somehow in a compatible string or something. Is there an actual need for that? You need to pass the information about the composition to anything afterwards.
So we'll get into that with the fit image. Yeah, Doug?
Sure. I mean, I think that was just getting into the point of what's the point of the top level compatible string anyway, right? So the question is, when you make small changes because of the overlays, should it change the top level compatible string, and why does it need to? Gets into the overall question is, what the heck is that compatible string for, right? And that's what my mailing list post was about, and I'm happy to have more discussion on the mailing list about that.
That's an excellent question. Another thing is, one of the problems we have in the ARM64 laptop scope is when people report bugs, you have no idea which DTB they're actually running. And in the case here where the bootloader has stitched together some concoction of overlays and not, what is it that my system is actually running? So therein I can see that there is benefit to convey that information to not necessarily OS, but to some sort of telemetry system. Presumably also with some version information or something. In particular, if we treat device tree as firmware, then this becomes very useful.
Yeah, so I think Bjorn's question or proposal is more like after the kernel as loaded thing. And what I'm trying to address is something what the bootloader should use to load the kernel and DTBs.
The top level compatible value is your last resort to fix any issue that you have somewhere. So if there's some issues that you discover later in a board, you can use SOC device match against the top level compatible. So I think it's very important that each of these SKUs does have a different top level compatible value. Yeah, you were mentioning that you just have these make files to create final DTBs.
Yeah.
The kernel, for example, we have that. I think we could add an option to FDT overlay to insert some new top-level compatible value in front of the top-level compatible value that you already have. And I guess that you can also then in the make file specify the overlay, the flags to pass to FDT overlay when creating the FDT.
So
we already have rules like C flags for this object file append this, so you could use.
So if I understand correctly, you're saying we add like a new command to the DTC to allow it to insert the compatible string?
No, to the FDT overlay, which is the program you use to apply multiple overlays to a base DTB and create a new DTB.
Mm-hmm.
I have a proposal. Consider that you would add into every single device tree overlay a top-level node, say, let's call it config, right? And into that config node, you would add a property which would be exactly the file name of that DTO, right? Now, if you were to apply any such combinations of the DTOs, that config node in the result would contain exactly the list of those DTOs which you applied.
Mm-hmm.
And you wouldn't have to patch any tooling or anything. It would just use the regular DT behavior.
Yeah, I think that would work. It also.
Oh yeah, of course it would have to be unique, as he had said.
Yeah, I think that also covers Bjorn's case for like identifying the combination, and we can also use those properties to like work back to like which files to combine.
Yeah, exactly. And you can also probably work back in which order they were applied. And by the way, this is something which I already prototyped for U-Boot. There is a patch on the U-Boot mailing list from like last year.
Oh, well, I think the file name insertion to that config area should be automated because file names tend to get stale.
Yeah.
Not fixed.
And what about all the ways that the DTs are already being modified by bootloaders, like memory size and OPP tweaking and stuff? How do we incorporate that into this uniqueness? Because that's being done very commonly already today, but not being incorporated in any identifiable way.
Yeah.
After the fact.
I don't have any ideas for that.
Doesn't have to. I mean, the point of here it was not that the top level compatible has to represent exactly your precise model, right? But just a fallback for us to identify in the case you need to quirks, either user space needs some quirks.
Okay, so I'll also respond to that one comment. When I'm debugging any issues where also the bootloader is modifying the DT in any way, I'm always asking for the content of sysfirmware DTB from the running system. This way, I always have the device tree that the user was using, including the bootloader modifications. It's exactly what the kernel is running, as far as I can tell. So this is how you can get exactly what the user is running, no matter what SKU, DTBOs you have applied, and so on.
Yeah, I think that makes sense, especially for random devices that are not commercially produced. Yeah. For like top level compatibles, we could like have the bootloader insert the proper value if that is desired.
We could also alter the model string, or I guess what Linux makes out of it, which is the machine name after those overlays are applied, so that if we're already going to encode some sort of a name of the DTBO, we can just append it. So it's like my nice board 1 plus camera overlay plus audio overlay plus.
I think that's the problem with overlays.
But they don't show up in
The comment was
or whatever.
The comment was adding unique properties is easier than modifying a string, correct? Yeah.
So the machine name is useful to have when somebody gives you a D message to make sure that. But I suppose if you get a sys firmware FDT from them, you have confirmation. So maybe that's exclusive.
Problem with the compatible would be that if you run the validation on the DTB produced by the board, given to the board, the current bindings don't know that there will be any compatibility in front, and they will kind of fail. So we need to change the bindings. That's why additional property actually makes it easier for validation of the bindings.
Yeah. So I have some more slides to cover.
Okay, more questions? Yeah.
Yeah. So we currently use fit images in Chrome OS, and the fit image requires you to have a compatible string that maps to a configuration, and a configuration maps to a kernel image, maybe some RAM disks, and some DTB and DTBOs. So that's where the top level compatible string comes into. It's not for the DTB itself, it's for the fit image. The bootloader produces some list of compatible strings that matches the device it's running on, and then it uses that to match within the fit image to find the actual configuration it needs to boot. And if we're using like overlays without the last SKU specific compatible string, then we need some other place to store this mapping. Yeah, that's so like in this example, we have a base DTB and then 2 overlays, and then configuration 1 matches dev panel 1, and then configuration 2 matches dev panel 2. And we need some place to store the mapping of dev panel 1 to FTT1 and FTT2. So there's a tool, Simon Glass, that upstreamed called MakeFit, which builds the fifth image based on the kernel image and the DTBs that you give it. You can also decompose the composite DTBs into like the base DTB and all the overlays, but it takes the top level compatible string of the composite DTB as its configuration. So again, we need some place to store the mapping. Yeah. Any questions?
Okay, so for development kits, which can have extension stuff, essentially panels, what I do is I bundle DTs in the fit image, and I bundle DTOs in the fit image, but I bundle them separately. And then in the fit image, I include also a script which allows U-boot to auto-detect the board configuration and then pick up which base DT it's supposed to use, plus the DTOs. I'm never including the combined DT plus DTOs in the fit image. I include only the base DT and DTOs separately.
Yeah, well, that's what I want, but then you still have to know like which combination.
Right, that's why I have the script in there, which somehow figures out from the hardware what combination I need to.
Yeah, so what I'm saying is we need to store that combinations information somewhere near with the device tree source files. So anyone packaging fit images can use it, and you don't need to Google find some random wiki page to like figure out how to boot Linux on your Chromebook, essentially. Yeah, the comment from Jan sounds like fit configuration nodes need to learn about which set of DTBOs are applied as a separate property. Yeah, pretty much. Basically, yeah.
It sounds almost like you're saying you want to put a subset of the fit image source in, like, say, the kernel source tree next to the device tree source.
Yeah. So last bit is about Android. So Android has DTB images in the vendor boot image and DTBO partitions. So the vendor boot image is just a bunch of DTB blobs concatenated together, and the bootloader has to like go into each blob to figure out which one it wants to select. So we'll not cover this. Actually, I think today's generic bootloader, they're working towards using fit images for Android. Now, the other one is DTBO partitions, which has a format, and it has like 6 values that the bootloader can use to look up a specific overlay or a DTB, and then select based on that criteria. And it's not using compatible string; it's using like the 6 values. I was wondering if we could like put these values into the device tree source, because the tooling can actually fetch these properties out of the source and then insert them into the table.
Yes, we looked at that extensively, and the natural first idea was that we just squash them into some sort of compatible, and we end up with some sort of magical regex thing in the bootloader with fallbacks and things. Some of these numbers are have to be exactly matched. Some of them has to support fallbacks. Some of them has to support ranges, and so on. So, and as we see in the U-boot example, having a script that figures this out, and I believe in the Chrome OS case that you build your compatible string and you do some sort of matching scheme there.
Yeah.
Coming up with a generic format here, it's, yeah.
So my idea was just to like, we don't really care about what the format should be. We just put these 6 random numbers into there. Then whatever your tooling needs to do, it can do it. Yeah. Huh? Yeah, Doug. Doug, go ahead.
Sure. Yeah. So, I mean, one thing is, I think technically, according to the documentation, we are allowed to put information for the loader into the DTBO for overlays. If you look at the documentation, it has, you know, a little section that says before the overlay node, you can put information for the loader here. So it's intended for the information to be stored there, but nothing talks about what the format should be. I haven't made any formal proposal, but when I was talking about other stuff, I made a reference and said it would sure be nice to allow loader specific documentation. So you could add like bindings that say the, you know, MKDTBO image from Android needs these properties. And so define it, and any overlays intended to be loaded or intended to be parsed by MKDTBO image would look at that, and you would add those properties. And you could have different sets of properties depending on what the intended loader of the overlay was, or even multiple sets of properties if multiple loaders might look at these overlays.
Yeah, so I guess my question to the maintainers is, can we put bootloader specific properties into the device tree source? Because it's not used by Linux. Yeah, and that's all I have.
But that's still an ABI that we need to document.
Yeah.
If nothing else, just per vendor or something. So in this scheme, we're talking about overlays. Do we extend that to base DTs as well, so that we can store multiple of them and use the same selection criteria for?
I don't work on Android, so I don't really know. Sorry.
No, but it's in your fit image.
Yeah.
Is the fit image board specific?
We can do like platform specific. We can build like a fit image for the whole platform, like for all of MediaTek Chromebooks, and that still works. So it's not like board specific. We can do a unified image, and that works. I think that's all the time we have.
The next talk unfortunately got cancelled, so actually we have more minutes to discuss this, especially that the restaurant beer will be a bit further, right? So we can keep going. And answering the question whether we can put such properties to the DT, yeah, the consensus also statement from Rob was that yes, you can. He only wanted more than one user, and that's the standard rule, right?
I guess the question then would be like, is Android a big enough user?
No, more than one vendor in the kernel. So you need to get, let's say, Qualcomm, MediaTek on board.
Yeah.
Not
that makes sense.
That because so far such properties were per SoC vendor, and that was the problem.
If this is a close to Android problem, you could probably put this into GBL, and suddenly you have 1 billion users.
Yeah, but then GBL is moving to fit images.
Right.
Yeah, GBL is working on a whole bunch of things, I think. Any more questions?
But Christoph, why does it need to be a generic thing? Why can't we? That's like saying all I2C devices need to have the same set of properties, right? If Qualcomm is using a different bootloader for these boards and MediaTek is using a different bootloader, having them take different properties makes sense as long as you document it and add MediaTek bootloader bindings and Qualcomm bootloader bindings. Why is it a problem that they're different? They have different rules and different needs.
So I2C controllers have actually the same properties. So they have, for example, clock frequency. We don't have MediaTek clock frequency 1 and stuff like that. So this is what you select here is a generic problem. Therefore, there should be a generic solution, generic property for that one. That's why you need
some common properties, but there's some distinct properties also, right?
Yeah.
We don't just have a single I2C host controller bindings. We have, the MediaTek I2C controller bindings that extends the generic ones, but it's okay if there's some differences in there too.
And high level, a lot of these properties that we want to choose on are looking the same, or in a PowerPoint they're the same. But when we actually look at the very details, they might not be. And the criteria for, in particular those, how should you do matching? That might very well differ between the different vendors. And so I think that's where we ran into the problems when we looked at this a year or two ago, where we have the 6 numbers, and I don't think they are serving us. We probably need more. Might be numbers, might be strings, and so on. And I don't know if they have to be generic.
So I think the meaning of the property, so what exactly the number means, does not have to be generic, right? But another rule here coming from the device tree schema is that each property can have only one type. So, I mean, the one property can be only integer or string. You cannot have one property with 2 different types, and that's the limitation which have in this schema, right? So we need to agree on a type, set of integers, array of integers. The length of the integers can be longer, and the vendor will decide what's the integer has a meaning. Maybe this would fly.
But are you suggesting that it's a single property?
I don't know. I mean, could be single property, could be 2 properties, yes.
Because we have that thing we had in the Qualcomm binding where we use compatible, because someone tried to push us to actually properly represent in the compatible whatever the SoC or all these variants was. And that string was, I don't know, it blew the 80 character thing, and it was incomplete. Because, for example, there was only 1 PMIC mentioned in that, and we had like 12 PMICs in some board. So I don't know we probably need much more flexibility than just a series of numbers. And it's probably not going to be user friendly.
So how many?
Well, right now, apparently 6, but
doable.
But our 6 numbers are most likely not going to match what MediaTek has. And I can say that because Qualcomm's 6 numbers is not sufficient for the things that we had at Sony. There we had a few more axes of variability for handling SKUs and so on.
I don't have a comment on that, but there can be more than one property. So 4 or 6 properties, they could have different length, and this could solve the requirements of Rob in that matter, right? Are there any other comments? Well, then that would be it. So thanks, Dan. So thank you very much for coming. We were supposed to have one more talk, but I didn't get any response. And some hints were saying that due to the flu, there would be no talk. Therefore, that would conclude the session. Thanks for the sponsors for hosting us here. Thanks for the talks, for preparing the slides and sharing your problems. And hopefully, I will write some sort of notes afterwards and maybe send them on the device remaining list. So at least for some problems, I mean, some notes I remember, and then you can update them. Yeah. So thanks for coming.
So the chat will disappear at 6:30. So anything you want out of that, you can copy and paste down. Okay. Well, actually, I think that whole screen is. I don't know.
The matrix server will still be there, I think. The CVV will go, the room will go away, but the matrix server will stick around.
I think you're figuring out. Maybe it's the shared house. Yeah, but that's part of. Yeah, but what I mean is, it's right. How do you define this here? And your problem is that you don't have the problem. So how great it is to do it? Alex.
You are currently the only person in this conference.
Thank you.